Hello. Yes.
Hello. Hello. Yes, sir, we are able to
Yes.
hear you.
Okay. So you want me to share my slide, or you want to wait for that?
Yes, sir. If you want, you can share.
Yeah, just in case everything is working, and um, can you see my part? No.
No, sir, we are not able to see your slide as of yet.
Okay. Yes, I can see your something. Let me try. Okay, so at least I'm connected at the right place, and let me try one more time, to share. Okay. Yeah, can you see now?
Yes, yes, sir, we can see it now.
Okay,
Yeah.
okay. Very good.
Yeah.
So,
Maybe you can try a full screen and let's see.
okay,
Yeah,
now it's a full
that's fine, sir.
screen.
Yeah.
Okay, so now I
Sir, you
think
can
we
you
are
can stop sharing now.
okay.
Yeah.
Okay, just
The session is yet to start. We'll start sharp at 9:30 Indian time.
okay, sir. No problem. No problem. Let me stop sharing, and okay. So now it's ready. Okay,
Yes, sir. Thank you so much.
no problem. Thank you.
Hello.
A very good morning to all of you. I welcome all of you on behalf of NLS-30 in this third day of our symposium, where you are going to have many interesting sessions. The first session is on laser spectroscopy and applications. This session will be chaired by Dr. Vasdev. He is Rajaramana Fellow in BARC. Dr. Vasdev received his MSc honors in physics from Punjab University, Chandigarh in 1982, and he joined the erstwhile multidisciplinary research section of BARC after graduating from the 26th batch of training school. His work on development of frequency stabilized CO2 lasers and studies on dynamical instabilities led to completion of his PhD degree from Mumbai University in 1991. He was a visiting scientist to the University of Kaiserslautern, Germany during 1996 to 1998, where he was instrumental in proving first unambiguous proof of Bailey's phase in sodium trimmer. His recent interests include lasers and laser spectroscopy of lanthanides and actinides. Dr. Vasudev has guided many PhD students and published more than 100 research papers in various national, international journals and symposia. I request Dr. Vasudev to please take this session forward.
Thank you, Dr. Sabri. Good, good morning, and warm welcome to all the participants. Today, it is the third day of our NLS-30 and the first session, and which is dedicated to laser spectroscopy and its application. Our first speaker is Dr. Jagdish Singh from Mississippi State University. Dr. Singh, are you there? Dr. Singh, are you there? Please unmute.
Okay, yes. Okay, so now can you hear me?
Yeah, yes, we can hear you. Thank you.
Okay.
Aisha.
Okay.
Dr. Singh, good evening. And because the time, this thing, Prem, you will be late in the night. And for that inconvenience, we are sorry. And Dr. Singh received his BSc, MSc, and PhD degree from Banaras Hindu University. After that, he worked as a postdoctoral fellowship in McMaster University, Canada, and Kansas State University. Last 35 years, Dr. Singh is working in Mississippi State University and had developed many laser-based spectroscopic techniques. His interest includes laser-induced breakdown spectroscopy and coherent anti-Stokes Raman spectroscopy, and he had used these techniques for large varieties of work. And Dr. Singh has supervised many students, PhD student, MS student, and monitored large number of postdoctoral fellows. And he had published large number of papers, and he is a member of several scientific organizations and fellow of OSA and LSE. Today, he will be speaking on laser-induced breakdown spectroscopy application to nuclear management. Over to Dr. Singh. You can start.
Okay. So good morning, good evening, depending on where you are located. Let me try to share my slides. So can you just a second? Okay, so thanks for a nice introduction. So can you hear me now? Hello? Can you hear me?
Yes, we can hear you. Please go ahead.
Okay, so I can continue now, right? Okay. So I'm going to speak about laser-induced breakdown spectroscopy, application to nuclear waste management. As you know, like I'm now retired from Mississippi State University. I used to work there, but still, I go there. And then I have a, company called JPS Advanced Technology. And it is my pleasure to be giving this presentation in BARC. Of course, I am not there, but I was there in 1976 when Dr. Bhavalkar was head of the laser division. And I used to come quite often in India before COVID, like every year. So I am very happy that I'm giving this presentation to you all online. Regarding my talk, I will give you some introduction about my work, what we are going to present here, and then some experimental details, how we manage this nuclear waste. It's a kind of slurry. So we develop some technique how to analyze this kind of sample. Then I will mention about LIPS instrumentation. Of course, one of the things with the LIBS, laser-induced breakdown spectroscopy, is data processing. So I will show you how we process the data and get the information. So that is one of the challenging things in the LIBS technique. It's very easy to get LIBS spectra, but it's hard to get some useful information. Regarding LIBS community, I like to mention that I have started several international LIBS conferences around the world. Sometime I used to be the chair of those conferences. One is called International LIBS Conference. It's every alternate year, And then we used, I started something in 2007, NASLIBS, North American Symposium on LIBS. Of course, later on in 2015, it changed to NAS LIBS Society. Then there are other international conferences, on the LIBS. Even the Chinese LIBS Symposium was started also in 2011. Of course, Asian Sim. So there are a lot of activity around the world going on in this area. So there are various groups which used to work, are still working in the LIBS related field. There are a lot of application of LIBS technology. One I like to just mention is NASA in 2011 sent a rover, Curiosity rover to Mars. And luckily, still it's working and giving data regarding the Mars surface. So essentially, it can, tell you the composition of the, so that is working. So it's one of the uh, uh, interesting application of the LIBS. Even India, I sent that system to Mars. Unfortunately, it has not landed. I think it was also having LIBS for the measurement, regarding this particular application, I like to highlight the problem. Like during the Cold War, US was processing a lot of weapons grade plutonium. At that time, they stored waste in the big tank. Now you can see the size of this tank, 50 feet height and 80 feet in diameter. And so that time they stored all the things, and now, one of the problem right now, you can see with the time, those tanks got corroded. And the difficulty is probably they are started leaking, some of the waste inside the soil, or it might go to groundwater, and then that will be the main problem. So one technique they are trying to develop is something called vitrification. Like they try to take this nuclear waste and then add something, called glass frit, or do some processing so that they can make glass out of that nuclear waste. And this glass they can, put at one of the mountain they used to call Yucca mountain, and then it might last maybe 1,000 years. So that's the idea how to change a nuclear. And so one of the problem is how to analyze the waste. For example, they don't know what's the composition of the waste inside the tank. So you need to know the composition, and based on that, you can add some, uh, uh, chemicals, to make the right kind of glass, so that the glass won't leach. To do that one, right now the technique is ICP, So that means they take some sample little sample and make glass, and then dissolve that, you know, glass sample and then run through the ICP. This is the standard analytical technique, you know, analytical chemists they use. As I said, like in the LIPS, there are different types of people involved. Like myself, background is physics. There are some mechanical engineering people, chemical engineering, you know, plasma physics, you know. So in this particular process, I can show you the lip system. Essentially, you just need a laser, you know, and you just focus the laser beam on the sample. And sample can be solid, liquid, or even the gas or a slurry. But the slurry has its own challenge, you know, because it's a mixture of solid and water, you can say. So one problem is how to, you know, uh, avoid the settling down of the solid in the slurry. So the concept here is we are focusing the laser beam, and then essentially you collect the light coming from the plasma, and by analyzing the light, you can tell what are the elements present at the sample. So this is a slurry system, you know, circulation system we developed. And this is the typical composition of the slurry which they use in the glass. Again, there are some glass chemists involved so that they can develop a unique glass so that radioactive element, you know, they don't leach with time in the environment. So that's the glass people come. So one of the challenge or problem with the slurry application is, you know, with time it try to settle down. And also when you focus the laser beam on the surface, it creates shock wave. So that way you are creating disturbance at the sample surface. So one has to be careful how to avoid, and also the mist which generate from the surface might travel to your lens, and so that way you have to keep maintaining that kind of thing. So there are several problems, and one of the problem is because it had a lot of water, so it quench the plasma. So that means you have to optimize the system and work with that one to get the information about the slurry so that you can process the uh, nuclear waste. And one of the typical things we use with the LIPS is cell spectrometer, where you can see all the various elements at the same time. So this is a typical LIPS spectra. You know, you can see. So when you focus the laser beam at the sample surface, you see various, you know, atomic emission coming from the surface. And by looking this spectra, you can analyze this one and develop some kind of your unique calibration things. For example, in this particular case, we developed some calibration for iron, and which is standard things, and then you can measure the iron concentration in the sample. And then method I like to mention is simple, you know, you use stirrer to keep on, you know, stirring the slurry. That way you can get a uniform sample even at the surface also. So that way you are handling this particular case. As I mentioned, in case of slurry, you create some kind of disturbance when you focus the laser beam. So we try to optimize when you get a more stable signal. And you can see if you increase the frequency of the laser beam, you see more fluctuation in the signal. So we found out that at 1 hertz, like 1 pulse per second, you get better stable signal. So pulse to pulse fluctuation is less when you use 1 pulse per second. Also, as I mentioned, in one of the things in the lips to get information is process the data. Like you can see the pulse to pulse fluctuation in the spectrum is pretty high when you take intensity of the line. But if you normalize that signal or intensity of that particular line, then you get more, like relative standard deviation is less. Like typical is 10% and it reduced to 4%. When I use the word normalization means like you take the area of the particular line, let us say some particular line of iron, and then divide by total area of the spectrum. That's a software where you can do very easily, and that will improve the measurement. Relative standard deviation will go down. So there are various techniques which we use for this lips data processing or analysis. So another method we develop is something called spin coating, where you take a drop of sample and then you just spin and create on the glass slide, as you will see later on in this presentation. And for this measurement, one of the gentlemen from chemical engineering working with Savannah River site, and they develop four standard sample which we use for calibration, and then he gave one unknown sample. And so based on this one, you can see we process that information, and you will see how good this technique, because he wanted to evaluate our lips technique that is useful for the site or not. So in this one, you can see how we prepare the glass slide, and then we did the measurement, lips measurement. Essentially, you see again similar things like we have a laser beam which focus on the glass slide, and then you create plasma, and then again you are looking the plasma sending to spectrometer. Of course, it's a computer control everything, so you can process the data. So in any sample, either is in this particular case, spin on glass sample becomes some kind of slide. So the same way this technique can be applicable to liquid, solid, even in the gas also we have used this one. So again, we collected data, and one of the things is you have to optimize, the experimental parameter to get a reasonable spectra. So in this particular case, you can see with the laser energy, signal is going up. The same things in this one is the gate delay. One thing in the lips is you create the plasma and then you wait for microsecond, depending on the sample. Like in the case of liquid, it could be fraction of a microsecond, maybe half a microsecond. but if it's solid, it might be little higher, 1 to. So and that's where you collect the spectra. So essentially, you can see the typical parameter depending on what you are looking. In the slide one is around 22 millijoule per pulse, and of course the delay is 1 to 2 microsecond. So here we try to see the reproducibility of the LIPS data. So for example, we did this measurement at different dates, and the data you can see fairly reproducible from one date to other date. As I mentioned, one of the things in the LIPS is data analysis or data processing. So in this case, we use three methods. One is simple calibration, which is univariate calibration, then multiple linear regression, and then partial least square. And then we try to see the data processing technique, and they all give reasonably good results in this particular case. But in some application, one technique is better than other. So this is simple calibration for calcium, and this is for iron and nickel. Of course, for various element, you develop that one. And then basically you are trying to see how good this, technique is. So basically R square, you like to bring close to 1, 0.996. The same thing when we try to go through other one, for example, multiple linear regression. Of course, we selected different lines. So when using the statistical method, there you can have more than one line to use for calibration or to do the measurement. For example, we took several minimum line, of course, one select the right kind of line, and you can say R square, we try to again get reasonably good to do this one. So this is multiple linear regression results. Then we did something with PLS, partial least square, and again we try to process this one, and then we try to compare the results with ICP. So because ICP is some kind of standard things, and they like to compare how your technique is good compared to that one. So now you can see by comparing the three methods, they are reasonably good in this particular case, except you see in the silica, the variation is little more compared to the other one. And when we compare with ICP and the LIPS result, it looks reasonably good. So I think they like. So by using this technique, you can reduce the time. As I mentioned, they used to use the standard ICP method where they spend 22 hours to get the results, whereas using LIPS, you can get in half an hour. So in summary, I like to summarize that we have developed this slurry circulation system for this kind of measurement, and spin on glass sampling, and then we optimize the technique, and we use different data processing technique, univariate, MLR, things like that, and this one. This is one of my research group, and of course, as I said, I'm retired, so it's old, and most of the people, one was Dr. Bansilal from IIT Kanpur, one of my friend, now he's also retired. Even most of the people have gone to India, they are retired. One gentleman is IIT Guwahati, and couple of them are settled in US. The one you see. Again, as I mentioned, that is old group, and funding came from Department of Energy. And thanks for you all hearing my presentation. So I'll be very happy to answer any question if you have, by the way.
Thank you, Dr. Singh. First, you are completing your talk well within the time. And secondly, your talk was very interesting and informative. I think for the young students, it will be of great interest. I would like to ask one thing that you yourself said that in LIPS, getting a spectrum is much relatively easier, and then analyzing it and quantifying the things is a little more very difficult. Now, we people working in a nuclear establishment, we will be very much interested that how far it has gone, LIFS technique in quantifying those nuclear based. Now, when you compare with the standard analytical technique ICP used as compared to that.
Yes, sir. It's very good question and very interesting. One way I can mention at this point is this technique is good to apply for difficult environment where it's very hard to uh, do, and it can reduce the timing, and it's close to ICP, but it's still it will take some time to reach the standard ICP technique, because what you are doing here is trying to do everything together, like you are using same laser pulse to create plasma, uh, this way, and also prepare the sample. So it's a little uh, so accuracy at this time you can say one has to optimize and see. But in this particular application, what I was showing you is it can do the work for glass analysis for this nuclear waste management. But if you want to do something with very low concentration, then it will be challenging. But some of the unique application I mentioned, like doing measurement at Mars or Moon, are a place where you cannot take any technique, or you can take in the field. Uh, so it has a lot of unique application. But it's a good question. Still, people are working to look for particular application. There are several company, they are selling the LIPS instrument, and they are trying to, so this technique has been tested for several applications. Even it can provide you explosive, um, they are trying to develop uh, and standoff, like you can do the measurement from a distance, or you can use optical fiber to go the place where it's hard to reach. So for those type of unique application, even in the nuclear industry where it's very challenging, to get sampling or do something, this technique can be applied. But it's a good question. Still, uh, accuracy, one has to work with that.
Hello, sir. It was a nice talk. I have one question, especially for the nuclear establishment. What will be the usefulness of a calibration-free technique instead of calibration-based techniques? Because the radioactive environment, calibration-free, if we can make it, then I think that will be slightly better. Or what is your comment?
Yes, sir. Like there are several group, they have worked on calibration free measurement, and even there they have some patents and also some techniques. So basically, by looking the spectra you process, even we have also uh, published a paper in applied spectroscopy, where you can do calibration free analysis. So basically you are training your spectra by looking some of the spectra, and then you can go to unknown. But essentially, you have to train with the similar type of samples so that you can go to unknown sample. So yeah, it's possible, and people are working in that direction to use you know calibration free, so that you use all these software or program available to get the information by looking the spec. Of course, at some point, if people know more about this plasma and all those things, and they can put all the parameter, then it's easy to get the information by looking, you know, the spectral lines you can process without doing the calibration, which I mentioned. So it's possible, and it's people are doing that.
Hello.
Dr. Lokre want to ask you one question.
Basically,
Sure.
you mentioned that there is a spin-on glass sampling, but for the radioactive nuclear waste, how you do that actually? Because gamma radiation problem may be there. You are trying to do a spin-on glass sample of the radioactive waste. That is one question. Another thing, you are doing calibration. When you are doing calibration with particular species, you have to have similar composition. But since the composition is unknown here, radioactive waste, how do you take care of that?
Yes, sir. So essentially, like the glass people, they develop what type of glass it's going to be. So they know exactly the composition of the glass. Only the variable will be the radioactive things coming from there. So in that particular case, you know what type of sample are there. So that way, so you know the composition because they work on that one. And I agree with your spin. We developed this one and it gives a reasonably good result, but it's difficult to apply in nuclear environment. So it was just nice to publish a paper, but and for some application where you are dealing with the food industry or things like that, it's more, but not in the nuclear environment, sir. So I agree with you. But the other things is possible, like you do similar, because you know the composition of the glass which you want to develop. So it's easy to uh, do the calibration in that environment, and you change the things you want to measure.
Thank you, Professor. Actually, there was one question in the chat box. One Mr. Praveen Kumar Agarwal, he wanted to know, can you please throw some light on whether any other laser can be used instead of ND-YAG laser?
Yes, sir. In principle, any laser, the one which is available, cheapest laser in lab, because essentially you are focusing the laser beam and creating a plasma. So ND-YAG laser we use, one was a safety point of view because green light you can see, and most of the, but in principle you can use any laser, and suppose either infrared laser or UV laser, but different laser has, you know, its way, but any laser can be used, sir.
I think with this, we can come to end this question session. And again, I would like to thank Professor at sparing your time at this very late in the night and giving very interesting and informative talk. And I thank
Okay,
you.
sir. And anyone who has any interest or have question, just email. I'll be very happy to provide the information if someone is interested. And we have written a book on this one. We written in 2006, but again we put the second edition of that book. So I'll be very happy to provide the information. And it was my, I'm really happy that I saw the BARC, you know, because which I visited 50 years back. Okay, sir. Okay. Thank you, sir.
Thank you. Thank you very much.
Okay. Okay. Good night. Good morning. Good evening.
Thank you. So friends, with this we come to end the first talk, and now the second talk is by Professor Naresh Patwari from IIT Mumbai. Professor Patwari did his BSc from Osmania University 1992 and master degree from the Hyderabad University. Later on, he joined for PhD work Tata Institute of Fundamental Research. In 2000, he completed his PhD. And later on, he had worked as a JSPS postdoctoral fellowship at Tohoku University from 2002. And since 2003, he is with IIT Bombay as a professor. And Professor Tiwari had done a lot of work in this area, intermolecular interaction using both experimental and theoretical methodologies. And Professor Tiwari has been a recipient of Shanti Sru Bhatnagar Award in 2017, which is one of the very prestigious award in India. Today, he will be talking on intramolecular Coulombic decay in molecular clusters. Are you there, Dr. Patwari? Thank you. Over to you, please. Take over.
Thank you very much. To begin with, let me thank the symposium organizing committee, Dr. Nilaya and Dr. Nitin Kavde to begin with, and other members of the committee, and also to the chair for introducing me. I'm going to basically switch a little bit of gears and let me begin with share my slides. I hope you can see my screen. Can you see my screen? Can someone confirm that my screen? It is visible?
Yes, it is visible.
Okay. So I'm going to talk about intermolecular Coulombic decay in molecular clusters. So to begin with, of course, my group works on a lot of things. Here are the keywords that my group works on. One keyword that today I'm going to talk about is this intermolecular Coulombic decay. Okay. So to begin with, let me define what is intermolecular Coulombic decay. Of course, we are not the ones who coined this word. Okay. Intermolecular Coulombic decay is basically a energy transfer process from one molecule to other molecule. Okay, but when the energy is transferred, okay, what happens is it's a bound to continuum energy transfer. So there are a lot of energy transfer processes. For example, FRET is an energy transfer process. Frosters resonance energy transfer process. However, Coulombic decay is a process which, by the way, FRET is a bound state to bound state energy transfer process, but Coulombic decay is a bound state to continuum. So when you have continuum, then you one of the things that can happen is eject electrons. So it ejects electrons and forms ions, and these ions can be detected. Now you can realize that when you have bound to continuum decay, the kind of energies one is talking about is at least about several EVs. Okay, most molecules and atoms have several EV of energy that you will need to eject an electron. Typically, what you do is that if you want to transfer this electron and energy efficiently and kick off an electron, ideally, what you would like to do is to excite the inner valence electrons or core electrons. Okay, so generally in the intermolecular or interatomic Coulombic decay, people excite the experiments that are known use very high energy photons to excite core electrons or inner valence electrons, so that there is a sufficient energy transfer to kick out the electron from the partner. And in generally, By the way, there is a nice review which appeared a couple of years back in Chem Reviews, and one can see that generally it is a very broad process, can happen in gas phase clusters and can happen in liquids, in aqueous systems. And most probably what you do is the excitation mechanisms are these. You use synchrotron radiation or particle beams or free electron lasers, and these are all high energy sources. Okay, and then you can choose a method, okay, like electron spectroscopy, ion spectroscopy, and coincidence imaging or fluorescence. You can choose a methodology to detect whether this process is happening or not. That's about, and where do we come into picture? I'll tell you. So our journey towards intermolecular Coulombic decay is kind of, interesting, and I will share you in next 15-20 minutes how we ended up with the intermolecular Coulombic decay. About few years back, we were working out on hydrogen bonded complexes using a technique called IR UV double resonance spectroscopy. The details of IR UV double resonance spectroscopy is for some other day. Today I'm not going to talk about it, but what it essentially does is it selects, you will be able to record IR spectra of size selected species, okay, and when you record spectra of size selected species, IR spectra, then you can figure out what the interaction is. For example, we start with this molecule phenylacetylene, okay, and then when we start adding amines, okay, when you add ammonia, it goes in this fashion, which is nothing but the CHN hydrogen bond. But when you take methylamine, okay, then it goes in a slightly different fashion, that is NH pi. So what we did is, here we could just change the structure of the way two molecules interacted by adding just one methyl group. So what I would call it as a methyl group induced structure switching. And if you add a lot more methyl groups, then of course this is going to be something like this, called CH pi. Okay, and these kind of clusters are examples for hydrophobicity. So when you have molecules that are not hydrophobicity, rather hydrophobic effects. Okay, when you have two molecules that don't like to mix with water, then what happens is they come together via small interactions which add up to a large value. Okay. And then what we did was, instead of so essentially what we did was we could switch the interactions between molecules by adding without changing the real the functional group of the molecule. We could just switch by adding methyl groups. Now what happened is that later what we did was we were trying to add, instead of taking the phenylacetylene, we added 2 fluorine atoms, okay, and then did the same exercise. When we did the same exercise, what we found out is that we could keep this mode of interaction common, and to add that we could actually get more interactions. So now what you have is you have plethora of interactions between two sets of molecules, and then you can switch between one and other depending on how you are looking at the experiment. But when we were doing these experiments, then we caught attention. We could record the spectra, but then we caught attention to the fact that, okay, when you record spectra of this difluorinated compound with either methylamine or dimethylamine or trimethylamine, we will not see the parent peak. Okay, we only saw the spectrum, in the mass spectrum, we only saw these cations. Even though we were ionizing the entire parent molecule, we would not see the parent molecule, but you will only see the fragment. And the fragment was not on the chromophore. So this is your chromophore. We were exciting the chromophore, that is the benzene ring, but the fragment was from the partner, not from the benzene ring. Okay, so we were a little bit confused as to what was happening, because you are exciting somewhere else and you are seeing the ion from its partner. And as I told you, when you excite A and you get the ion of B, one of the decay mechanisms is the intermolecular Coulombic decay. So we kind of figured it out that it could be Coulombic decay. Okay. So what we find is we take this cluster, which is together, in which this benzene ring or the phenylacetylene is bound to dimethylamine or trimethylamine, very simple molecules. And then when you ionize using a resonant 2-photon excitation, what you end up, you detect is only the cations of these. Okay. So you can essentially think you start with AB, 2H nu. What you get is, what you're supposed to get is A, B. But what you actually get is B plus and not A plus. That is, even though excitation is on A. Okay. So you excite A using a 2-photon transition, but you get B plus. So one can think that this is the bound state of A is getting coupled to the continuum state of B. And that's why you are getting B plus. And that's your intermolecular Coulombic decay. And one of the ways to look at it is the following. So if you are A, in this experiment that we were doing, the total energy of the photons 2h nu was equal to 8.86 eV. But ionization potential of A was 9.11 eV. This is your A. But ionization potential of B, which is nothing but 8.32 or 7.82, depending on whether it is trimethylamine or dimethylamine. Okay. So of course, the total energy that you are putting in is more than the what you have for the ionization potentials of B, either this or this, but less than A. So you go to very high excited states of A and transfer the energy to B so that you kick out the electron from the B. So this is a mechanism here. So you excite A below its continuum. However, this energy is, you excite A below its continuum, highly excited state, but below, which is above the continuum of B, and the charge transfer will happen, leading to ionization of B. And of course, you have the when you kick out, you get the you have to have the kinetic energy of the electron and the kinetic energy of the fragment. One can do a simple math and figure out whether so this is the total energy that is available, 0.54 eV. Okay, so that must go, or 1.04 eV, depending on the molecule that you choose, and that is the amount of energy that you will have as a electron kinetic energy, supposedly. Okay. And then when you fall it apart as an asymptote, you will get the kinetic energy of the fragments. So what we wanted to do is we want to measure the kinetic energy of the fragments. Okay, so this is the process. How does it work? So what you have, initially you have a hydrogen bond, in which this delta positive hydrogen atom is going to interact with the delta negative nitrogen atom. Okay, this is hydrogen and this is nitrogen. So you have this hydrogen bond. Now once you ionize, let's say 2H nu, and what you get is you create a cationic state. In this cationic state, the charge is localized on the fragment, this one, because its ionization potential is lower. And now you have the scenario that what you started with delta minus delta plus now turns out to be delta plus delta plus. Okay, when you have delta plus delta plus, there is a Coulomb repulsion, and this Coulombal repulsion will lead to fragmentation. Okay, now one can think of a elaborate mechanism and a energy level scheme, which is shown here, but I'm not going to talk about it. Essentially, one can see when you are be able to access the this scheme essentially tells you when you can access the continuum of the B molecule when you excite the bound state of A molecule. Okay, now we are not the only ones. There are a lot of people who are working on Coulombic decay, and here is one example which was published in about 3-4 years back, in which what they did was they took high energy electrons and knocked out an electron from the water molecule, inner electron from the water molecules. Consequently, they find that a tetrahydrofuran, that is, which is bound next to the water molecules, kicks away electron, and you can detect the tetrahydrofuran cations, even though you are exciting the water molecule. And there is another in which you take a mixed alkali dimers, which is nothing but, in this case, potassium and rubidium. You excite the inner electron of the potassium, and then you kick out, and then the relaxant process leads to formation of double cation. Okay, one is potassium cation, another is a rubidium cation. When these two are formed, the KRB, which is a van der Waals molecule to begin with, now has K plus and RB plus. That leads to Coulomb explosion, and that Coulomb explosion, okay, leads to formation of both potassium atom, a potassium ion, and the rubidium ion, and then you can measure the kinetic energy of these using the velocity map imaging technique. Therefore, we decided that much before this paper came, we decided that we will also use velocity map imaging technique to measure the kinetic energy of the fragments. Okay, so what is velocity map imaging? Velocity map imaging is basically you make an ion cloud, okay, which is after breaking a bond or whatever. Usually after breaking a bond, it could, in this case, it's just a van der Waals bond. Then what you do is you let the ion cloud expand and move towards the detector and pancake on the detector, and it falls flat on the detector. And so you have a 3D ion distribution, which allows you to get a 2D distribution on the position sensitive detector. And then you can do some kind of transformation called mathematical inverse transformation to get the velocity distribution for height. And this is the equipment that we have. This is the equipment that we designed to do these experiments, and it's working now. So to begin with, we wanted to calibrate the experimental setup. So we looked at the CH3I, that is the methyl iodide photodissociation, okay, using the Q state excitation at 266 nanometer. However, when you don't have to do the entire imaging of the entire ion cloud. What you can do is a sliced imaging. Okay, sliced imaging is nothing but if you take an orange and you cut the central slice, which is the thin central slice, okay, it will tell you the shape and the distribution and the size of the orange. Okay, only one central size is enough to get the idea of the orange that you want. So this is the sliced imaging. Here I am showing you just a central slice. Okay, and that central slice tells you everything about the orange. You can guess the diameter. If it is spherical distribution, spherical orange, then you can tell you what is its diameter, what is it going to be its size, but just by looking at the slice, and what is the internal distribution. Okay, so how many parts are there? You can just count everything. So central slice is just enough to tell you the distribution. So in sliced imaging, you can actually get the sliced image of the central ion cloud, and then you can get all the information regarding the ion distribution. And this is what we have done for the CH3I dissociation, and we could calibrate our of course, we could calibrate our instrument and compare it with what is published elsewhere. Now coming to our own molecule, that is the phenylacetylene versus amines. Okay, now we wanted to measure the kinetic energy. So here what happens is you start with this van der Waals complex. You excite the difluorophenylacetylene. So this is the complex to start with in the ground state. You excite the difluorophenylacetylene to an excited state, but this excited state is above the continuum of dimethylamine, so it will charge transfer, leading to the dimethylamine cation. But once you have dimethylamine cation, it's on a surface that is repulsive, and you get the dimethylamine cation. But in this experiment, we have used tabletop lasers. There is no need for synchrotron, or there is no need for any of the high energy sources. We can use, in fact, we were using resonant two-photon ionization. So we were using only 4.4 eV photons. Okay, these are the images that we have measured, and these images corresponds to when the one case dimethylamine is bound like this. This is this image. When trimethylamine is bound like this is this image, and when trimethylamine is bound like this, which is this image. Okay, so you can see that so this image one is larger size than these two images. However, here we could not do slice imaging because the fragment was very narrow, which was nothing between the pulsed power supply that we had. We have about 75 nanosecond width power supply, and the width of the these fragments was less than 75 nanoseconds, so we could not do sliced imaging. So we could do only the normal whole ion image, whole ion cloud imaging. So since we have done whole ion cloud imaging, we have to do able transform. We did able transformation. And using able transformation, you get the kinetic energy data out. So this is the kinetic energy profiles of these three images. And you can see that you can see three curves, and out of which two curves are almost identical. Now, the first curve, the red one, is for this dimethylamine bound like this. And the green curve here is the trimethylamine bound like this. So when you take the same binding profile, but you change the cation or change the counter cation, then what you see is you get a different kinetic energy profile. Okay. By the way, this is total kinetic energy profile, which is you can get it from the center of mass transformation. And when you take the same molecule but you change the binding mode, okay, you still get the same binding profile. That is because the asymptote is same for both of them. Okay, you are exciting by the same amount of energy, and your asymptote is also the same. That's why your kinetic energy profile is similar. Okay, now you have to explain this kinetic energy profile. So we asked our collaborator, Dr. Balnarayan from ISAR Mohali, and we looked at all the potential surfaces for these molecules, both excited as well as the cationic state. So what we start is, we start from exciting. The two-photon excitation leads to this very high excited states, which are of the neutral state. Okay, and then below this, you can see the red curve. The red curve is the cationic state, which is repulsive in nature. So it is going to go down and produce the fragments. Okay, and the excitation is above that, above the cationic curve, which is repulsive. And there are a lot of curves. You can see there are a lot of excited states. So these excited state, depending on how they interact, we have not evaluated that, but depending on how they interact, they will finally land up on the cationic state, and this cationic state now rolls down and give you the fragments, and these are the fragments that we have detected. In summary, what we could see is that by adding fluorine atoms, you can switch the interaction, and you can make the hydrogen bond more prominent. And then when you ionize, you have a Coulomb repulsion, and that Coulomb repulsion comes from the ICD process, leading to non-zero kinetic energy distributions of the kinetic energy profiles. And we can capture the asymptote using the potential energy curves, and which is going to give you the kinetic energy that the ions will have. I have to thank my student Namita, who did these experiments, and the collaborators, Mr. Nitin Singh and Professor Balnarayan from ISAR Mohali, who carried out all the electronic structure calculations to get the potential reserves. While we were setting up this velocity map imaging technique in our laboratory, we had a lot of help from colleagues in other places like Dr. Vaibhav Prabhudesai from TIFR, Professor Arthur Suits from University of Missouri, Professor Andrew Irving from Bristol, and Professor Lunis Barnes from Madrid. All of these guys helped us to set up these machines while optimizing the machine. And I'll also thank the funding agencies for giving me the money to carry out these experiments. And I'll stop here and take any questions that you have.
Thank you, Professor Patwari. Very interesting talk. And now the session is open for question. Any question, please?
Hello, very nice talk, Professor Patwari. I have one question that can you please comment on similarity or dissimilarity of this intermolecular Coulombic decay process with autoionization process when the autoionization level is corresponding to doubly excited electrons?
Actually, autoionization can happen even within a molecule. Okay, Coulombic decay has to be coupled by 1 over R potential. Okay? So which means that actually it goes over 1 over R to the power of 6. But so which is actually a bound state of molecule A with it's between two molecules. So you excite a molecule 1 and then you ionize molecule 2. Okay. So that's the subtle difference. Essentially, both of them are energy transfer processes. Okay. Except that where does the energy land up?
Or the shape of the spectra that you will get, peaks that you will get, should it be different in?
It depends on what you're looking at. Are you looking at the ions or are you looking at the electrons?
Okay.
Okay, if you are looking at electrons, of course, you have these resonance states that can come in, but for ions, I don't think that is going to matter.
Sir, I have the next question. Sir, this seems to be an extremely novel or innovative process. So what kind of applications we can expect from, because we are exciting one molecule and getting the effect on the another molecule. So
okay, actually there are some, I mean, first of all, we were the first one to show that you can actually use very small energies to, because everybody in the world is using synchrotron radiation or anyone, but we were the first ones to show that, you can just do it using tabletop lasers. Okay. Now our aim that we are thinking is that when you see, for example, radiation damage or a lot of, in biology, people are just started to think in this. Okay. It's not the chromophore that is absorbing. Okay. So something absorbs and something else gets ionized. Okay. So what you see as finally the of course there are, when you do this intercoulombic decay, there are secondary electrons which can do a lot of other things. So I'm not even talking about the secondary electrons. So if you see an ion, okay, now don't be so sure that from where it has come, because it would have come from something else absorbing in the neighborhood. Okay. So I cannot, for example, if you see that DNA strand breakage has happened, so it can come from water getting absorbed, or so. Now, I mean, it's a very, very indirect consequence, and you don't even know. It's very difficult. What I'm trying to say is that unless you study all the decay path mechanisms, it's very difficult to put your finger and say, okay, I have done this and this is the result. No, the result is something which is very complex mixture of what has happened. So I will not venture a guess on what is going to happen, but what I can see is that okay, in Hindi it's like, kahin pe nigahein kahin pe nishana kind of thing. You actually ionize somewhere else and you get product somewhere else.
If there's no more question, I once again thanks Professor Patwari for very interesting talk and sparing your time and sharing your excitement with us. Thank you very much.
Okay, thank you.
So friends, now we come to the last talk of the session. That is, the talk is delivered by Dr. Anil Kumar, my younger colleague from LNPT division, and Dr. A.K. Singh joined Laser and Plasma Technology division of BARC in 2009 under a DGFS scheme, completed his MTech in Optoelectronics and Optical Communication from IIT Delhi. He obtained his PhD from Homi Bhabha National Institute, Mumbai, in the field of laser-based surface processing for field emission enhancement. Currently, he is working on development of high-power lasers, high pulse repetition, tunable laser facility for laser isotope separation. Presently, he will be talking today in his talk. He will be talking on enrichment of isotopes for laser isotope separation technique for nuclear medicine. Now it is over to Dr. Anil Kumar. You can please take the stage.
Yeah, please, Anil, you carry on.
Good morning, sir. Thanks for a nice introduction. I'm going to share my PPT now.
Anil, you can
Just a
start
minute,
now.
sir. I'm trying to share my PPT. Yeah. So is it visible to all of you? Hello.
Continue. You can please
Okay,
continue.
okay. Thank you so much, ma'am. A very good morning to all. Today I'm going to speak on a very interesting topic, that is enrichment of isotopes by laser isotope separation technique for nuclear medicine. This topic is very important for Indian perspective. But before starting my presentation, I would like to thank to the symposium organizing committee for giving me opportunity to present our work here. So outline of my presentation is like this. First, I will cover a brief introduction, then basics of the laser isotope separation process. After that, development of lasers will be presented and its qualification will be done. And then development of atomic vapor source will be presented. After that, some of the results from our enrichment experiment will be presented. And at the end of the presentation, I will present conclusion and the future perspective. So let's begin with the presentation. As we know that many elements have more than one isotope, and these isotopes are identical in their chemical properties, but they differ in their nuclear properties. Because of this difference in the nuclear properties, different isotopes are used for different applications. And to get optimum performance of these isotopes in a particular application, we need to enrich them beyond certain level. So now question comes, what is isotope enrichment? Isotope enrichment means basically increasing concentration of one of the isotope in a multi-isotopic element beyond its natural abundance. And these enriched isotopes are used for a variety of applications. Some of them are listed here, like energy sector, then it is used also in the industry, then agricultural sector, basic nuclear physics research, nuclear medicine and biology, etc. But we are interested only in the nuclear medicine. Nuclear medicine is the branch of medicine in which radioisotopes are used for treatment and diagnosis of the diseases. And we know that this field has emerged very elegantly over past few decades, and scientific community has developed a large number of radioisotopes for this purpose, and one of them is lutetium-177. This isotope has emerged as one of the most promising radioisotope for cancer treatment, and it is produced by mainly two different routes. Number one is direct route, and number two is indirect route. In the direct route, target enriched with lutetium-176 is irradiated in the nuclear reactor to produce lutetium-177, while in the indirect route, target enriched with ytterbium-176 is irradiated, which produces ytterbium-177, and this very quickly converts into the lutetium-177. And both these routes have their own merits and demerits. For example, direct route has the advantage of high production yield, but co-production of lutetium-177M, which is an isomer of lutetium-177, is the biggest drawback because it is a gamma emitter with half-life of 160 days. This half-life of 160 days is much higher than the half-life of the lutetium-177 itself, which is only 6.7 days. Also, the lutetium-177 produced by this route has low specific activity. On the other hand, the indirect route produces no carrier lutetium-177 with very high specific activity, which is close to the theoretical value. But the problem with this route is that it has very low production yield. So for producing lutetium-177 with high specific activity, we need highly enriched targets. For example, lutetium-176 needs to be enriched beyond 65%, and ytterbium-176 needs to be enriched beyond 95%. But the problem with us is that India does not have any enrichment facility for these two isotopes, and therefore, for producing lutetium-177, we import these enriched isotopes. Therefore, considering the current applications of the lutetium-177 in our country and its growing importance, we have set a goal to make India self-reliant in the production of lutetium-177 by both the routes. And for this purpose, we have set a target to enrich both the isotopes, ytterbium-176 and lutetium-176, beyond 95% and 70% respectively. And the advantage of setting this enrichment facility for these two isotopes is that we will get two additional isotopes of medical use. They are ytterbium-168 and ytterbium-174. They are used for producing ytterbium-169 and ytterbium-175. Ytterbium-169 is used in the brachytherapy. So now let's look on the isotope enrichment techniques. There are several enrichment techniques available, but the selection of a particular technique depends upon the type of isotope which we are targeting and the level of enrichment required. But for our purpose, means the two isotopes we have targeted, we are having only two options. One is electromagnetic isotope separation and other is laser isotope separation. But we have selected laser isotope separation because it gives numerous advantages. For example, it provides high selectivity, high energy efficiency, high throughput, and low capital cost in comparison to the electromagnetic isotope separation technique. Therefore, we have pursued this scheme. Now let's have a look on the basics of the ELIAS process. And the ELIAS process can be understood with the help of these two schematic diagrams, in which there is a atomic vapor source which generates atomic vapor of the target isotope element, and this atomic vapor beam is transversely illuminated with a laser beam of consisting of specific wavelengths and line width, which selectively ionizes one of the targeted isotope. And the ions are collected on the collector plate by using applying high electric field, and the remaining atoms are collected on the tail collector. So isotope selective process now can be described using this energy level diagram. As we know that for all the different isotopes, there is slight difference in their energy levels, and therefore by precisely tuning the wavelength and keeping the line narrow enough, we can selectively excite one of the isotope which we want and finally ionize it. So for developing an ELIAS facility, we need to have three basic requirements. That is, number one, there should be an efficient photoionization scheme, and number two, there should be suitable lasers so that we can selectively ionize them. And number three is there should be a process chamber in which laser atom interaction and ion collection can be done. So now let's have a look on the available isotope selective photoionization schemes for the lutetium-176. There are several two-step and three-step photoionization schemes available for the lutetium-176, but we are currently interested only in the three-step photoionization schemes because the generation of laser corresponding to three-step process is relatively simple, relatively easy, because the corresponding wavelengths fall in the visible range. And for this, there are two such schemes available in the literature. One is reported by the Russian group, and other scheme B is identified by our group. Both these schemes have their own merits and demerits. For example, scheme A has advantage of high energy efficiency, but it has low selectivity. On the other hand, scheme B offers high selectivity and more atomic accessibility in comparison to the scheme A, and the lasers corresponding to this scheme are suitable for generating using the diode pumps dye laser system. So let's have a look on the detail about the scheme B. So in this scheme B, all the spectroscopic data corresponding to first stage of excitation is already reported in the literature. From there, we have simulated hyperfine spectra for the two isotopes, and we found that this particular hyperfine component is suitable for our purpose because it gives maximum energy separation with respect to the nearest hyperfine component of the lutetium-175, which is 2.8 gigahertz. Now, a wavelength corresponding to second step of excitation has been identified by our group, and for this purpose, we have used two color rims investigation, and this is showing the hyperfine spectra corresponding to lutetium-175 and 176 for second transition. And here we selected this particular hyperfine component of lutetium 176, which gives energy separation of 5.7 gigahertz, which is very high for attaining the high selectivity. In addition to that, we have also identified different auto-ionizing levels connecting from the second step excitation to the auto-ionizing level. And we have identified several such auto-ionizing levels. And for our purpose, we have selected this, which corresponds to a wavelength of 577 nanometer, because corresponding to this high auto-ionizing level, this absorption cross section was maximum. So with this work has been published recently by our group in this particular journal. Now available photoionization scheme for ytterbium 176. This is the scheme shown in this figure, is the most widely used three-step photoionization scheme for ytterbium 176, which has been used by several countries to increase ytterbium 176. Therefore, we have also pursued this scheme, and in this scheme, minimum isotope shift is for 176 is around 300 megahertz in the second step of excitation. But we are also targeting isotope 168 of ytterbium. For this, minimum isotope shift is around 150 megahertz only in the first step of excitation. Therefore, we need to develop a laser with line with less than 150 megahertz to get high selectivity, and this kind of lasers require single longitudinal lasers. So, considering the available photoionization schemes for lutetium 176 and ytterbium 176, we have developed a high average power dye laser facility. This is slide is showing an overview of our laser facility. Here, this is our dye laser lab, which is consisting of 3 different wavelengths. Here, lambda 1 and lambda 2 are single longitudinal mode dye lasers, and lambda 3 is multi-mode dye laser. These dyes are pumped by copper vapor laser output beams, as well as using the diode pump solid state lasers. CBS and DPSS have been supplied from the RRCAD, and we have developed the dye laser facility here. So this image in the left-hand side is showing a typical image of the copper vapor laser MOPA chain, and the right-hand side is image of the dye laser lab under the operation. So now let's have a look about the developed SLM laser. SLM and oscillator is schematically shown here in this picture. Number 1 is output coupler, and number 2 is dye cell through which dye is flowing, and number 3 is a prism beam expander. Number 4 is intracavity etalon. Number 5 is grating, and this oscillator is pumped by a optical fiber delivered CBL beam, which is focused in the dye cell. This figure in the right hand side is showing actual image of the developed oscillator. In this, all the components have been mounted on a SS base plate, which is temperature stabilized using this DC heater, and this complete setup is kept on mounted on a vibration free table. So specifications of the developed SLM laser is like this. It gives a laser line width of 60 megahertz, and wavelength stability is around 45 megahertz. Pulse duration is around 65 nanosecond, and it works at the pulse repetition rate of 12.5 kilohertz. Efficiency of this oscillator is around 5%. So after that, we have investigated the performance of the dye laser system, which is reported here. First, we have confirmed the SLM operation by sending the dye laser output beam through a etalon of 4.5 gigahertz FSR and finish of 25. And we can see that clearly sharp peaked fringes, which is indicating that operation is SLM operation. Figure in the right hand side is showing temporal profiles corresponding to pump and dye laser pulses. Here, typical pulse duration at the 10% level is around 100 nanosecond for the pump pulse, and it is around 65 nanosecond for the dye laser pulse. And this curve is showing efficiency versus pump power for the developed oscillator. And as we can see from this, as the pump power increases, efficiency also increases. But we have restricted our pump power to around 6 watt to get stable operation of the SLM laser. And this curve is showing a typical curve of the tuning curve in the broadband operation mode. So most challenging part in the development of single longitudinal mode dye laser is stabilization of the wavelength and the line width. And this has also crucial impact on the LIS process. Therefore, we have stabilized it, and we can see from these two images, upper part is showing wavelength and line width stability under free running condition, and this is the stability under the active control. And we can see from this image that we have achieved excellent stability for the line width and the wavelength for this test period of around 4 hours. So with this, now we are using this control and monitoring system for the laser wavelengths during the operation. We continuously monitor the wavelength as well as the line width. So next step after the development of lasers is to qualify these lasers and the photoionization scheme for the LIS process. And for that, we have used our time of flight mass spectrometer. We have combined all the three wavelengths and sent them to optical fiber. And we have precisely tuned the wavelength and determined the wavelengths for all the three levels with the accuracy of plus minus 30 megahertz. So by optimizing the wavelength and the laser power, we could achieve selectivity of more than 99% for all the targeted isotopes. And typical mass spectra is shown here. This spectra is corresponding to the natural uranium under non-selective excitation condition, and this is corresponding to the ytterbium-176 when all the laser parameters are tuned for ytterbium-176. This corresponds to optimized condition for 174, and this is for 168 ytterbium under the optimized condition. Now the time of flight mass spectra for lutetium-176 is shown here. We have deliberately first kept our wavelengths in between the lutetium-175 and 176, and to identify the two peaks, two isotopes. After that, we have precisely tuned the wavelength corresponding to lutetium-177 and 176, and we could achieve selective isotopic abundance of more than 99% for this case also. So with this qualification of the wavelength as well as the lasers, we now will talk about the development of the atomic vapor source. Since the melting point of ytterbium is not very high, and we can get required number density in the interaction zone by getting the temperature in the range of 550 to 600 degrees Celsius. Therefore, we have designed a resistively heated furnace, which is shown here. This figure is showing actual resistively heated furnace here. In this, this type of crucible has been kept. On top of the crucible, we have kept a collimating slit, which collimates the beam for reducing the Doppler broadening of the atomic beam. Apart from this, we have also used the Doppler width reducer, which further reduces the Doppler width of the atomic beam. So this source has been characterized in terms of the atomic flux through the interaction zone. Then we have characterized it for this distribution, vapor distribution along the longitudinal and transverse direction. Doppler width has been characterized, and scattering because it is the most important parameter which also governs the quality of your product. So we have characterized measured scattering on the collector plate, and we could achieve atom number density of the order of 10 to the power 12 with the Doppler width of the 230 megahertz in the interaction zone. But we have, for our practical purposes, we have restricted our atomic number density in the interaction zone in the range of 2 to 5 into 10 to the power 11. And atomic vapor length is around 160 mm, width is around 15 mm, and neutral atom scattering on the collector plate is around less than 0.1%. So with this, let's see our experiment. actual experiment for enrichment was done in the high vacuum of 10 to the minus 6 millibar with the number density of 2 in the range of 2 to 5 into 10 to 11 atoms per cc. And these are the laser intensities which has been used for enrichment of terbium isotopes. And this figure is showing entry and exit of the combined dye laser beam inside the separator chamber. This is how laser beam propagates inside the chamber. It does multiple passes in the interaction zone to efficiently ionize the atoms. And this figure is showing the actual interaction zone when we are doing multi-pass alignment. So for extracting the generated ions, we have used a double grid plate based system in which grid is keep close to the photo generated plasma, and it is kept at high negative potential to extract the ions from here. And in between the grid and the this collector plate, this is further deaccelerated so that it landed softly on this plate to avoid the sputtering of the deposited product. And using this, this is our actual system, photograph of the actual system. Here is the grid, here is your interaction zone, and here is our collector plate. This side is repeller plates, which is kept at positive potential to repel the ions so that they cannot reach on this plate. And now the results and discussion. We have achieved this is showing a typical photoionization signal in the oscilloscope when we do experiment. These pulses are coming at 80 microseconds apart, and this is how our collector plate looks like. In the collector plate, this is the area showing where product has been deposited. And after analysis, leaching and analysis of this product, we have achieved this kind of enrichment. For example, ytterbium-176 isotope has been enriched up to 97.8%, and ytterbium-174 has been enriched up to 98.5% from its natural abundance of 31.4%, and ytterbium-168 has been enriched up to 15% with the throughput of like this. So we have generated different enriched isotopes, and we have given these products to our collaborators for irradiating the nuclear reactor and carrying out the clinical trials. So with this, I will like to conclude like this. We have developed high average power narrow band dye laser facility for LIS of the ytterbium isotopes and the lutetium isotopes, and we have demonstrated enrichment of ytterbium-176, ytterbium-174, and ytterbium-168 up to 97.8%, 98.5%, and 50% respectively. And we have tested reproducibility corresponding to enrichment of ytterbium-176. And out of 12 experiments, we have achieved more than 97% in the 10 number of experiments, except for in the first 2 experiments, we could get only in the range of 95%. So we have also devised a photoionization scheme for lutetium-176, which is highly selective, and atomic accessibility is high in comparison to the reported value. And we have developed lasers, and the photoionization scheme has been tested and developed for the lutetium-176. Characterization of the atomic vapor source is in progress, and we are hopeful that we will demonstrate enrichment of lutetium-176 within a month or so. So with this, now the future perspective for the 2 isotopes. In future, we will first optimize our parameters in the existing system. They will try to scale up the throughput for the isotopes, and our target is to deliver
Anil, time
176 with quality more than 97% and throughput of more than 50 milligram per hour, with the cost comparable to or less than the imported targets. And for lutetium-176, we have to demonstrate enrichment more than 70%. Then again, we have to do upscaling and deliver the product for quality 70% throughput more than 1 milligram per hour. With this, I would like to acknowledge the contributions from our team, This is our LIS team. I would like to thank all the members of the team, and special thanks to the Dr. Rachna Sharma for so thanks to all for your kind attention. This is the PSSS supplied from our guide.
Thank you, Dr. Anil. Very informative talk. And I also want to, because know a little bit about your program, to congratulate your group to doing such a important work and doing it. No, I wanted to ask some simple question. And the thing is
Yes,
that
sir.
you know that finally you will need some quantities which will be more than what you have already demonstrated. No,
Yes, sir.
what are the limitations that if you have to go for the higher quantities, what are the things using? First, you can tell in the case of ytterbium, and
Yeah.
then I understand that finally you have to go for lutetium.
Yeah. No, sir. Actually, yeah. In the long term, we should go for the ytterbium only because it provides no carrier aided lutetium 177. But the problem is we have to demonstrate that we can produce the ytterbium 176 with the required quantity. If we can give them, then it will be the best option.
Another thing about your stability of the laser, because you have a very narrow isotope shift and narrow laser line width.
Yes, sir.
How you make sure that your laser is stable there? And you said that the 4 hours. What will happen if it is more than 4 hours longer? Will it
Sir,
go
till
away
now
or
we have tested only for the 4 hours, and we are hopeful by watching the pattern of this whole stability curve and actual what is going on in the ecosystem. We are hopeful that we can go beyond 10 hours also, but we have to prove it. Actually, we have to carry out the more experiments and prove it.
Thank you. Any question from the audience? Anil, there is a question in the chat box from Mr.
Yes, sir.
Srikanth. What is the dye laser base plate temperature and its temperature stability to achieve observed wavelength stability? Did you get me?
Yeah, actually, normally people use INVAR for the base plate, because, but we have this is the novelty of our system that we have achieved a stability only at the use of SS plate. And just by stabilizing the temperature of the this SS plate, which is plus minus 0.2 degrees Celsius. This is most critical part to achieve. Once you achieve this stability and apply active control, you can get the stability. Unless you will achieve this kind of stability, even with the help of this active control, by controlling the cavity length, we are not able to get the stable operation.
Another question is there from Praveen Kumar Agarwal. That good work by the team. What prompted you to go for different wavelength instead of reported one?
Yeah, because for the reported one, it was known that the isotope shift in the second stage is only 900 megahertz. So if you will try to ionize, increase degree of ionization for achieving more product as well as to increase the more up to the higher level, because by that scheme, people have demonstrated up to 65% only. Russians have demonstrated up to 65%. But to increase beyond that, we need to increase degree of ionization of the vapor also. And for that, we have to increase the power level. So unless we have a sufficient selectivity, we will not get that kind of enrichment.
Dr. Alok Kumar.
Hello, Anil. Yeah, thank you for the good work for your whole team. Of course, you have shown that many subsystems also need to develop, not only the laser spectroscopy, but many subsystems. I just have the lutetium production through the 176 ytterbium route. Only problem is nuclear cross-section is low in the reactor.
Yes, sir. Yes, sir.
But you can get a high specific activity, as you mentioned, which is required for the patient. But you can reuse it also, no, because the cross-section is less. So after irradiation, the remaining enriched 176 ytterbium, which is not converted to lutetium, that can be reused again.
Yes, sir. Yes, sir. Actually, Russians are using that one. They reuse the, actually, when you irradiate in the nuclear reactor, less than 0.5% is converted into the lutetium. Remaining is there. So by chemical separation, people separate remaining ytterbium 17, whatever is left, 176, and they again re-irradiate in the nuclear reactor by producing that. So
Yeah,
by this way, they can reduce the cost.
yeah, exactly. And of
Yeah.
course, you can produce more quantity. That also you can do it. And but you have
Yes, sir. For increasing throughput in the case of ytterbium is easy in comparison to that of the lutetium, because for this required temperature is low. So we can make a bigger atomic vapor source while keeping the temperature of the surrounding, where we are keeping the multipurpose mirrors at the room temperature, close to the room temperature.
yeah, but main advantage is that you are getting a high specific activity and no carrier also. Because for the
Yeah.
lutetium direct route, you have a metastable state of lutetium which is radioactive.
Yes, most of the countries in Europe and USA are using now. They are shifting toward the NCA route, means indirect route.
That is the you have to pursue with the radiopharmaceutical division department. But one more
Yeah,
thing
but
I can see your result when you are doing 176 ytterbium, your production is around 5 milligram per hour presently. But for 174 ytterbium, which is starting at 31.4%,
yes,
your
sir.
production rate is lower, 3.5 milligram per hour. So that is may not
Yes.
be intentional.
No, sir. Actually, it is for ytterbium 174. We have carried out only one experiment at low number
It's
density.
like that because your
Yeah.
initial
So
abundance is much
yeah.
higher, so it should be more.
But yeah, for ytterbium 174 and 168, we have carried only one experiment. And for ytterbium 168, we have carried 12 experiments. So out of 12 experiments, we have always get more than 97%. The remaining, except only for the first two experiments.
But those other isotopes, are you giving to some other people for use it? 174 ytterbium and 168. Other
Pure 174 ytterbium also used for the atomic clocks.
Alok.
Okay, thank you.
Okay.
Time is not there.
Okay, Anil, thank you very much for a very good, interesting talk and the work you have done. And with this, we come to end this session. And
Thank you so much, sir. Thank you so much.
Thank you very much, Dr. Vasdev, for chairing this very interesting session. So with this, this session ends, and we will take just a short break for 5 minutes, and we will assemble here again at 11:15. So all the participants who have joined online, I request all of you to please come back at 11:15. Thank you. I also request all the people, all the participants, all the dignitaries to please visit the exhibition gallery as well, because this is the place where you will find many equipments, a review of many good quality tools which will strengthen your research.
Hello.
Can you hear me?
Professor Banerjee, we can hear
Hello.
you. Professor
Okay,
Banerjee, we can hear you.
okay, sounds good.
Hello. Am I audible?
Yeah, yeah. Rawat sir, we can hear you. We'll start this session at 11:15.
Hello, welcome back everybody. So now we start the session 10, which is another aspect of lasers in application area. This is laser-based instrumentations. And this session will be chaired by Shri A.S. Rawat from BARC. Shri Asim Singh Rawat is working at Scientific Officer Edge, and he is presently head laser application section at Laser and Plasma Technology Division, BARC. He did his bachelor's degree in electronics from SGS Institute of Technology and Science, Indore, and MTech in electronic systems from IIT Bombay. He joined BARC through BARC Training School and has been working in the field of laser-based instrumentation for more than 25 years. His major contributions are development of laser-based diameter measuring instrument, surface roughness measuring instrument, projectile velocity measurement, optical triangulation-based and interferometer-based vibration instrument, and flow visualization. He has transferred technology of 3 of his instruments to private industry. He is recipient of DAE Scientific and Technical Excellence Award 2012 for his contribution in the field of laser-based instrumentation. His present field of work is on interferometer-based intrusion detection and fluorescence-based sensitive detection systems. So I request Shri A.S. Rawat to please take this session forward. Over to you.
Yeah. Good morning, everyone. Now, let us start the session on laser-based instrumentation. There are 3 talks in this session. The first talk is by Professor Ashis Banerjee. Professor Ashis Banerjee is an associate professor of industrial and systems engineering and mechanical engineering at the University of Washington, Seattle. He did his PhD and MS in mechanical engineering from the University of Maryland, College Park, and BTech in manufacturing science and engineering from the IIT Kharagpur. He worked as a research scientist and postdoctoral associate at Massachusetts Institute of Technology, and also worked as a research scientist in the Complex System Engineering Laboratory at General Electric Global Research. Dr. Banerjee has published more than 50 articles in peer-reviewed journals and conference proceedings. He has received several honors, including 2021 IAOTP Top Engineer of the Decade Award, 2019 Amazon Research Award, 2012 Most Cited Paper Award from the Computer Aided Design Journal, 2009 Best Dissertation Award from the Department of Engineering, 2009 George Outstanding Systems Engineering Graduate Student Award from the Institute for System Research at the University of Maryland. The title of his talk today is Towards Precise.
Hello, Mr. Banerjee, now you can start.
Okay, thank you. Hello, thank you everyone for inviting me to this symposium. It's a matter of great honor for me to be able to give an invited talk here. So today I'm going to talk about how we can use optical tweezers to do something useful and interesting in terms of patterning objects at the micro scale in a very precisely controlled manner. So I think Dr. Shri Rawat has already given a very long, kind introduction of myself, so I won't get into that again. So let me begin quickly by discussing briefly what optical trapping or tweezing is all about. So some of you may already be familiar with it, but in case you're not, what essentially is happening is that we have a laser beam, and you can think of a single beam, or you can have multiple beams, as I will soon discuss. But essentially you have a laser beam which is focused extremely tightly by this objective lens, which has a very high numerical aperture. And if you are able to achieve this kind of extremely tight focusing of a laser beam, then people have observed experimentally that near this focal region, if you have small scale objects, by that I mean objects whose characteristic dimensions would vary from few nanometers all the way up to like 20 microns or so. So if you have all such objects in this focal region of this tightly focused laser beam, then the beam exerts enough of trapping forces to those objects so that they are kind of pulled towards this focal point, and then they kind of remains in that stable trapped manner. So if we now move this laser beam around, so if you steer the laser beam around, and you can do that in 3 dimensions, then what happens is whichever object has been trapped, or if you have multiple aggregated objects that have been trapped in this focal region, they kind of move along in perfect synchronization with your laser beam. So this means we now have kind of a tool at these small scales using which we can sort of pick and place objects. You can like pick an object from here and you can transport it somewhere else, and that way you can start creating some patterns or arrangements. Now, if we do that one by one, then that, even though it's still useful, it's not very efficient. So it's not really going to lead you to any practically useful structure formation in any reasonable period of time. So that's why, like, for a long time, people were like trying to come up with some instrumentation or design of how this can be parallelized effectively. Now, before I get into that, just for if you are wondering, like from the core physics point of view of how optical trapping works, this is a famous illustration from a pioneering paper that was published by Arthur Ashkin, who in fact won the Nobel Prize for his of optical tweezing just a few years back, and he in fact recently just passed away. So he won the prize, Nobel Prize, a couple of years before he passed away. So this is a very simple ray optics based model which turned out to be surprisingly effective in modeling how and why optical trapping actually works, especially at the micro scale. Now, if you go down in the size scale and if we talk about trapping objects in the nanometer dimensions, then this model doesn't quite work. So we have to look at from an electromagnetic wave standpoint. But for the objects that I will be talking about today, this is a perfectly valid model which gives us good estimate of like what the trapping forces are expected to be depending on where the object is initially positioned relative to the beam focal point. So the basic idea is very simple. You have a Gaussian intensity profile of your beam. You can have other profiles, but this is the most commonly used intensity profile. And then you can imagine like you have an infinite collection of rays that are coming from this laser beam, and depending on this Gaussian profile, you would have varying ray intensities. So now you have the objective lens, and they all like are focusing, it's focusing all these rays onto this object that you are trying to trap. Now, the key requirement is that this all needs to happen in a fluid medium, and the optical refractive index of this dielectric object that you are trying to trap needs to be greater than that of the surrounding medium. So if these criteria are satisfied, then we can do some simple ray optics and model like how the rays would be reflected or transmitted, and maybe internally reflected or refracted back into the media. So all these possibilities we can account for each ray individually, and then if we then sort of integrate over all such rays that are going to be incident on the surface of the object, then we see that the net outcome or result of all of it is a force that's always going to be directed from towards the beam focal point. So that means no matter how like you have originally no matter how the object is displaced, you will always have a net sort of pulling force that's directed towards the focal point. Now, of course, the magnitude is greatly impacted by this relative displacement of the object center and the focal point. So if you are too far away from the focal point, obviously the force becomes vanishingly small, and then this mechanism doesn't work anymore. So now coming back to the instrumentation question of all of this is great. So we can model the forces, we can do the stable trapping, but if we just do it one object at a time, it's not very practically useful to make any kind of assemble structure, let's say. So in that regard, a big breakthrough was made when this holographic optical tweezers were devised primarily at David Greer's group at New York University. Probably was at University of Chicago at that point. So what they did, so reasonably straightforward idea, but it worked very well. So they basically added a SLM or spatial light modulator to the system. And then what happens is that even though you have now a single incident laser beam, because of the phase modulation that is being imparted by this SLM, that single incident beam now gets split into an arbitrarily large number of beams, each of whose phase you can regulate quite precisely. And then if you focus all those split beams by that same kind of objective lens arrangement with high numerical aperture, and then shine those split beams onto your workpiece, then suddenly from just being able to stably trap one object at one near the trap focal region, now you're able to trap as many objects as the number of beams that you have split. So this kind of multiplexing capability was really made a big difference in like the practical use and opportunities provided by the optical tweezers. So in our lab, we have one such more modern version of an holographic optical tweezers, which uses a similar spatial light modulator, which is entirely computer programmable. So we can write some software code and basically figure out, and then there is a translation code which figures out what kind of phase modulation needs to be imparted, so that we can just say, and here is an cool example, that you can have a touchpad and you can basically with your fingers point that I want to set a trap here, I want to set another trap here, here, and that's exactly how the beams would be split, and we can see that precisely those traps are being set exactly at the locations that you specify. So the big advantage is that you can do independent control in 3 dimensions for each individual beam that you are basically getting as an output of your SLM. So then coming to the natural advantages provided by this system, it's of course the main capabilities, this multiplexing. Then we can do like completely independent manipulation in 3D. So it's not like you are restricted to moving objects along certain planes. You can move them arbitrarily in 3 dimensions. Also, you can create some interesting light patterns by, again, adjusting what kind of phase modulation you do. So you can actually create some annular rings or like pattern of rings. And that way, let's say you have like a bunch of objects which are kind of arranged in this concentric manner. So you can trap essentially all those objects together and just transport them concurrently at one go. So all these nice features are provided by this system. And then one other big advantage, which is true for any optical tweezer system, is that there is a lot of versatility in terms of the material that you can move, or the type of material your object needs to be made of. So unlike in case of some other competing techniques, like if you can use electrical fields, pure electrical fields, or you can use pure magnetic fields to also do such transport of particles in a stable manner at these scales. But here, like we are not limited to the types of restrictions that may otherwise be imposed if you are using pure electrical or pure magnetic fields. The only key thing to note is that it has to have a decently high refractive index, which needs to be greater than that of the surrounding medium. But that's mostly true for most like colloidal particles and biological objects like cells and so on that we normally study using tweezers. Okay, so that's the kind of instrumentation we are using. Now, what we specifically have done using this system in our lab is to look at automating what we can do once these beams or split beams have been created. So things that can be done potentially or have been done by others in the literature is they have used this as a probe to study all kinds of interesting behaviors or interactions among objects at these small scales. So for instance, human cells would be a great example of that. Most of our cells have dimensions, characteristic dimensions of the order of few microns. So you can like bring together this collection of cells and then like turn off your laser, and then you can kind of study how like this arrangement, the geometry of the arrangement impacts like their interactions of their signaling and so on. You can also do lots of things with non-biological objects, like start creating these directed microstructure assemblies. And if you are able to automate the process of controlling those split beams, then you can do this in a very repeatable and scalable manner. So that's what we wanted to explore, that whether we can use AI, artificial intelligence, to be able to automatically control all those split beams and do this kind of manipulation of objects in parallel without like requiring any human intervention. Otherwise, someone has to like constantly operate and decide where to position the beams, how to move them at what speed and following what trajectory and so on. But we can replace all of that using an automated module, and then you just say, okay, these are the initial objects you want to trap, and then this is the final arrangement you want to make, and I'll show you some videos, and then the rest will be done by the system itself. So in order to build such a system, we had to focus on two key modules. One is like being able to process the objects that are present in the workspace. So that requires some image processing algorithms. And then the other thing was once we know what the shapes and sizes of the objects are, we feed that information to a dynamics model, which can then be used within some kind of an optimal controller to compute the optimal paths or trajectories for moving these objects around. So that's kind of the scope of the work within the automation. So there are some details now about like what kind of image processing algorithms we use. So I won't spend too much time on this, but we'll probably look at some results here. So the things you can see here is that we are talking about kind of these heterogeneous environments where we have a mixture of biological objects like cells and you have some colloidal particles. And the reason we have this mixture is sometimes it's not a great idea to share the laser beam, even though we are talking about very low intensities, but still we don't want to shine the laser beam directly onto the cells because that might affect their normal physiological properties or viabilities. So instead, you can think of like having these sort of fingers to grasp the cells and move them around. And those fingers are the ones that are actually trapped by the laser beams. And those fingers might be these colloidal particles or micro objects. So we need to be able to recognize where those objects are and where the cells are, and then only we can have an automated system to move them around. So if we use the classical image processing algorithms, there we did run into some challenges for very densely crowded workspaces where you have a proliferation of cells and beads, and it just doesn't work that well. So for that, to avoid or alleviate this issue, we then switched over to a more state-of-the-art deep learning model on which we trained on like a few images, not a whole lot. We found a good model that could be trained using limited number of images. And based on that trained model, we could then run it without any further human intervention for test workspaces where like it has to figure out where the different objects are. And these are the kinds of really crowded workspaces where our image processing method works well. So you can literally see there are dozens and dozens of these colloidal particles, quite a few cells of varying shapes because these cells are wiggly. So it's not like they have these very rigid, well-defined structures. So they also morph their shapes quite a bit. And we are able to like dynamically track all these objects, and as they are also exhibiting Brownian motion or changing their forms with changes in fluid composition and so on. So this image processing, the current version works very well actually. So based on that, then we can go to feeding that information into a state space model, which requires modeling of these trapping forces based on this ray optics schematic that I showed earlier. So we can do some kind of approximation on the core ray optics model calculation that was presented by Ashkin, and we can actually sort of write the trapping forces as a composition of a linear restoring force and then a nonlinear force that gradually that exponentially decays based on the relative distance of your object from the trap center. So we model the trapping forces in this way that helps speed up computation instead of using the full-blown ray optics model. And then we add in the other expected forces you might be might be expecting in such fluid environments. So we have to deal with the viscous drag, the buoyancy, and then the Longevin forces arising due to the Brownian motion. So we model all of that. This is very standard modeling. And then we use it in a tensor form so that we can model the interactions of multiple beams and multiple potential objects that can be trapped by those beams. So we built this kind of dynamics model and then fed those states or estimated states of the objects into pretty well-established control architecture called the model predictive controller, which predicts like what the future stable trajectories of your objects should be, and then executes those based on the predicted trajectories one step or control step at a time. And then if you see any deviation in your actual behavior and the predicted behavior, you can do error tracking and that way get more robust object motion. So we did that along with some additional AI-based methods to avoid collisions among the objects. So we don't want like one beam trap which has an object trap to collide with another beam with another object trap, because due to the collisions we may have a loss in trapping. So we have some additional collision avoidance and then put that all together to the form of an overall control architecture. So
Dr.
once
Banerjee,
we
you
do
have
all
5
of that,
minutes.
yep. So now I'll show you some videos of how this works in a fully automated manner without any kind of manual intervention. So it decides like how many beams need to be created and what objects should be trapped is the only input that it gets, and then it traps those and moves them around. So this is the first video that you are seeing is a very simple one where we only have a few colloidal particles and it's not that crowded of a scene. But now when we go to more challenging environments which have a lot more particles, you can and we vary also the medium itself. It need not be always water. It can be done in all kinds of different viscous media which are more representative of the media that you would expect in a physiological setting. So so we can basically demonstrate like automated formation of different kinds of patterns given just the input of what pattern we want to create. So it's able to basically move the objects while avoiding the hitting any other object along the way. So whichever object is trapped, you see like visually its dimension looks smaller, and whichever are untrapped, like they are kind of exhibiting their free diffusion or the Brownian motion. And then we moved on to doing some experiments with human endothelial cells and created some basic patterns with them as well. So I have more videos, but in the interest of time, I'll move on and try to conclude my talk. So one cool thing that we started studying as a result or as an outcome of being able to create these patterns in a controlled manner is to understand like the interactions among live heterogeneous cells. And this is very important if we have to like create engineered or artificial tissues in a controlled manner, which can then later be implanted in on an actual human body. So these interactions of among heterogeneous cells is still not a very well understood phenomena. And one of the hypothesis is that like the spatial arrangement of those cells and their intercellular separation matters quite a bit along with the medium and the stimuli that the cells are experiencing. So these tweezers, these multiplexed tweezers provides a good tool for us to be able to create these controlled formations of cells that whose behaviors then we can study for hours. So to conclude, we took this well-established holographic optical tweezer system and developed our own automation pipeline in order to move around several objects in parallel, and we demonstrated that we can do it experimentally reasonably well, at least for tens of objects. But there are plenty of opportunities to expand and extend on this work. So theoretically, we can get stable control of up to 100 different objects. However, there is a challenge with the field of the workspace, the volume of the workspace that this thing operates in. So if we have to move 100 objects in a relatively small area, it becomes quite a challenge. So this is something that we want to explore how to deal with, and potential is to combine this form of manipulation technique with alternate things like microfluidics or electrical or magnetic, which can then provide us with a larger work volume to work with. So with that, I'd like to conclude, and once again, I'd like to thank the organizers for inviting me, and I'm happy to take any questions that you may have. And of course, none of this would have been possible without the contributions of my students, and for the many of the biological experiments, collaborators played an invaluable role as well. Thank you.
Thank you, Dr. Banerjee, for a very lucid and informative talk on optical tweezer. I just one question is that what is the power requirement, laser power requirement for carrying out this optical tweezer? Is there a minimum power required at the focus spot for carrying out this tweezing action?
Yeah, the power is quite low. So to trap one object, it's like about 100 milliwatt is more than sufficient. It depends a little bit on the geometry of the object, but typically 100 milliwatt is sufficient. So for many of the experiments where at the same time, concurrently, we moved around, say, 10 objects. So then we went up to 2 watts of power. It's not exact, but approximately like it scales in a linear manner based on the number of objects that you want to trap simultaneously. So most systems come with an like upper limit of about 3 watts. So that's another practical restriction on how many objects you can trap at the same time. But yeah, so we are talking in that power range.
Okay, doctor. And then there is any limitation on size of the object, higher limitation on the size of the object?
Yes, so the upper limit is 20 microns and the lower limit, I mean, experimentally, people have gone down all the way up to 10 nanometers, but most commonly you would see like it being done for in the range between 100 nanometers to 10 microns.
Whether the length has some.
Hello, Dr. Banerjee, there is a question for you from Dr. Pratima saying, can we trap
Yes,
the
please.
quantum dot?
Yes, the short answer is yes. So some people have indeed shown that it's far more challenging than trapping the objects at the micro scale that I talked about, and you'd need to like use a specific form of laser. So the wavelength, the laser wavelength matters quite a bit. So for our experiments, we were using the near infrared regime, but that is not the case if you have to go down to that level of the quantum dots. So yes, it is possible, but not yet available in a very widespread manner, and definitely you won't see any commercial system which claims to do that in any repeatable manner.
Okay.
Hello,
Thank
there is one
Banerjee.
question from the audience here. Dr. Padmanilia wants to ask question.
Yeah, can I ask?
Hello.
Hello.
Yeah.
Hello.
Yeah, one question from the audience.
Yeah, I am from Tata here. Yeah. Am I audible?
Yes,
Yes.
Am I audible?
go ahead.
Yeah. Dr. Banerjee, I have just one clarification and two small questions. One is when you have inhomogeneous particles like biological cells, how do you model it? Because it is a inhomogeneous refractive index. And even in my scattering, you take into account the inhomogeneousness plus the absorption. This is my first question. Second question is, when you are saying 5 micron silicon particles, usually they will be very heavy. So gravitational force sedimentation, or so you need to apply a lot of optical force. So how do you circumvent that part? This is the second question. Please address. Yeah.
Yeah, so when we are talking about, so I'll begin with the second question. So yes, like the settling down effect due to gravity is a prominent one when we are talking about colloidal particles of that size scale as the one that I mentioned. So if we do like start the whole system like even like a minute or so after like our solution has been allowed to stay at rest, then it doesn't work anymore. So we have to pretty much start instantaneously. But if we do that and we basically set the trapping plane reasonably above like the bottom plate, the what we call as the trapping restoring force in the z direction, that is actually strong enough to counteract the pull of gravity. So and that turns out to be the maximum magnitude of that force turns out to be about 120 piconewtons or so, and that is sufficient to avoid that problem. But yeah.
That inhomogeneous.
Yeah. Yeah, so that is a bigger challenge. So modeling the inhomogeneity of things like cells is a bigger problem. So right now I don't have a great answer for it. So people have developed some viscoelastic models which they have added on as extra terms to those dynamics model that I said. The way we have circumvented it is, as I mentioned, we don't shine the beam directly on the cell or trap the cells directly. Primarily because of the reason that we don't want to damage the cells or affect their normal viabilities. So we kind of shine them on the particles, and we know how to model the particles well. And then we will have a collection of say 3-4 particles which kind of act as fingers to grasp your cell from the periphery and then move the around. And then all that we model are kind of the interaction between the sort of reaction forces between the particles and the cell at the boundary regions. So that's how we have dealt with it. But yes, if you account for the scattering that some of the beam would invariably fall inside the cell, then it does have to be modeled. And so far, we have not done that in any appropriate manner, and mostly it's something that has been ignored so far. But it's a great question.
Are there any other questions? If there are no other questions, then we thank Dr. Banerjee again for his very lucid and informative talk. And
Thank you.
Which is Professor Naveen Nischal is in replies at IIT Patna. Southern University of Oulu, Finland. His research include optical preparation.
Hello, Dr. Naveen,
Hello.
can you hear us?
Yes, I can hear you.
Yeah, please go ahead.
Okay, thank you. So I hope my slide is visible to you.
Yeah.
Yeah.
I'm
I have
audible too.
completed the introduction. Should I continue?
No, not needed, sir. I'll speak.
So he'll like Professor Naveen, please.
Okay, sir. Thank you. So very good morning to you all. Many thanks to the organizers for giving me an opportunity to discuss with you my research work. So my name is Naveen Kumar Nischal. I am currently working at IIT Patna as an associate professor in physics department. Prior to that, I was in IIT Guwahati for some time, and before that, I was in a DRDO laboratory at IRD as IRD Dehradun. So the topic which I am going to discuss is the image encryption through structured light. So basically, I shall be dealing about the optical crypto systems. It may be new for many of you or some of you. And in this case, I shall be discussing how optically we encrypt or decrypt or encode information, encode and decode information. In this scheme, I will be talking about two main techniques. One is based on the general exclusive OR operation. Another one will be on the optical singularity or the vector beam based schemes. So partly it overlaps what just now Dr. Banerjee has talked about. So what is the basic optical crypto system, or how we do encoding in the optics? Basic structure, what it started in 1995, called double random phase encoding. The technique says that if we start with an input image, or it may be a data, it may be a text, it may be a video, it may be some sound, audio, video, and image, text, anything. So we multiply with the random phase mask here and apply coherent beam of light to obtain the optical Fourier transformation with the help of a lens. And in the Fourier plane, we place another random phase mask. So what happens due to the application of these two phase masks, one in the input plane, another one in the Fourier domain, the input image get transformed into a noisy form. That form we call as the encrypted image. Now the output, what you see here, is a noisy pattern. So this beautiful image has been converted into this noisy form. Now there are some certain properties of this noisy form. It is technically it is called as the stationary white noise. Now in optics we have several degrees of freedom which can be utilized, which can be used for encoding information, such as speed is the best important thing, that it works with the speed of light, and that is why it has parallel processing ability. Other degrees of freedom like amplitude, phase, wavelength, spatial frequency, state of polarization, orbital angular momentum, these things we can choose differently, and they are added advantage in this optical based crypto systems. So the one of the schemes which I wish to talk about, that we start with the this laser system, and in this study we have not even used a laser, we have used a LED light also, because many of the reports what they have said that in optical crypto systems the output of the decrypted image, when we decode that information, it becomes noisy and it has lots of inherent noise. And one of the main factors of those noise is the laser source, because it introduces speckles into the path, and that is how the output of the decrypted output becomes noisy. So we thought of removing that noise, and we introduced two things. That one, we will replace the laser with a normal LED light, which is a partially coherent light source. While actually conducting this experiment, we use two spatial light modulators. It is a liquid crystal based electrically addressed device, which is an optoelectronic device, which works as an optics and electronics interface. It is a computer controlled device. Dr. Banerjee also mentioned about that. So we use two SLMs because it's a pixelated device. So we have to match the pixel to pixel matching we have to perform. This is what you can see in the setup, a snapshot of the setup. So we have to do this matching, and then we perform the exclusive OR operation with the keys and with the input information. And through this exclusive OR information, we encode the data. Now, what is the most important thing, what I wish to add here, that recently this QR code has become very ubiquitous. It is used everywhere. So this QR code, which is the quick response code, it's a two-dimensional binary code. So it's a two-dimensional barcode basically. It has some structures. It has data containing ability. In a barcode, you have very less data can be contained, but in a QR code, lots of data can be contained. There are different versions of also of the QR codes also available. Best part of the QR code is that it is noise resistant. It controls, takes care of the lots of noise. So we have combined them. This is what I can show you here. So the information is basically encoded into a QR code. So this is the plain text encoded QR code. This is the encrypted key here, encryption key here, and this is what the encrypted image looks like. But when we apply the correct keys, and we have to, of course, we have to reverse the order for decryption. This is what the decrypted images are. So decrypted QR code with correct keys. We have used the green LED. Then second one is the decrypted QR code with incorrect keys. Keys are incorrect. Then we did not get the original information. Here it is with an white LED, and this the last result which I am showing you is with a laser light. In that case, the laser introduces noise. So even if we are using QR code, but still there are noise, and that is because of the speckle patterns introduced due to the laser system, laser light. We analyzed our results, and we thought that the LED-based systems work very well, and then we are moving towards making a practical system out of that. Then we further thought of whether we can, because it was color, it was a black and white information or binary information. We should encode the color information. So in that case, we added some more features into that, and that added feature was in terms of the phase retrieval algorithm. So we used some phase information and generated that random phase information based upon the original plain text or the original information. This part, how the phase retrieval algorithm works. I will not go into the details of that, because this phase retrieval algorithm is very important, because we start recovering the phase information out of the recorded intensity information. So we combined everything, and then because it's a color information, so color information can be segregated into the 3 primary color codes, red, green, and blue. And we have to process each one of them separately and then combine them. I'm not going to the details of that. So this is what one of the examples of the colored information is. So one of the red component is seen here, and this is a phase value decomposition for the red component. Then we encode them into the QR code, and then we perform this exclusive OR operation. This is what the results you can see. And if we do everything correctly, then we are able to retrieve the original information. So these are some more experimental results, simulation as well as the experimental results. More details you can this journal publication. Next, coming back to the other part of my presentation, that's the structured light, and how a structured light can be utilized for information encoding. So interesting property of light is that it can be shaped spatially and temporally. So what are the parameters what we can tailor? They are intensity distribution or amplitude, or the wavefront, and polarization. So we can tailor wavefront, we can tailor polarization, we can tailor the intensity information. So there are 3 ways how to generate such structured light. It is diffractive optical elements or spatial light modulators can be used. Now it becomes important that when we have generated those structured light, how we can measure them. So there are 3 techniques. One is based on interference, another one is based on polarimetry, third one is based on diffractive methods. Now there are many applications where we can utilize them. Of course, the properties and applications are in optical manipulation. One of them, what the optical tweezers you have just talked about. I have not worked into that. Another one is then imaging and metrology, then optical and quantum cryptography. So our application area is basically the optical cryptography. This is the polarization ellipse. I will skip them. When the light beam is polarized, there are 2 types of polarized light. One we call as the vector beam, another one we call as the scalar beam. A scalar beam means it has homogeneous state of polarization, uniform state of polarization, and vector beam has different state of polarization across the cross section. So angular momentum, again, it involves because a vector beam has this associated angular momentum of the amount LH cut, and when light beam is traveling in the straight line, but when it encounters with some material, It can be also be rotating. Where it is rotating, it can be spinning or twisting. So one is associated with the spin angular momentum. Another one is we call as the twisting. Then we call as the orbital angular momentum. So spinning is based on the polarization and twisting is based on the wavefront. So these are the properties, and this is what we deal with them, and we are going to utilize that. This is what how the spin angular momentum interaction will look like, and the orbital angular momentum will look like. The spin angular momentum is because of through polarization, and orbital angular momentum is because of the wavefront rotation. So in optical singularity, they are all associated. So parameters which describes an optical field are amplitude, phase, and polarization, etc. So in optics, we have the singularity, which refers to a point at which some parameters describing the field becomes indeterminate. So there can be phase singularity, there can be polarization singularity. So phase singularity means polarization becomes indeterminate, and polarization singularity means the parameters defining the state of polarization becomes indeterminate. Intensity is 0 and these parameters become indeterminate. So we have to generate those beams having these properties, and then we try to encode them into the main schemes. Because of the shortage of time, I will not go into much details of this part. So this is how the polarization singularity we have generated those beams. This is how we have two beams. Commonly similar beams are the vortex beams and vector vortex beams. So one is the vector beams. Vortex beams have the helical wavefront, and vector vortex beam will have the vector nature of light. So it is inhomogeneously polarized, but vortex beams are homogeneously polarized. This is how we generate vortex beams. It has the property that it associates with the orbital angular momentum, and there is an associated term what we call as the topological charge. So it is the minus IL phi, exponential minus IL phi. L is the topological charge. So what we do, we can generate beams which will have different values of L. So like you can see some of the examples of the L equal to 1, L equal to 2, L equal to 3. Now this topological charge can have the value positive as well as negative. So there are values for L equal to +1, L equal to -1. Only the orientation is different. In one case it becomes right-handedness, another case it becomes left-handedness. Similarly, L will have -2, +2. L will have -3, +3. So L can take any value. We can start from 1 to 100. It is not restricted to that. To that only we can have the fractional values of L. So when it comes fractional values of L, and again positive and negative, then it is going to offer me a large number of parameters, and which I can utilize for information encoding. So this is how we generate this the vortex beams, and spatial light modulator is a very handy tool where we display some plane image and other CGH having that property where you have this 0 to 2 pi phase, because this SLM is a Pluto SLM which has the phase variation from 0 to 2 pi. So we can display it on that one, and then two beams will interfere and will give it as the desired vector beam. So once we have those desired vector beams, I'll skip some of them. I'll show you some of those results like this: the beam 1, this the beam 2, and this when they interfere, this is how we generate this spoke structure, and this has that property, and then we can utilize that. Orientation will change, will tell you that whether the L value is positive or negative. Similarly, there are several schemes what we have developed with self-referenced interferometric schemes. In that case, we can count how many L values are there in both the cases. Number of fringes we can count, and we can calculate the L value. So this is how there are different techniques we have used. I just thought of showing you these results. So there are many techniques, like here you can see the results with the L equal to -2, L equal to +2. Different geometries we have used based upon our need, based upon our ability and availability of the devices. Then we kept on working on that and thought of coming there, which is the best one can utilize and use that. So once we have got them generated those beams, then we thought of applying that for the encoding information. So let me get back to this encoding scheme. So this is what the encryption scheme is. So we have this input beam. Then in that case, in the spatial filtering, we can use 2-quarter wave plate. So we are taking two beams, two states of the beam, and record the intensity pattern here. So the different terminologies have been expressed here. So one is that I51, another one will have the I52, and then we are going to manipulate because it is this polarization based scheme. So what is important that we can only record the intensity values like the Stokes parameter S0, S1, S2, S3, and with those values only we can do the decoding. So encoding, we have to follow this structure, but the basic, it becomes very easy once we are dealing with the intensity parameters only, because for dealing with the complex functions we have to go to the holographic scheme or interferometry based schemes. So this is the important part, that we leave this complex function part, and we are recording the Stokes parameters S1, S2, S3, and that gives us the desired results. So these are some of those simulation results with the input image. We have generated those phase distributions, phi1, phi2, and these are the decrypted images. We can use this study, this aspect, for authentication purposes also. Authentication purpose means we do not need to decode the information, we do not need to decrypt the information, we simply want to test whether it contains the correct information. So this is what we apply the optical correlation schemes, and like these are the two data. One we keep under the category of true class, another one is the false class, and then we can follow up all those procedures. It gives us those results for the true class and false class. When it is true class, we get very good autocorrelation peak. When it is false class, we do not get any autocorrelation peak. So that tells us that without even going to the decryption procedure, we can simply authenticate the information. So coming back to this arbitrary vector beam generation. So the last result which I showed you, it was based on the simulation part only. Then we started working on the optical implementation. We have developed those vector beam generation schemes, generation and detection schemes. So then we introduced it for the encoding information. Now here in that encoding, in the previous case, we took two beams and utilize those 2-quarter wave plates and generate the desired pattern. Now here we can use arbitrarily, and when we go for the arbitrary vector beam, then it becomes it offers more complexity to the system. If somebody steals the information and tries to recover that, then it becomes very, very difficult for them. So then
you have 5 minutes.
Okay, sir, I'm almost at the end now. So this is how we start with we have 3 plain text information, 1, 2, 3, are all digital format. And these are the phase information we generate during the process, use a quarter wave plate. And finally, this is the pattern polarization state, what we are going to look at. This is what it gives. It has a random nature. And we record the Stokes parameters, S1, S2, S0, S1, S2, S3, and we can start decoding them. So ciphertext is basically obtained by recording the Stokes parameters of output beam and using this relationship. This is the decoding scheme. So we will start using one of those keys one by one, and this gives us the decoding. So one phase information is I5D, another one is IK1, but we are using these two. I'll get the first decrypted information. Similarly, use another orders, another set of phase functions, then we will get another function, another result, and so on. So this is what the basic optical scheme is. This part is for the generation of the vector beam, and the second part is for the encoding. And again, here we use this, we can use QR code, and for any other information, this we can decode them. So there are three aspects associated with it. Initially, we had used laser light, but further I have also used an LED light. Those results I'm not able to show you now. Further, we have used LED light. So I start with the basic analysis that we have to leave away this laser system to avoid the speckle generation. So we will go to the LED based device, and then we will do this encoding because it is based on the intensity recording. So it becomes easy to store data, easy to transmit data, and easy to decode data also. But on the other hand, there is no compromise with the strength of the security in this case. So I'll conclude that techniques based on this various geometries for the generation of the vector beams, and I have discussed, and based on this, I have discussed two geometries for the optical crypto systems. So thank you so much. I must acknowledge my PhD students and collaborators for we are taking some help from them, and we are still working and collaborating, working on those aspects. So thank you so much on this topic. This is my research lab, what you can see virtually. And on this topic, I have authored a book which was published by Institute of Physics UK. It was published in December 2019. It's an e-book, but the hard copy is also available. So if somebody is interested, you can go through those details of that. So many thanks again for giving me this opportunity to interact to you. Now, over to you, sir. Thank you so much.
Hello, am I audible?
Yes, sir.
Yeah, there are a few questions. One
Yes,
is,
sure, sir.
how good and robust is this method in decoding unknown? Hello.
I did not. Yeah. Please, could you please repeat the question? What you mean? What I can understand that you want to know how to decode that.
No. How good and robust is this method?
Okay.
Sorry to intervene, Dr. Rawat. There seems to be some problem in the net connection from your side. So I would request coordinator to please read the question again.
Dr. Nischal, there is one question. What is the resolution upon which you can encrypt and decrypt back original image accurately?
Yeah, resolution means you want to know what is the minimum dimension.
What is the resolution upon which you can encrypt or decrypt back original image?
Yeah, it depends here on the resolution of the two devices. Our basic device is the spatial light modulator. It depends upon the resolution of the spatial light modulator. And currently that has 1000 cross 1000 pixels roughly, what we can do. But even if you have a larger size object, even if you have a smaller size object, you can do imaging, and again we can feed back to the system.
How robust is this method in generating?
Yeah, robustness, I did not talk more in detail because you can go through my paper. It is very robust. It is very, very robust. We first check the robustness, then only we propose some schemes, because there are many attack algorithms which are existing and which people work on, and they prove the systems vulnerable. So we first check the vulnerability, and the scheme what I have just presented is very, very robust.
Each decryption gives unique result.
Yes. It depends upon there are 2-3 schemes into that. One scheme is based upon the input image. So we have used this phase retrieval part that I said in the beginning. That phase retrieval part, it is depending upon the input object. So if you change the input object, we have to generate another phase information. Then we fade into this. Then we have another random phase mask associated with that. So there are many things associated with that. and then we do the decoding. So it is very, very robust. So far, no one has proved them vulnerable. The initial schemes of the double random phase encoding, which I showed you in the beginning, like this slide, which was proposed in 1995, this has been proved vulnerable, but the current ones have not yet been proved vulnerable, and we have checked all the possible attacks onto this. But one thing one has to remember, that no encryption scheme is sacrosanct and it cannot be decoded. But what is important, that how long it is going to take to decode that. I always give my students one example, that if I am making a question paper and somebody comes into my office and breaks my computer and takes that starts decoding my computer and try to get the question paper, and tomorrow 10 o'clock the exam has to start. If he or she is able to decode it after 10 o'clock, it has no meaning. It becomes meaningless, and then I am successful. So this is kind of thing we have to secure, because even in the digital encryption schemes, there are no scheme which cannot be broken. Only thing is that in the digital schemes, we keep on making very longer encryption key length, so that when somebody tries to recover it, it takes very long amount of time, very large amount of time.
Thank you, Dr. Nischal, for your nice talk and nice discussion. Thank you very much.
Sir. Thank you, sir.
Now we will move to the next part of our talk. Third one is from Dr. Amit Rao. He is from BARC Mumbai. Dr. Dr. Rao, please stop sharing. Yeah. Dr. Amit Rao is head dynamic compression physics section of applied physics division of BARC. He completed his bachelor's in engineering in electronics and communication from Gujarat University and obtained his PhD in data processing and estimation techniques from uncertainty minimization in the dynamic compression experiment from Homi Bhabha National Institute. His field of specialization include experimental signal processing, development of diagnostic techniques for dynamic compression experiment. He has more than 20 publications in various journals. Dr. Rao is recipient of DAE Scientific and Technical Excellence Award, DAE Group Achievement Award 2010, 12 and 16, and DAE Special Contribution Award 2009 today. He will speak about characterization and utilization of VISAR in shockwave experiment. Now, Dr. Amit Rao, you can share your, please share your transparencies. Dr. Amit Rao, can you hear me? Dr. Rao? We are trying to connect with Dr. Rao.
Hello, we are trying to connect Dr. Amit Rao. Please stay with us.
Yeah, we will connect with Dr. Amit Rao within a few seconds. Please wait. We are trying to connect Dr. Amit Rao.
Am I audible? Hello.
Yes.
Okay. So I'm start sharing my screen.
Yes, please.
So shall I start?
Yes, please.
Okay. Thank you. Thank you for nice introduction, and also thank you NLS-30 for providing me this opportunity to present my work. So today, what I'll be discussing is about the velocity interferometer system for any reflector, which is called visor, and it is one of the important instrument in shockwave experiments. And my present talk will be based on this instrument only. So the plan of my talk will be like this. I'll be explaining briefly about the shockwave experiments, how they can be done, and what are the measurements are taken, what are the measurements being done during the experiments. Then I will explain some of the important instruments that we have developed in our lab. This I'm taking care, like since we are in NLS or laser symposium, so these instruments are basically laser-based instruments. Then I'll be presenting my work on characterization of recording system of visor, interpreting their results. And then one of the application where visor can be used for measuring mechanical properties of aluminum alloy, that I will explain. And then we will summarize the presentation. So just before starting to go into shockwave, I'll just show you a small clip. Okay, the clip is this much only. So what we are seeing in this clip is there are some jet planes, and what these jet planes are doing is they are transiting from subsonic speed to supersonic speed. And when they are transferring or changing their speed from subsonic to supersonic speed, what is happening is you can see the dense cloud is forming behind them. And these dense clouds are the indication of formation of shock wave. So with this, I will give you the formal definition of shock wave. Shock waves are basically the disturbances, and these are the disturbances which travel in a medium with a velocity which is more than the sound velocity in that medium. So if I'm talking about air, the sound velocity in air is around 340 meters per second. So if any disturbance, like a plane in this case, is moving with a velocity more than 340 meters per second, it will create a shock wave. And if I take an example of, say, steel alloy or something, where the sound speed is 5.7 kilometer per second. So if the disturbance is traveling more than that speed, it will create a shock in the steel alloy. So ideally, the shock wave looks like this, where there is a disturbance which is discontinuous. So material ahead of the shock is in the normal condition. It is not feeling anything. It doesn't know what is coming behind it. But the material which is behind the shock is at very high pressure, the densities are very high, the particles are moving very high speed, and it contains lot of energy. So this is the ideal shock wave. And how these shock waves are generated in the sample? How the shock waves are generated? So what happens is we accelerate a flyer, which can be a metal or any material. We accelerate to a very high velocity, and then when this high velocity flyer impact on a target which is stationary, it generates a pressure pulse inside the target as well as in the flyer. Typical shape of pressure pulse is like this. When shock moves in the target, it rises to a high pressure very instantaneously, stays there till there is a no release wave or there is something low pressure coming to it, and then it goes to a ground state or normal condition. Now, what is the importance of thickness and this peak of this pressure? It defines the flyer velocity. With what velocity you are flying the impactor. That defines the peak pressure. And then the thickness of target and flyer, they combine define the pulse width or pulse duration. This is called pulse duration, pulse width. Because the thicker is the sample, the more time it will take these waves to come in and release the sample. The relation between shocked region and unshocked region is governed by the conservation equations. They are the mass conservation equation, momentum conservation equation, and energy conservation equation. So what happens is the velocity of shock and particle, they are related to the compressed density behind the material. And then momentum of conservation, where the velocity of shock and particle are related to rise in the pressure. And then these two combines give the energy conservation. So if I measure some of the parameters of the shock material, I can characterize the material, what is the condition before shock and after shock. And what are those measurements? These measurements are fly plate velocities, shock velocities, particle velocity histories, and stress histories. Next, here I am trying to explain how a typical shock wave experiment where a fly plate impact the target is shown here. So here is the flyer, which is accelerated to a velocity ranging from 100 meter per second to few kilometers per second, maybe up to 8 or 10 kilometer per second, depending on what kind of energy you apply to it. Then it's hit on the stationary target. Before hitting the stationary target, it passed through an array of sensors. These sensors can be electrical sensors or optical sensors, which measures the time of flight of fly plate and measures the impact velocity before impacting on the target. Then you have some sensors which senses that the impact is going to happen. So you need to get your systems ready so that you can record the system, record the data. Then we have some of the sensors which are inserted in the target at different locations. Like this is on the impact surface, this is at the interface, and it is at the rear surface. So these sensors are basically the shock arrival sensors. So what they do, they measure the arrival of shock at these points. And by measuring time of flight between these two sensors, they can measure the shock velocity. Then we have some magnet gauges. Magnet gauges are the stress gauges which are inserted in the sample. They are sandwiched between two plates. And then when shock wave passes through this gauge, it gives the resistivity of this gauge changes. So this change in resistivity is measured and it gives the pressure information about the in the system. Now, as you see, all these shock arrival sensors and gauges, they are to be embedded into the system. So when this is to be embedded in the system, that means it is changing the initial condition of the sample. But then we have a class of instruments which are optically coupled to the system. Optically coupled means they are not in the physical contact, but they are launching some light on the target and then collecting the reflected light. And based on that, they are measuring the property of the surface. So these instruments are like visor, PDV, which I am going to explain. They measure the free surface velocity or movement of back surface of the target. So these are non-contact type. They are not in physical contact with the system, and still they are giving the information. Important part here is the visor and gauges. These are the time resolved information. They give the profiling of the gauges, the profiling of the parameters. But shock arrival sensors or time of flight sensors, they give the average value. They don't give me the profiling of the signals, parameters. Here are some parameters which are measured during experiment and type of sensor. Shock velocities are measured with self-shortening pins, optical pin, Asian pin. These are the discrete and in contact measurement. This can be electrical or optical. Then fly plate velocity measurement, which are again electrical or optical, but they are discrete and in contact techniques. Stress profile, it is continuous technique, but electrical and in contact technique. But free surface velocity measurement using Doppler-based interferometers like visor, PDV, Fabry-Perot, they all are time-resolved profiles and they are non-contact and optical methods. Shock temperature is another parameter which are measured optically, but it doesn't involve any incident source. What happens is during shock, the temperature rises of the sample, and because of the shock temperature, there is a shock luminescence. So that shock luminescence are measured, and this radiation parameter measures the temperature. Now, why we are talking about velocity at all the time? Because we know that by conservation equations, if I know the shock velocity and particle velocity, I can completely characterize the system. I can calculate the density, I can calculate the pressure, even I can calculate the energy imparted in the system. So this is why velocity measurements are important, because it completely characterizes the material. Second thing is, if you have a velocity profile, it gives you the each point information about how the shock is rising and what are the features available at the rising part of the shock. So this information is a very important input to propagation code, wave propagation code, which are used to simulate such kind of experiment and such kind of scenarios. So this velocity measurement gives very good input to those these codes. As next is, this time resolved information provides elastic plastic transition, phase transition, mechanical failure, all this information are provided by this velocity measurement. That is why we need to do velocity measurement. Another part is why interferometer. We are saying velocity measurement, we are saying velocity interferometer, but then why interferometers? So interferometers are different class of instrument. Basically, if we have to resolve any evolving surface, and if we are impacting a light on it, so what we get is the phase change in the light. So we need to detect what is the phase changes of the reflected light that we need to detect. But what happens is the absolute change in phase is very difficult to measure. Like in this particular case, if I take a 1550 nanometer laser and I take what is the wavelength shift of that laser, if it is reflected from a surface which is moving of around 1 kilometer per second, then it is only 0.001 nanometer. So that change in wavelength is very low. So absolute change in wavelength detection is very difficult. But what interferometer does is it generates beat frequencies. What happens is when beat frequencies are generated, these signals and frequencies are downshifted to lower frequencies. And these frequencies can be still very high, but can be recorded and can be utilized for deriving the velocity profile. So velocity interferometers in a class, they are the time resolved velocity measurements. Now, the commonly used interferometers in dynamic compression or shock experiments, they are list are many, but what I'm trying to do here is that I'm trying to classify them on based on their sensitivity and based on their recording system. Based on sensitivity means, in general, if I say Michelson interferometer, it is displacement interferometer. So it when a surface is displayed, the phase changes and the phase is corresponding to the displacement, like lambda by 2 displacement corresponds to 1 fringe shift. So that is basic displacement interferometer. But in dynamic compression experiment, we use velocity interferometers also. But what happens is these velocity interferometers uses the differential Doppler measurement. If we use differential Doppler measurement, then this phase change is directly proportional to velocity instead of displacement. So these are the velocity interferometers. So based on whether fringe count is proportional to velocity or displacement, they are classified as displacement interferometer or velocity interferometer. Now, based on recording system, earlier the recording system is like whatever scope you are using, whatever ADC you are using. So these are forms, or whatever optical detectors you are using, they forms the recording system. So optical recording system are mostly the cameras, streak cameras. So what happens is the development of streak camera is much earlier than the high-end oscilloscope which are available right now. So initially the Orwes, the Fabry-Peros, these are the differential Doppler measurement equipments or interferometers, but they were recording on streak camera. So the streak camera were the main recording equipment. So that is why they are recording is based on optical recording or using streak camera. Then there are electrical recording system like PMT and photodiode. Visor is one such of type. Then PDB and specular deflection, velocity interferometer and displacement interferometer. So these are the electrically recording systems. Now I'll be moving to next part of my presentation where I'll be discussing some of the instruments that we have developed and we are using in our lab. One of such instrument is Fabry-Pero interferometer. Since it's an interferometer, so what happens is here is the surface which is evolving in time. So what we do is we shine a laser on the surface and collect the reflected light. It passes through a Fabry-Pero etalon, and this etalon generates fringe pattern which is focused on a streak camera. So when you focus this streak camera, you get a fringe like this. I hope, okay, the streak camera is a camera. Since it's a camera, it gives two-dimensional information only. But the two dimensions are not the space dimension. One is the time dimension. This one is a time dimension. And this one is the space dimension. So here what you see is, this is the initial fringes which are there at t equal to 0 when there is no movement in the surface. Okay. As the camera triggers, the time axis moves. So this is my time axis. Now it is moving from t equal to 0 to next higher level. And then this is the point from where my surface starts evolving. So when as surface is evolving, it is generating fringes and fringe separations are increasing. So by knowing or recording this fringe separation, what we can do is we can relate them to my velocity. So here you see the number of fringes, they are not related with the displacement, but they are related to the velocity directly. So that is why we are saying that this is a velocity interferometer. This is the optical setup of fabric velocimeter in our lab. It has a typical range of 0.2 to 10 kilometer per second. Fringe constant is this first term, which are the constant of the instrument, speed of light, wavelength of the laser used, then it is refractive index of etalon, fabric etalon, and their mirror separation. So this is the fringe constant, and then we have by measuring the diameter of fringes, we can calculate the velocity. Next class of instrument is photon Doppler velocimeter. This is one of the recent development, and it first reported around 2006. And this instrument theoretically was available much earlier because it is a simple Michelson interferometer, but only difference is it is in all fiber based. So what happens is the laser source is launched in the fiber, and then reflected light is again collected through the fiber. Inside the fiber, beating takes place, and this beating is detected by the digitizer. So what happens is when we are saying fabric arrow or visor, they are measuring differential Doppler. But what PTB measures is absolute Doppler. So here the velocity is related to frequency. As we know, frequency is the rate of change of phase. So since we are measuring rate of change of phase, it is related to velocity. So this absolute Doppler measurement, velocity of the evolving surface is related to beat frequency. Now, since it is measuring beat frequency, so what happens is number of signals or frequencies are more. I would like to just go back to previous slide. Here, what we can have is this is kind of one fringe and second fringe. These are the number of integer fringes which are used here to calculate the velocity. So you see there are only two fringes and you are going up to the velocity of 4 km per second. Since your fringe constant is very high. Okay. But here what is happening is this data is of around 600 or 700 meter per second only. You see the number of fringes. So these many number of fringes can be recorded, and time scale, if I say, it is not more than 100 or 150 nanosecond. So the time that signal is recorded, but we cannot count the number of fringes in this signal. But once you convert it to the frequency domain, time frequency domain, so what happens is the evolution of frequency inside this will give you the information about the velocity, because beat frequency is proportional to velocity. So this is frequency time plot where I can see the change in evolution of frequency, which is related to velocity in this way. So this we have this equipment in our lab and we are using it on regular basis. This is the setup photograph where you have this lasers optical setup for all those equipment, and then oscilloscope. Then last class of instrument which are very important and which I'm going to discuss more about it. But before going further, I'll give you some comment about this visor. The theory and technical know-how is available. So this equipment is initially developed in 1965, where there is no high recording instrument, nothing was available. At that time, it has been conceptualized and implemented. So the theory, the literature, everything is available, and it is based on differential Doppler measurement. Then it can use low bandwidth equipment to record the data. So what happens is now, as we see that absolute Doppler is giving me very high number of fringes. So these many fringes at that time in 1965 is very difficult to measure. So what they do is they use differential Doppler measurement. So in differential Doppler measurement, there is another down conversion of frequency, and then this frequency or the phase is now proportional to velocity, like in the case of fabric interferometer. So low bandwidth equipment can be used to record the data. As you can see here, this is a free space equipment. It requires lot of optical alignment. It requires very precise component. So that part is along with this equipment. Second thing is system characterization is critical. System characterization means apart from optical alignment, what happens is the amplitude of each fringe is very important, because detecting the fractional part of fringe defines your resolution of measurement. So once you have characterize the electrical measurement part, or how you are going to measure the amplitude of the fringes, then this system is very good. So
Dr. Ram, you have 5 minutes.
What? Okay, it is. I'm already done. Okay, so I'll just quickly go through the characterization part then. So this is visor where we have a this light is coming, and then it is going in the system where it has been polarized and delayed using echelon. With lambda by 8, we create a quadrature signal, and these quadrature signals are measured through 2 PMTs. Here you can see again the number of fringes is proportional to velocity, so it's a velocity interferometer. Here you can see these are the recorded fringes of the system. These are in quadrature. One is moving with a cos function and another is moving with a sine function. Phase is the which is proportional to the velocity. This is the error in phase. So what we are having is the voltage measured during the experiment. Then these are the DC offset. DC offsets are this offset which are due to the maybe due in the system, and then there are some time varying amplitudes. This time varying amplitude is the signal which is defining by the defining my phase amplitude fringes, amplitude of my fringes. Then this is signal phase, phase error, and these are the noises. So how to estimate the velocity? We measure the velocity by first calculating the fringe constant. This fringe constant is the ratio of amplitude versus the DC offset. So this DC offset has to be minimum. So as low is my DC offset, the more is my fringe constant. Fringe contrast is important to identify the fractional part of fringe. And then once we know the fringe contrast, we can calculate the phase estimation, and then we can go for, by knowing the number of fringes, we can calculate the velocity by knowing the fringe constant of the system. Now, what I showed you is the desired part. But what reality is, because of we are using PMT, we are having all the noises and the saturation effect and the presence of octopulse of the PMT. And because of dark current, we have a lot of DC values. So what we have is very bad time response as well as amplitude response. So these are the fringes we are lost during the recording of the system. So that is why what we require is the output or should be the linear with respect to input. Output of PMT should be linear with whatever optical inputs are available, and output should have a sufficient SNR so that we can detect the signal. So for that, we created an optical measurement setup where we switch the laser into a pulse of required duration for our experiment. We measured it through the optical visor optical system and measured the signals. So three variables we are having right now. This is the laser source, optical aperture, which is at the imaging optics of this, and then PMT gain. Recording system consists of this. This is optically coupled PMT. Here we have optics which couples the fringes onto the PMT. It contains aperture, it contains focusing optics, polarizing splitter inside this, and then PMT. What we are measured is the signal amplitude at different laser volt powers with aperture settings, and then signal amplitude with laser power with different PMT gains at fixed aperture, and then per shift with PMT gain. What we got is SNR, signal to noise ratio, with respect to laser power. So as we increase the laser power, our SNR increases. But you see at the lower value, the SNR is low because it is not allowing more light to go in. So in separate studies, what we got is the SNR of 20. If the signal is having SNR more than 20, it is better to analyze. So we kept the power of laser, which is giving me SNR more than 20. Then aperture SNR calculation with aperture opening, because if I open aperture very large, it gives me background current, background light inside, and if I open it very small, it gives me low SNR. So I kept the aperture opening from around 25 to 40 for my setup. Then I measured the gain linearity at different optical power. I measured the gain. So you see that if the lower power is there, the gain range is high, and for higher power of laser, the gain range is low where it is linear. And I also measured the fall time and rise time. This is the complete summary of exercise. Here what you see is the with laser power, I measured the amplitude at different PMT gains. These are the different PMT gains. And what I did is I found the linearity estimation based on additivity and homogeneity. And these two black lines shows me the data that inside this, my system is point linear with non-linearity of only 5%. So this defines my operating condition with which if I operate my PMT and recording system, I can get the better result. And this is what I get. Before applying this constraint condition, these are the losses of signal. I cannot get these fringes back. It is difficult to analyze in the software or post-processing. But after that, the signal amplitude increases and I can easily resolve them in my post-processing. So next is some application. Here is the measured velocity profile using visor. What I want to show you here is this particular neck is representing elastic to plastic transition of my material, and then this is the plastic part. here the pressure is constant and then it is falling because of the release. But when the mechanically material fails, it generates a separate plane and from there shock is reflected. And this signature, it signifies that material failed mechanically. So there is a fracture inside that. So by measuring various parameters of this, what I can measure is elastic Hugoniot limit and corresponding strain rates, yield strength of the material, spall strength or fracture strength of material, and strain rate. These measurements are in dynamic nature. These are not at the static condition. So we do experiment on two very important aluminum alloy which are having application in different aerospace industries. So one is 2014 T6. We did different experiments, measured their parameters. So we measured their spall strength and yield strength. Similarly, we did it for 2024 T4. There again, we measured the spall strength and yield strength and compare the data. So what we here we can see is the spall strength of aluminum 2024 T4. T4 is on the higher side compared to T6, and this difference could, and this is the measurement in dynamic range, and this difference could be due to the different heat treatment of T014 T4 T6 then 2024. And I will just summarize this my work, that what we have done is we have laser based instrumentation, which is the key instrument for studying the material under shock wave loading. Then we have interferometers like Fabry-Perot PDV visor. They are developed in our lab and are in use. Then we have a procedure for recording system characterization of visor, and it has been incorporated. Why I am saying procedure is because once I change my optical setup, these absolute value may change. But the procedure with which this data is being calculated, this can be followed anywhere. Then we have demonstrated the application of visor by measuring mechanical property of aluminum alloy. I'll take one moment to give this slide. They are the major mentors and collaborators of my work, Dr. Gupta, Dr. Kaushik. They started the shockwave work, interferometer work, and then we are continuing to do this in our lab right now. Thank you. I would like to from my side it is over, and thank you. Am I audible?
Hello?
Yeah.
Rawji, can you hear?
Should I? Am I audible?
Yeah.
Yeah.
Acha. Dr. Amit, it was a nice talk, briefing all the major velocity, high-speed velocity measuring instrument. I just wanted to ask one thing: how have you calibrated your measurement? The measurement you have carried out for using visor, how accurate it is? Have you done any comparative study or calibration thing?
Yeah, sir. Actually,
what is the accuracy?
Yeah. So what happens is we are developing this instrument for a very high velocity system. So we cannot have those velocity system at our will. Like we cannot have that as a calibrating system. But what do we have is we have a system or experimental condition. Like I know the properties of aluminum or a standard material during dynamic compression. I know if I impact it with some certain velocity, I'll give these parameters. So first type of calibration is by measuring the physical parameter or interpreting the data. And second is by the instrument design itself. So what we can see is this is the velocity interferometer. The number of fringes are low, and counting the integral number of fringes is not difficult. Difficult part is calculating the fractional fringes. So fractional fringes, if I do all the calibration, what I showed the procedure of defining the amplitude, then it is reported in the literature, and we have also observed that errors or accuracies of more than 1%, as low as errors will be as low as 1 or 2%, not more than that. We can achieve the accuracy of very high level.
Okay, thank you. Shadi, any question in chat box?
Yeah. What is the wavelength range that visor can work with? This question is asked by Dr. Shobha Shukla.
Yeah, the visor which we are using right now is as 532 nanometer using DPSS anti-arc laser.
Okay. Here are no more question in chat box.
Okay. Then for visor, do you have any specific requirement of laser, means power and line width requirement?
Say say basically we need a coherent laser. Coherent laser in the sense what we are working here is temporal coherence because we are delaying we are making differential Doppler. So the phase wavefront should not disturb at the two time instance. So line based requirement is there. And power requirement is not very high because right now we are working around 0.5 watt or something. So power requirement is not very high, but coherence requirement is, yes, definitely it is there.
Okay, thank you then. Shaji,
Thank you.
can you
Thank
close?
you so much. Yeah, thank you so much. Thank you for allowing. Thank you.
Thank you for giving a nice and lucid talk. Now we'll close this session and over to session management for further announcement.
Thank you, Rawatji. Thank you very much for for chairing this session for us. And now we will move to the next part. Right now we will take a break for lunch. And the next session is again poster presentations. And I request all of you to please join these sessions at 1:45. So we will break for lunch here. And I also request all of you that you please visit the exhibition gallery. There you will find many interesting instruments which will help you in doing your research in a better way. Thank you.
Welcome to poster session day 3, auditorium A. We'll begin the session in 2 minutes.
Hello. Sir, shall we begin the session? Chakera, sir. Hello. Chakera, sir, can you hear us? Chakera, sir, can you hear us?
Excuse me. Hello. Ajantika.
Yes.
Hello.
Hello.
Yeah, I'm Pradhan speaking. He is having a little bit discussion among these judges. Okay. So you are with for some time actually.
Okay. Okay, sir.
Yeah, just 2-3 minutes. He has talked to me, then he is talking to other person. Okay.
Okay, sir, sure.
Okay.
Please note that the presenters will be made panelists shortly before their turn comes. And also, we'll be sharing the slides for all the presenters from here.
Judges, shall we start the session? Chakera sir? Pradhan sir?
Yeah, I am available, but Chakera sir is probably talking with the another person.
Okay, sir.
So anyway, I am trying to contact him. As soon as he is available, then we can start.
कविता
Pradhan sir, shall I begin?
Hello. Yeah. Dr. Pradhan and Dr. Umakant Rapol, you people are there, na?
Yeah, I am there, but I don't know about other actually. I
Dr.
am Pradhan,
Umakant?
I am there.
Dr.
Umakant, we have
Umakant,
to see.
are you there?
Actually, Dr. Chakera was not able to use his microphone. That's what. Yeah, Umakant has joined now.
And yeah.
Dr.
Okay.
Umakant, you are there, na?
I am here. Yeah.
Yeah, Dr. Umakant and Dr. Pradhan. Dr. Chakera is having slight issue with his mic, so he'll soon join. But
Yeah,
we'll
yeah.
start the first person.
Okay.
Yeah,
Yeah.
thank you. You have that 3 minutes and 2 minutes question answer. Yeah.
Yeah.
Good afternoon and welcome everyone. We are now going to start the poster session for day 3 in auditorium A now. We request all the presenters to be online. If somebody is not connected, we will go to the next presenter and your turn will come in the end. Every presenter will have 3 minutes to present. After 2 minutes, there will be a first bell. And then after 3 minutes, there will be another bell. Please try to wind up your presentation quickly within 3 minutes. And then in the next 2 minutes, the judges will take over for question answers. So judges, shall we begin with the first presenter?
Yeah.
Yeah, please.
Okay. So I now request Kavita Yadav to begin her presentation. Her poster number is CP0402.
Okay, good afternoon, everyone. Am I audible?
Yeah.
Yes, you are audible. Please.
Okay, good afternoon. So I'll be discussing the effect of residual Doppler averaging on EIT when we consider an inverted Y-type of system. So first of all, I'll just give a brief introduction of what is EIT. So EIT is basically electromagnetically induced transparency. So in general, when we study when we study a two-level system, so what actually happens is when we shine the laser, we are getting an absorption and at the detuning or at the zero detuning or at the resonance condition, we are getting maximum absorption. So now instead of a 2-level system, if we take a 3-level system and a third and a second field, which is actually stronger than the first field, which we call actually a pro field, and the other one a control field. So instead of absorption at the resonance, this time we are getting a transparency. So we can actually control this transparency by changing the strength of the second field, which is stronger field, and by changing a detuning as well. So in general, we study 3 level EIT system called as lambda, ladder, and V. So what if we actually add now more number of levels and fields, so that can actually enhance our EIT control in different systems. So in general, when we talk about EIT, so in real atoms, this wavelength matched condition. So this wavelength matched condition is actually the condition where we are taking 2 type of fields, for example, the Prof field and the control field. So if the wavelengths of these 2 fields are equal or are similar to each other, so we are actually getting a wavelength matched condition. So in general, in real atoms, when we study particularly ladder type of system, so this wavelength matched condition is difficult to achieve. So in general, most of the EIT studies take this wavelength match condition to minimize the effect of Doppler broadening, or we can say the residual Doppler effect, Doppler width. But in real atoms, it has been observed that this wavelength matched condition is difficult to obtain, particularly when we are considering a ladder system and when we have a higher excited state. So in this particular work, I have considered an inverted Y type of system, so which is basically a combination of 2 EIT system, lambda and ladder. So can you please move to the next slide? Okay, the left one is the level diagram of 4-level inverted Y type of system. So in this particular system, the level 1, 2, and 3 are forming actually a lambda type of system, and the level 1, 3, and 4 is forming a ladder type of system. So this gamma C here is the ground state decoherence, and gamma Ij are the decay rate from the excited states. So in this particular system, for this lambda system containing 1, 2, 3, 1, 2, and 3 levels. So here we have to take this probe and control co-propagating to each other, so that we can reduce the effect of Doppler broadening. And in the ladder system, we need to take counter propagating lambda T and lambda C, so that we can reduce the effect of Doppler averaging. So I have discussed here stationary atom case as well as moving atom case. So in this diagram, in this upper diagram, so we have this Doppler free case because the atoms are rare. So here we can see that for 2 type of different systems, if we take different levels as this 4 level, the level 4, the first one is 5d pi by 2 state of rubidium 87, and the other one is 44d pi by 2 rubidium 87. So in this stationary atom case, similar kind of EIT profile is obtained for these 2 subsystems of this lambda inverted Y system. But can you just oh my God.
Judges, please start questions. It is already 4 minutes.
Yeah.
Okay, so yeah.
Yeah, please go ahead. Please go ahead. Please go ahead.
Rakul,
Please
you
go
can
ahead,
start
Pradhan.
with,
No, Pradhan, please go ahead.
yeah.
Sorry.
So you are talking about only absorption part, right?
So similar effects will be observed when we actually talk about the dispersion as well. So right now I'm just discussing. Can you please move to the second slide?
Yeah, no, I'm coming to my question basically. And if you will see the dispersion specifically for inverted Y kind of system, then how it will look like? Can you tell me?
So actually, sir, as we can see in this absorption part, so at the line center we have a narrow transparency window, and then there are other 2 transparency windows as well. So similar kind of actually behavior is observed in the dispersion part as well. So we actually get a splitting in the dispersion profile as well, similarly as we are getting in the absorption profile.
And, will you get at the line center? Will you get anomalous dispersion or normal dispersion?
Actually, both type of dispersion we'll be getting, because here along with this transparency window, there is a slight absorption peak kind of behavior as well. So we'll get both the things, anomalous and normal dispersion.
Dr. Rahul, you can.
Yeah. So, Ms. Yadav, I didn't really understand exactly the crux of the matter in terms of what is your aim, objective in this three-level inverted Y system. What do you want to do, and how do you achieve that?
Sir, basically, I'm just trying to here tell the importance of this wavelength mismatching factor or wavelength matched condition in real atoms when
So,
we are
which wavelength mismatch are you talking about? Are you talking about the wavelength not coming in resonance with the atoms or with the particular two levels of interest, or
so,
what?
so basically, in this EIT system, we are talking about this two photon resonance condition. For this lambda system, we actually try to minimize this minimize this two photon resonance, so that the photon resonance terms comes equal to delta P minus delta C. So when we actually
Here
take
you
this.
have three photons. Here you have three photons involved in the process, right?
So, sir, actually, in this particular case, when we are actually analytically deriving this coherence term, which is actually rho 1, 2, so we have two similar type of system acting simultaneously. The one is lambda. So here we are actually getting two different type of two photon resonance condition. There is no three photon resonance thing happening here for this particular system. So there are two different two photon conditions. One for the lambda one and the other one for the ladder system.
Okay, fine. Thank you. I'm done, Mr. Pradhan.
Yeah, so we can move to next speaker.
Yeah, yes.
Our next presenter is Rajaya Kaita, poster number CP0403. Rajaya, can you hear us?
Yeah, yes, ma'am. Am I audible, ma'am?
Yes, yes, please begin.
Yeah. Can you make this my presentation in bigger screen, ma'am? Slightly, can you enlarge?
Rajaya, that is at your end. You can make it bigger.
Okay. Okay, sir. Shall I start, sir?
Yeah, please go ahead.
Yeah. Good afternoon, everyone. This is Kaita Rajaya from ISRO, Bangalore. Here I am presenting CPT resonance frequency shift in rubidium neon vapor cell for application in atomic clock. Coherent population trapping is a quantum interference phenomena. This phenomena in alkali atoms is used for the development of miniature precision atomic clocks. First time we are developing the CPT-based atomic clock for space application, particularly in our NAVIC satellites. Atomic clock is the heart of the satellite navigation system, which provides the timing reference for navigation signals. The performance of atomic clock depends on CPT-based atomic clock depends on the CPT resonance characteristics, which are influenced by the operating parameters, mainly laser intensity and cell temperature. Here, the bottom three diagrams. First diagram shows the hypercon energy levels in rubidium-87, which involve the CPT phenomena, which are excited by using laser light. And the second diagram shows the clock development scheme, which is utilized for the experiments by controlling and varying the laser intensity and cell temperature to optimize the clock performance. And the third figure shows the realized engineering model of the physics package, which we used for these experiments. Can you go to the next slide? Atomic clock performance is expressed in terms of the frequency stability. As shown in the first equation, the short-term frequency stability of CPT-based atomic clock depends on the quality factor, which defines as the ratio of contrast to full width of maximum. Whereas the medium to long-term frequency stability depends on the center frequency shift fluctuations. The top figure shows the typical measured CPT resonance, where the frequency shift is approximately 9 kHz. This frequency has two major terms. The first one is light shift, which depends on the light intensity, and the second one is temperature shift, which depends on the cell temperature. As shown in this equation, the light shift coefficient and temperature shift coefficients are calculated by measuring the rate of change of frequency shift and dividing by the theoretical center frequency. Coming to light shift, the bottom left side diagram shows the variation of the change of light shift at low temperature and high temperature, say 63 and 85 degrees centigrade. And the bottom right side figure shows the measured light shift coefficient variation with temperature, which is optimized at a temperature 72 degrees centigrade. And at the same temperature, the quality factor also optimized. Can you go to the next slide? Coming to the temperature shift, the top left side diagram shows the variation of the temperature shift, and the right side diagram shows the measured temperature shift coefficient, which is corrected for the light shift, and which is optimized for laser intensity for the magnitude of 10 to 13 watt per meter square. And the bottom figure shows the measured clock frequency stability up to averaging time of 100 seconds, which is on par with onboard clocks. And the major application is these developer clocks will be employed in the upcoming Magic satellites, which will provide the position accuracy better than 10 meter on ground. Currently, we are using onboard clocks from external agency, which are very costly. So the development of these clocks will become independent of the external agency, and we can improve the performance over time. Thank you.
Raful, can you start?
Yeah, thank you. Okay, so you're using a CPT resonance and trying to see what is its systematic shift as a function of temperature. So what is the line width that you get in this experiment?
Sir, we get a few hundreds of heads, sir. The best we could get is 300 heads, sir.
Okay, now you have not talked about shift of the resonance line with magnetic field. So why is it so?
Sir, here we fix the magnetic
Residual
field.
magnetic field. Yeah,
Residual,
tell me.
sir, this magnetic field will have two components. One is linear and quadratic component. The linear component we will eliminate by using the fixed magnetic field by controlling it. And the quadratic component variation will be there, but that is very much less, which will be well within the noise level of our required stability.
And what's the origin of the frequency shift because of temperature? What is the physical origin of that?
Yes, sir. This is basically due to the interaction between the buffer gas and alkali atoms, sir. And basically, it is because of two effects. One is attractive van der Waals forces and repulsive Pauli exclusion forces, which depends on the size of the atoms. For example, for
No, that's fine. That's fine. But this should be a symmetric effect. It should broaden the line. Why should it shift? See, these are symmetric effects, right? In frequency, why should it shift in one direction?
Yes, sir. For example, if you use neon, where low level atom, there the Pauli exclusion forces are the dominant, so you will get the positive shift. If you take the heavier atoms, there the van der Waals forces are dominant, there you will get the negative shift. So if you take the combination of lower and heavy atoms like argon and nitrogen, there you will get positive and negative both, and both will be compensated, and you will get
No,
the.
in this case, you have rubidium and neon, right?
Here we have rubidium and neon, sir. This is basically because of the neon
In this
interaction.
case, what's the physics? In this case, what's the physics that the line should shift and not just symmetrically broaden because of collisions?
Yeah, because of collisions only. Mainly here, the Pauli exclusion forces are the dominant, so it is giving the positive shift, sir. So here we can measure a systematic effect, and we have to compensate for the clock application. Here we cannot make it zero.
Okay, why can't you just reduce the pressure to reduce the collisional effects?
Yes, sir. We can study the pressure effect on the shift also. That our future experiments, that is what activity we have taken, and we are conducting by taking different pressures, and we are trying with different buffer gas also. And finally, our aim goal is for which pressure and which buffer gas we will get the optimum frequency shift.
Okay, fine. Thank you. Over to you, Dr. Pradhan.
Yeah, to continue with that earlier question, actually, if we will reduce the buffer gas pressure, then what will happen to width? It will not change? Width of the resonance?
So shift will decrease, sir.
Okay, so where you are using buffer gas basically in your cell?
So yeah, basically to increase the laser atom interaction time, sir.
So
interaction time, sir. So because of the diffusion by using these buffer gases, we can increase the interaction time between the laser and atoms.
Can you use some other kind of cell for doing the same thing? Means not buffer gas, but by coating, by using anti-relaxation coated cell?
Yes, sir. Wall coating cells also we can use, sir.
So is there any advantage of using buffer gas cell over anti-relaxation coated cell?
Sir, as well know, this wall coating over time it will have the like aging drift, sir. Aging effect will be there, that wall coating, but whereas we will not observe that in case of buffer gases.
Okay, thank you.
Dr. Pradhan, if you allow me, I just had
Yeah,
one quick
yeah,
question.
yeah.
So Rajaya, you mentioned about increasing the interaction time with the laser. What if I just increase the laser beam size to the size of the cell? Always the atoms are always in the laser.
Yes, sir.
So what?
Yes, sir. Even that time, the interaction time will be more, and more number of atoms will interact with the more photons, and that time also we'll get the high contrast and good quality signal we will get, sir. That is also one other way of increasing the CPT resonance
Yeah,
characteristics.
but there will be a problem, right? Because the intensity profile is not uniform. The atom is going to trace different intensity locations all the time.
Yes, sir. It will have some impact that we need to study systematically. Yeah, exactly what happened.
Okay.
Yes, sir.
Okay, fine. Thank you.
Thank you, sir.
I'm done.
Our next speaker is Vivek Singh, poster number CP0404. Vivek, can you hear us?
Yeah, yes. Am I
Please.
audible, sir?
Yes, yes, you are audible. Please begin.
Shall I start? Yeah.
Yes, please start.
Please go ahead.
Yeah. Good afternoon, sir. I am going to present my work on this magnetic micro trapping of laser cooled atoms using gold ZR on atom chip. Basically, the atom chips are very important to play the critical role for the development of future atom optical devices. And this work is on the micro trapping of the laser cooled atoms on gold Z wire. And this is the schematic of our setup, where the chip is there, and the copper wire is used to trap the cold atoms to produce the cold atoms. And for the magnetic trapping, first we have to cool the cold atoms, then we have to transfer these cold atoms in the magnetic trap. And can you go to the next slide? This is the timing sequence, and this is a real experimental setup where you can see all the pumps which are used to create the ultra high vacuums. And this is a science chamber where all the experiments is going on. And this is the first 20-second takes to produce the cold atoms, and then we transfer these cold atoms to near to the chip surface by changing the current in coils and UR and the meanwhile, because we are transferring near the chip, the temperature gets increased, so we have to manage the temperature, and simultaneously we have to change the frequency of cooling laser beam so that we can change the temperature also. And in the meanwhile, we have changed the frequency around minus 70 megahertz, and in the mean we got the temperature in the mod stage itself is around 75 microkelvin. And can you go to next slide? Once the atoms are transferred to near to the chip surface, then we switch on this magnetic micro trap by switching on the gold Z wire current and the Y bias field. And the combination of these two basically creates the IFE Pritchard kind of trap, and in which we transfer our cold atoms in that trap. Can you go to next slide? This is a basically simulation for 2 ampere current in gold Z wire and for 9 Gauss. In Z direction, the trap is like this, and in XY plane is like this. And we actually measure the lifetime, and the lifetime is without using the mechanical setter. That's why the lifetime is little bit less. We are expecting the lifetime is around 2 seconds, and this exponential is fitting by 2 exponent, and first is very fast, and we believe that this loss at the beginning of the trap formation, because there is a mismatch in the mod center and the magnetic trap center. That's why the loss occurs. And second loss is to the collision from the trapped atoms with the untrapped background atoms, and we are working on this to increase the lifetime of the trap, and we actually trap around 1 into 10 power 6 atoms in the magnetic trap of gold Z wires, and we are trying to improve these things right now. That's it. That is the thing we want to report this.
Yeah.
So can I start? Okay.
Yeah, please.
So you have shown two time scale, right?
Yeah.
Vivek.
Yes, sir.
Yeah. Why do you say that the one time scale is because of mod mismatch and the other one is because of basically your collisional loss? I can also equally argue that the first one is because of collisional, and the other one the other one is because of old rubidium collision.
No, sir, because when the trap is formed, the position of trap is around 500 micron from the surface, and our G mod is around 1.2 micron. There is a mismatch in the position. Because of that, when the trap is switched on, the atoms are trying to move. Some atoms are going to the trap, some atoms are at the same time going outside of the trap due to the mismatch and on the higher velocity of atoms. The atoms which are having more higher temperature, they will get ejected from the trap. This process will be very fast.
But at the initial point, whatever you have, these atoms are already trapped. Na?
Yes, sir.
No, these atoms, they are already trapped, right? The
Yeah,
initial
already.
point, if you'll see.
Yeah, this is initially it is dropped. Yes.
Have you tried to repeat this experiment with a different?
Hello. Actually, your voice is not coming, sir.
Hello.
Yes, sir. Your voice.
Can you listen me? Hear me?
Yeah. Yes, sir.
Have you tried repeating this experiment with a different number of atoms?
Right now, we are trying to do with mechanical setters, and sometimes actually this is around when the trap is switched on, we just image the atoms, and after some times it just gets thermalized. Some kind of thermalization is going on when the trap settles down. Then actually we have repeated this experiment and we have found that it is fitting. Actually, best fit we are getting with double exponential only.
Okay, Dr. Raful, you can.
Yeah, so I have a couple of questions. So first is this 65 milliseconds time period seems to be very small, the lifetime, to be
Yes,
useful
sir.
for doing anything. Now, the reasons that you have quoted, that you have specified, I kind of don't understand completely. One of them is you're saying background collisions with the background gas. What is your background pressure?
Right now we are working to 3 into 10 power minus 10 torque vacuum, sir.
Okay, so that still doesn't explain why it should be 65 milliseconds. Now,
Actually,
which
we are also
hyperfine
not
level are you? Huh?
we are also not using this data is taken without using the mechanical shutter, sir.
Well, I mean, then you cannot you cannot say that this is the lifetime then.
Yes, sir.
Because then there will be
we
light,
have not.
then there will be resonant light absorption and losses of atoms,
Yes,
which is a
some leakage from
completely
the
unavoidable system, unavoidable
yes.
situation. Okay, I think you should probably report lifetime with taking care of all the background light. Okay, and the second thing is which hyperfine level are you pumping the atoms into before trapping them into the magnetic trap?
MF equal to +2, sir.
F equal to
MF equal to F equal to 2, MF equal to +2.
okay, so you should also ensure that, so if you see in literature, in one of the F levels, either 1 or 2, the light assisted collisions, three body collisions are very large. Anyway, you have not reached that stage because you are still limited by other factors, not even vacuum. So I think those probably are the reasons. Okay, fine.
Well, we are expecting that we should get lifetime more than 2 seconds, 2 to 3 seconds. We will get actually I think.
Even more, it should be like 10 seconds or so. Okay,
yes, sir.
fine. Thank you. Good work.
Thank you, sir.
Our next presenter is Hriday Dutt, poster number CP0406. Hriday, can you hear us?
Yes, I can hear.
Okay, please begin.
Good afternoon, everybody. Myself, Hriday Dutt from ISRO Inertial Systems Unit. Today, I'll be presenting on our work in implementation of magneto-optical trap in compact titanium UHV chamber. Next slide, please. The cold atom interferometry actually exploits the wave property of matter to make a measurement of inertial forces to a high accuracy. It can measure the acceleration, gravity, rotation in the similar manner. In our laboratory setup, the equipments are quite bulky, and the associated engineering technology we have been mastering. For a field application, this has to be realized into a compact, ruggedized model to test the inertial sensing in different environments. In IISU, we have two laboratory setups, one cold atom lab setup and a transportable setup, which we have been working on to develop into a mobile gravimeter. Next slide, please. Next slide. Okay. The image shows the compact titanium vacuum chamber of background pressure 5 into minus 10 millibars. It is made of titanium and occupy a volume of 2.2 liters with attached SIP and jetter pumps. The viewports are designed to have orthogonal alignment, and the collimators are 6 collimators are attached to it to form the cooling axis. We have attached an infrared CCD camera to capture the cloud images after trapping them. Anti-Helmholtz coil has also been integrated into the UHV chamber system that generates a quadruple magnetic field of field gradient 12 gauss per centimeter. Optical circuit have been miniaturized, have been designed to giving the paramount importance to miniaturize the system of cooling beam and repumping beam generation. It takes an area of 60 centimeter cross 40 centimeters. We are using laser sources of ECDL, Toptica DL Pro and Booster Pro lasers that have been locked to the required hyperfine transition of rubidium 87. And the entire apparatus is sitting on a vibration isolation platform to eliminate any kind of vibrations. Next slide, please. We have first we attempted and successfully stabilized a cold atom cloud with a magneto-optical trap. It was the cloud was stable, and the parameters such as the rubidium dispenser current and the mode coil current have been characterized to maximize the number of atoms in the cloud. The cloud is freely allowed to expand, and the spread of the cloud has been analyzed to measure the temperature. We have characterized the cloud, and we have found that it is close to 1 billion atoms that has been cooled to 100 microkelvin temperatures, and it has crossed the Doppler limit and further polarization gradient cooling will definitely bring down the temperature even lower. We are presently in the process of implementing the polarization gradient cooling to bring down the temperature. Thank you.
Dr. Rahul.
Yeah, sure. Thanks. So, Ruday, nice work. So, I would like to know a couple of things. One is, what is the density of your atoms in this setup that you have achieved?
Sir, the size of the cloud is of having a diameter of 0.5 to 0.6 millimeters, the diameter. And it has a 1.2 billion atoms.
Are you sure that the diameter sounds very small for that number of atoms?
Sir, the mode coils we have.
No. Did this size is in the MOT? You imaged it in the MOT, or is it after some time of flight, or what is it? This image that you have shown.
The value that I said is immediately after mode, sir. Freely
0.6 millimeters.
0.5 to 0.6 millimeters. Sir.
Okay, fine. And what kind? So how are you going to start the interferometry setup with these cold atoms? Are you going to do some velocity filtering or what?
Presently, we are implementing the polarization gradient cooling, sir. After achieving sufficiently lower temperatures, we are planning to do velocity selection.
How are you planning to do the velocity selection?
With the blow away, sir. Raman
blow away.
Sir?
Yeah, how? Can you repeat?
Sir, with the Raman beams, we can transfer the atoms from in between F equal to 1 and F equal to 2 stages. Then we can blow away the remaining atoms in one of each stages. We are preparing blow away beams to blow away atoms from F equal to 1 state and 2 state.
So finally, how many atoms will be left for the interferometry?
10 raised to 5 atoms, sir, after the selection, velocity selection. And
Okay.
then we are planning to go ahead towards interferometry.
And these lasers are commercial lasers or indigenously developed?
No, sir, the commercially available lasers, sir. Top-tier laser.
Okay, fine. Fine, thank you.
Thank you, sir.
Dr.
So
Pradhan.
why you are using the titanium chamber?
I'm sorry, sir?
Why you have selected titanium?
So the material has the non-magnetic properties, and after switching off the mode coil, the residual magnetic fields present inside the chamber can actually adversely affect the stability of the cloud. By choosing the material as titanium, we can eliminate the residual magnetic fields present inside the chamber where the cloud actually forms.
Yeah, but you could have chosen a simple glass cell also.
Sir, the stability of the chamber and the mobile, the transportable nature of the chamber, that is what we are given the importance, sir. So the manufacturing of chamber into small transportable model with the volume of 2.2 liters, sir, that was planned and implemented.
Okay, thank you.
Our next presenter is Kavish Bharadwaj, poster number CP0407. Kavish, please begin. Kavish, please begin. Kavish, are you there? Kavish, are you there? Are you there? Please unmute yourself. Unmute. Please unmute. We can't hear you.
Either increase the volume of the mic or unmute the mic.
We can't hear you. Please unmute or increase the volume.
We can't hear you at all.
I think he has some problem.
Kavish, you please resolve the problem. We will move to the next presenter. Our next presenter is Chandan Ghorui, poster number CP0408.
Am I audible?
Yes, you are audible. Please begin.
Good afternoon, everyone. First of all, we are grateful to the organizing committee giving me the opportunity to present of our work. And the title of I am Chandan Ghori from University of Hyderabad. The title of this work is Efficient Second Harmonic and Terahertz generation from the BIBO crystal using the ultrashort laser pulses. Next slide. The objective of this work is next slide. Hello. Next slide. The objective of this work is we are getting here 50% second harmonic efficiency using a femtosecond laser with a repetition rate is 1 kilohertz and the pulse width is 50 femtosecond. While the obtained the terahertz generation efficiency is 1.85 into 10 to the minus 5 percentage. 5%. First, give a small introduction about this crystal. This is the BIBO biaxial crystal, which belongs to the monoclinic and C2 group, and it is high damage threshold voltage. This is the biggest transparency range, 160 nanometer to 2.7 micron region. It has highly nonlinear coefficient. 3.5 to 4 times higher than the LBO crystal and 1.5 into 2 times higher than the BBO crystal. The de-effective value of this BIBO crystal is 3.2 picometer per volt. Here we employed two type of laser. One is the femtosecond amplifier, another is the femtosecond oscillator. Next slide. These are the first we recorded the terahertz efficiency using the femtosecond amplifier. Here we use the 800 nanometer wavelength TI-sapphire laser with a pulse with 50 femtosecond, and the repetition rate is 1 kilohertz. Then we recorded the terahertz efficiency with these are the incident power, and figure 3a shows the we get two type of intensity peak. One is the fundamental is 800 nanometer, another is the 400 nanometer, and for this 800 nanometer we get the incident power is 120 milliwatt, and the output power is the 40.8 nanowatt. And for case of 400 nanometer we get the output power is 20.8 nanowatt. And second we are using the femtosecond oscillator laser with a repetition rate is 140 femtosecond and pulse width is with a repetition rate is 140 and pulse width is 140 femtosecond, and repetition rate is 80 megahertz and pulse width is 140 femtosecond. Then we have recorded the time domain and frequency domain signal. These are the time domain and frequency domain signal. Using this is time domain and frequency domain signal, we are extract the refractive index and absorption coefficient. This is the first time we have to recorded the refractive index and absorption coefficient of this crystal, and this is the first time we are getting the 50% efficiency of this crystal. Next slide. We have successfully demonstrated that this is a type 1 with the crystal cut is 28.9 degree bismuth triboroid crystal from UV to terahertz generation using femtosecond laser. Conversion efficiency is quite high, 50% obtain the terahertz generation. Later we have to extract the refractive index and absorption coefficient in terahertz domain. Apart from this work, we have calculated phase matching angle, second harmonic efficiency using the NDA laser with a repetition rate is 10 hertz from Bardhaman University Laser Physics Lab.
Time
Thank
is
you
up.
for your kind attention.
Dr. Pradhan?
Yeah, I was just talking to Dr. Chakera. Now, sir, can you hear us?
I'm able to hear. Okay.
Sir, okay. Now it is okay, right? Yeah.
Okay, just I'll begin. Hello.
Hello.
Yeah. So my question is why your terahertz power is decreasing with laser power?
Why laser power, terahertz power is decreasing? Okay, so the next slide.
I had the same doubt, Dr. Chakera. Yeah. Okay.
No, sir. Third slide. Yes, sir.
Yeah, this one.
This one. Here we measure the terahertz efficiency with incident terahertz power, laser power, sir.
Yeah. Yeah. So normally you should have higher efficiency when you go for higher power, isn't it?
Yes, sir.
So why it is decreasing?
It is decreasing because if the crystal is not properly mismatched, there because for this femtosecond laser we need the group velocity dispersion is very less, and crystal thickness is 1.29 in millimeter for this crystal, so that's why it's decreasing.
Is it correct? Okay, you can go ahead now. Yeah, I'm done.
Yeah. Dr. Pradhan.
Yeah, I don't have any specific question.
Our next presenter is Kannan S, poster number CP0409.
Hello, madam. Am I audible?
Yes, you are audible.
So, good afternoon, everyone. So, I'm Kannan. I'm from ISRO Initial Systems Unit, Trivandrum. So, our work is on manifestation of Janus-based nature of quantum states in energy density. Can you please move to the next slide? The manifestation of squeezing, one of the non-classicality, was discussed in our recent work. So it was shown that all quantum wave packets with no squeezing shows positive energy density. Energy density here we have defined in terms of Einstein stress energy tensor. And we know that the classical matter will always have a non-negative energy density. But this may not be the case for any general quantum state. So in this work, we show how the Janus phase properties of well-known quantum partner states are mirrored in the energy density plot. As an example, we have taken even cat state and squeezed vacuum state as one partner state, and odd cat state and squeezed excited state as the next one. Next slide, please. So as I have mentioned, we used the Einstein stress energy tensor T for a single mode excitation, and we take the normal ordered expectation value of this one to measure the energy density. So for the even cat state, it comes out to be negative as expected, because we know even cat state is a quadrature squeezed state, and it can show negative values for certain values of theta. And similarly, when we plot the energy density for its Janus phased partner state, that is squeezed vacuum state, we can clearly see the contrasting nature between these two. That is shown in the right side figure. Next slide, please. So in short, we have analyzed the squeezing properties and the Janus phase properties of these quantum states in the energy density. A similar work was already done in in optical tomograms, the reflection of Janus-based characteristics of quantum states in the optical tomogram. And here we have shown that the properties of the quantum state, maybe the quasi-probability distribution, also can be derived from the energy density. And it can be a simple tool for visualizing non-classical effects, and also serve as an easier way to visualize the changes that happen in the non-classicality during various decoherence processes. And currently we have only studied for single mode state, and similarly multi-mode states can also be done, and deformed states also can be carried out. Thank you.
Can you please specify some of your application of your work?
In quantum optics, basically when we study decoherence process in open quantum systems, if we want to see how the non-classicality of the state changes, this energy density can serve as an easier tool. Similarly, there is no specific criteria which says, like, experimentally we cannot get any, even Wigner function fails when we check the non-classicality, especially squeezing. Wigner function is positive for squeeze states. But our measure, this energy density, will always show negative for squeeze state. And similarly, theoretically, there are many possibilities, like when we measure the Casimir force and stuff like that for quantum state, we can clearly visualize this.
Okay, Dr. Raful, have you any question?
Yeah, I have two questions. Okay,
Yes, sir.
first question is what is the meaning of Janus phased nature?
So the contrasting nature, like, can you go to that slide number 3, please? The previous slide. Sir, in the energy density plot, you can see how where the minima and maxima occurs in these two. So similarly, when you consider squeezed vacuum and even cat state, squeezed vacuum is a quadrature squeeze state. Even cat state also shows quadrature squeezing, but the position at which, the angle theta at which they show squeezing is out of order by pi. So similarly, such states which shows contrasting natures are called Janus phase state.
Okay, and the second question is just rephrasing what Dr. Pradhan asked. That is, where is the applicability of this work for the organization where you come from? I mean, well, you need not tell me if it is not to be told, but yeah.
This was done out of interest. I am working at the cold atom laboratory in IASU as of now. So
okay.
In there we are doing some contact optics experiment, and currently I am trying to relate in such a manner. So may not be a clear answer, but
okay.
This is a theoretical
Fine.
work. But in open quantum systems and always, especially when there is decoherence, I can use we can use these properties of it.
Okay, fine. Thank you.
Thank you.
Chakera sir.
Okay.
Our next presenter is Ajmal Ansari, poster number CP0501.
Hello.
Yes, please begin. Ajmal,
Hello.
please.
Good afternoon. Yes, yes. Hello. Good afternoon, everyone. My presentation title is we have done the experimental study on self-compression of intense ultra-short laser pulse propagating in oxygen gas sheath. So why we have need of this shorter laser pulse? Basically, we are talking about the short laser pulse duration smaller than the 10 femtoseconds. So this is for the purpose of related to the generation of higher order harmonics and its diagnosis. Uh, so what will be the method of compression of laser pulse? So there are typical method of compression of laser pulse is first you have to increase the bandwidth of the laser pulse and via like self phase modulation, uh, and then compressed it via some dispersion compensation techniques like grating, pair and sharp mirrors. So this is the typical method, but there is alternative methods for cell compressions, like ionization induced spatio-temporal coupling, and in this method there is no need of subsequent dispersion compensation. This is direct compression. So, and this method it works at high high ionizing intensities in the range of 15 to 15 to 17 watt per centimeter square, because in this range the Kerr non-linearity is diminished because the ionization is very high. That's so uh, non-linearity will be diminished or very less, and since the intensity is not so much, that relativistic non-linearity will be there. Okay, next slide, please. We have carried out an experiment to study this. This is the schematic of the experimental setup, and above is the laser and medium interaction region is shown in above figure. We have used a titanium sapphire pulse amplifier at 100 nanometer center wavelength with pulse duration, initial pulse duration 55 femtosecond and energy of 5.2 millijoule at a 1 kilohertz repetition rate. We have used a focusing optics L1, which has a focal length of 540 millimeter, and it is collimated by another lens of 650 focal length to diagnose it. And we have used a target oxygen gas sheet, which has around abdolochin width of 2.5 mm. We have used to diagnose the output laser pulse. We have used a bonsai autocorrelator, and we have measured the spectrum by optical fiber spectrometer. Okay, next slide. And this is the outcome of the experiment. This is the results of the experiment. We can see that with increasing the pressure in the gas sheath, we can see that pulse first start to increase, pulse duration start to increase first, and then it start to decrease after some pressure. After some pressure, and it will remain at that compression. And if we see that its intensity.
Time is over.
Okay, so hello.
Dr. Rapol, shall I start or you?
Okay, I'll go ahead.
Mr. Ajmal, why you have chosen oxygen gas sheet? Is there any
Basically, we have used oxygen as a because the gas medium, the selection of gas mediums depend upon the what will be the intensity you are using. So oxygen has a IP, the ionization potential around the argon, and it has a high. And if we want to see if there is some connection with the non-linear Kerr index, if there is some relation, then it also has a very high non-linear Kerr index, and also the ionization potential is around the argon atom. So so we have selected the oxygen to test it, and since there is no non-linear refractive index, effective non-linear refractive index is not present here, and this is due to the only spatio-temporal reshaping of the laser pulse in the interaction with the oxygen gas sheet.
So if you have a basically for depending upon your gas, available laser peak intensity, you are choosing the gas, right?
Yes, yes. So if we because it should have the laser intensity should have some intensity which is in the ionization regime of that gas atom, that gas material.
Okay, so for example, if I have a lower, I don't have that kind of a high power, and similar kind of study, what kind of gas I have to use?
If you have a very high intensity, you mean? Huh?
If
Hello?
I don't have kind of high intensity power.
Okay. Yes. Then I didn't think you can go, you can have such a process can be there, because if you don't have an ionizing intensity, then it should only go defocusing. Its intensity will be only reduced, and but its impulse duration will not be decreased. I don't think, because I have simulated and these results, and we have experimentally confirmed.
Dr. Rasul.
Dr. Satyara, please go ahead. I'll ask later.
What will happen if you increase the density of your gas sheet?
If we increase the gas density,
yeah.
Okay. You mean just increasing from initial to just increasing?
Yeah.
From 0 to just increasing.
Yeah.
Suppose first we this process will depend upon the relation of laser intensity and the gas pressure. Suppose you have fixed the laser intensity and then you are increasing the gas pressure. Then first at the lowest pressure, and there is simple just defocusing nature of the laser pulse, and this is decrease. But the in laser pulse duration is not change so much, but is and adversely it will increase. It will increase because due to defocusing, its peak intensity goes down. But as you increase much pressure, and there is some relation with the pressure and the intensity. If you are increase, then much higher than the pressure, then the laser intensity will be decreased so much. But at the same time, due to the spatiotemporal coupling, its pulse duration will go down. This is the process.
So ultimately, you are going to use this beam for some application, isn't it? After compression.
Yes.
So
Yes.
up to how much energy you can work here? Like suppose I want like 100 terawatt. Can I compress that pulse and get the 100 terawatt still?
You mean 100 terawatt? So
yeah, means pulse energy is higher in that. Okay.
Pulse energy is higher initially. Yeah. Pulse energy is higher. Yeah. Basically, if the pulse energy is very high, then you are basically increasing this laser intensity regime. Okay. Then if you are increasing this laser intensity regime, then
no, but always make it in a required regime of intensity, because you focus it. So it depends on your how tight you are focusing it, isn't it?
How tight you are focusing it?
See, whatever intensity regime is required for your this compression, that you can always bring to that intensity regime, isn't it? Even though the pulse energy is very high.
Yes. Pulse energy is very high. Then this process will be also be there, but it will depend upon the what will be the pressure it is interacting, and what will be the nature of gas medium, nature of material atom.
Okay, what is the typical transmission of the pulse energy through this gas jet?
So pulse energy is typically around 80% or 80 to 90%, but the effective region where the pulse is compression is there, the pulse energy is lower. So almost 20 to 30%.
Okay, Dr. Pradhan, I am done.
Okay.
Okay, so I have one question about the mechanism that is involved in shortening the pulse when it interacts with the gas. How does it happen?
Yes. So the mechanism is simple. First, as the laser pulse interact with the gas medium, there is two simultaneous processes. First, as the laser pulse interact, it's due to self-phase modulation, its bandwidth will get increase. But after, as the pressure will be much increased, as the pressure is increased after to certain optimum pressure, then there is always spatial temporal reshaping of the pulse. So as the pressure is so much that the spatial temporal reshaping will mediate the negative charge to the pulse, then the pulse compression will happen.
Okay, fine. Thank you.
Okay, welcome, sir.
Our next
Thank you.
presenter is Tirtha Mandal, poster number CP0502.
Yes,
Tirtha,
ma'am.
please begin.
Am I audible?
Yes, you are audible.
Am I audible? Okay. So, good afternoon, everybody. The title of my work is Demonstration of Superconductive Acceleration from Oscillation of Fast Electrons in Ultra-Short High-Intensity Laser Ball Interaction. So, basically, when the ultra-short lasers are focused into micrometer size, can you please go to the next slide? Next slide, please. Hello. Yeah. So when ultra-intense lasers are focused to a micrometer spot size, the laser peak intensity reaches relativistics. And when the intensity becomes very, very high, greater than 10 to the power 19 watt per centimeter square, J cross B heating mechanism becomes the dominant one. Here, due to the V cross B force, the electrons oscillating in the laser electric field get a forward accelerations. And this generates energetic fast electrons having energy from keV to MeV range. Now, this is a very highly active research topic. Generally, the temperature of the fast electron is decided by the conductive scaling, which is basically square root of the intensity. However, we have shown that by changing the pre-plasma scale length, the temperature of the fast electrons could be less than the conductive scaling as well as more than that conductive scaling. That we call this superconductive acceleration. So next slide, please. Next slide, please. Next slide, please.
This is your last slide, right?
Yeah, it is last slide.
So,
it is third slide.
so yeah, actually, can you go to previous slide? I could not hear. Maybe there's some problem in the connection. Previous slide, sir. So yeah, so the laser we used 150 terawatt SFI laser systems, and when we focus the laser systems, generates copious amount of MeV fast electrons, and by changing the pre-plasma scale length, we could change the energy of the fast electrons. So I'll go to the last slide. Last slide, sir. Yeah. So here we have seen that when the scale length is very, very less, of the order of a few micrometer, we get the temperature below the conductive scaling. But when the scale length was increased by using a lesser contrast lasers as well as a picosecond pulse, the temperature of the fast electrons goes beyond the conductive scaling. And we have also found out the reason for such obtaining such lower temperature. The reason basically for the lower temperature is electron transverse distance is greater than the laser skin depth in overdense plasma. Therefore, this is the reason for lower temperature. And for higher temperature, there are other acceleration mechanisms operating, such as stochastic heating, which is helping to accelerate the fast electrons to beyond MeV energy in a longer density scale. So, yeah. So, okay.
Hello.
Yes, sir.
Okay. So, which plot you're showing your superconductive acceleration?
So here in the third slide, in this slide, we could see that when the scale length was increased to tens of micrometer by using a picosecond pulse, we could see that the temperature is going beyond the conductive temperature, because this is the line is notifying the conductive temperature for the used intensity, and we have obtained these temperatures which are beyond this temperature. So because reason is the acceleration mechanism is changing from J cross B heating to stochastic heating. And further, in the longer pre-plasma, the laser is also getting absorbed more, as well as the laser self-focusing is also occurring. These are the two reasons which is giving this conductive acceleration, superconductive acceleration.
So this you have plotted for different intensity of laser light.
For different people's delay. Actually, in each delay is giving a different pre-plasma scale length. So this is first electron temperature versus scale length of the interaction.
Okay, thank you.
I have one question. See, what target you are using for this?
We are using a copper 7 micrometer target.
Okay. So the pre-plasma formation depends on the target Z also. Okay. So have you seen that if you go for a low Z target, the same effect is observed there also?
Yes, sir. In our previous experiments, when we used two metallic target as well as low jet target, as you have said, the CH targets, and for CH targets, we have obtained a slightly longer scale length, as we also obtained from the helios.
No. There the pre-plasma scale length would be small because it will be transparent for that pre-pulse. If you use a dielectric material like low Z, non-metallic, okay? Are you able to hear me? Tirtha?
Tirtha, are you there?
Tirtha, can you hear me? I think connection is lost.
So
I think Tirtha's connection is lost. We will move on to the next presenter. Our next presenter is Mohammad Tayyab, poster number CP0503.
Yes, ma'am.
Yes, please begin.
Am I audible?
Yes, you please begin.
Yes, thank you. So this work is about proton acceleration from thin file targets. So what is basically going on here? This is basically a new acceleration technique where a high intensity laser pulse is used to accelerate ions. So in this experiment, so this is our experimental setup. So to save time, I will directly go to my work and try to explain the process here itself. So we have a 150 terawatt laser system. The laser pulse from 150 terawatt system is focused using an off-axis parabolic mirror onto the file target. So, as explained by my colleague Trith Mandal, so the laser energy gets absorbed into the plasma, and high energy electrons are generated. These high energy electrons will leave the target. So, at target back surface, there is a creation of the sheath field. So, this sheath field is very strong, and it can ionize and accelerate the atoms present at the target rear surface. So we are detecting these ions using Thomson parabola ion spectrometer and radiochromatic film. So there are different laser and there are many laser and target parameter which can affect this ion acceleration process. So in this work, we have used transparent mylar target, which was one side coated with high-Z gold atom. So we have also collected the transmitted laser signal and monitored spectrum and also temporal profile. So next slide, please. Next slide, please. So this is the signal recorded from the spectrometer. So in case A, where there is only 5 mylar target, which was 5 micrometer thickness. So this is the ion signal, case A. And for case B, this is the case where there is a coating at the target front surface, and this is the case C when the coating at the target rear surface. So you can see that for when the target coating is at the target front surface, there is enhancement in ion signal, whereas when the coating is at target rear surface, there is a drastic reduction in the ion signal. These are the RCF profiles. So we have also measured that for transparent target, there was a leakage. So some part of the laser energy get transmitted to the target. However, when there is a coating, there was no transmission at all. Next slide, please. So the result can be explained by following. So when we have a only transparent mylar target, so since it is a dielectric and transparent, so at the early part of the laser pulse get transmitted through it. Whereas when there is a coating at the front surface, the pre-pulse it get absorbed into this coating, and there is a more absorption of the main laser pulse. So there was enhancement in the ion signal. Whereas when there is a plasma at the target back surface, so it drastically reduces the sheath fields, hence there is a reduction in the ion signal. Similarly, we have used the opaque target. Just 1 minute. Similarly, when there is an opaque target, so it does not show any effect of the coating. So our result is also explained by PIC simulations. Thank you. Yes.
Dr. Pradhan, you ask.
Yeah. So anyway, your best result is obtained with your gold coating in the front layer, right?
For this experiment, yes.
Yeah. So then, what is the role of mylar there?
Mylar is basically, since this acceleration relies on the for simple target, this acceleration relies on the hydrocarbon contaminants which are present on the any surface, whether it is ammonium or any target. But mylar being rich in hydrogen, that's why we have used it just to enhance the signal, and at the front side it is coated with high Z for higher absorption.
Okay, and what is the coating size you use?
It was around 30 to 40 nanometer.
And okay. Yeah, I am done.
I don't have any questions. Please go ahead.
Tayyab.
Yes, sir.
Yeah, just the question Dr. Pradhan was asking, why you chosen the mylar transparent target?
Yes, this mylar is rich in hydrogen. So it is expected that there will be some enhancement in the proton signal.
No, apart from that, you want that people should transmit also, isn't it?
Yes.
So
Transparent and yes, transparent and rich in hydrogen. Yes.
So you want to see the people's effect, okay?
Yes.
Yeah.
Yes.
Okay. Did you try any other coating? Why gold only?
Earlier aluminum coating. I also used aluminum coating, and it was showing similar effect.
So then why to go for gold if it is saying
gold? Since it is high Z, more high Z. So since collisional absorption is, since ASC is basically long pulse, so collisional absorption is expected to high in high Z target.
No, but you said that aluminum is also showing the same result.
Yes, but it has to compare. It has to compare on equal footing. And on the same experiment, I have to use gold and aluminum.
So then, what was the comparison?
For this experiment, it was earlier experiment. For this experiment, so the only gold was there. So it was for different laser parameter. It's not 10 terawatt laser systems. Not
okay. So there is no comparison under similar.
Right.
Okay. That's what from my side. Okay.
Our next presenter is Pinky Kumari, poster number CP0504. Pinky, please begin. Pinky, can you hear us? Pinky, you are not audible.
Hello.
Yes, now you're audible. Please begin.
Good afternoon to all of you. Today's my topic is effect of carrier heating on amplification characteristics of Brolin scattered stop mode in third or fifth and second, sixth semiconductor magnetoplasmas. Next slide, please. Now I want to introduce about my topic. Brownian amplification is a non-linear wave mixing phenomena where a low frequency mode induces an inelastic scattering of higher frequency pump wave in a non-linear optical medium. In this process, another signal with surplus energy resonantly passed to the vibrational state of the medium is produced. In this present paper, we develop a theoretical model to analyze the effect of carrier heating induced by an intense pump wave on the parameter character Brownian amplification in third, fifth, and second, sixth semiconductor magnetoplasmas. Under high power pump irradiation, this investigation became more important as it leads to better understanding to the Brownian amplification process. Next slide, please. Hello. In this, we obtain some theoretical formulations. In a Brownian medium, SBS occurs due to non-linear interaction among three coherent fields. These fields are an intense pump field, an induced aquistial vibrational mode, and scattered stock component of pump field. These three fields are connected with energy and momentum phase. Next slide, please. In this, we obtain different results. Next, please. Next slide, please. Hello. Next slide, please. Hello. Now I want to discuss my results. In order to perform numerical calculation, we consider three different semiconductor magnetoplasma, that is INSB, GAS, and CDS. These are the material parameters are given in reference second and third. And here we representing different crows for these semiconductor material. Blue crow represent INSB, red crows represent GAS, or black crow represents CDS. At last slide, please. From these graph, we draw different conclusion. When effect of carrier heating are included, the feature remain unchanged. The peak of the curve, which was occurring at B0 3.5 T and 10.8 T. The peak of the curve now occurring at B0 2.5 T and 9.4 T has been further enhanced. The range of B0 at which peak of the curve occurs except B0 14.2 T has been widened. Next slide, please. Thanking you. Hello.
Yeah.
Hello.
Okay, Dr. Rafal, you want to start?
No, you go ahead, please.
Okay, so okay, you have studied basically carrier heating effect, right?
Ji, sir.
So in which configuration you get the best result out of the three sample you have tried? And are they basically means they are readily available, those kind of sample, or it is just for theoretical calculation you have carried out?
Theoretical calculation. From the theoretical.
Okay, I have done.
Venki, where you find this application of your work?
Sir, repeat, please.
No,
Question repeat.
Yeah, where can you find application of your work?
Sir, I am not listening here properly.
Can you hear me now?
Yeah.
Yeah, so you've done some work, isn't it? So where do you find the application of your work?
Sir, I cannot understand question.
Yeah, question is where is the application of your work? Hello. Yeah, maybe.
We move on. Judges, shall we move on to the next presenter?
Yeah, please.
Our next presenter is Gopal Saini, poster number CP0506. Gopal, please begin. Can you hear us? Gopal, can you hear us?
Hello, am I audible?
Yes, yes, please begin.
Yeah. Good afternoon. I am Gopal, research scholar at Department of Physics, Lord's University, Alwar. The topic of my presentation is enhancement of real and imaginary parts of Raman susceptibility of semiconductor magnetoplasmas under off-resonant laser irradiation. Next slide, please. Yeah. Nonlinear optical susceptibility of a medium plays an important role in the fabrication of efficient nonlinear devices, including optical parametric amplifiers and oscillators, frequency converters, sensors, pulse narrowing, and signal processing. The choice of a nonlinear medium and its operating wavelength are crucial aspects in the design and fabrication of the efficient optoelectronic devices. Among the rich variety of nonlinear optical media, the semiconductor plasmas offer considerable flexibility for the fabrication of optoelectronic devices. Stimulated Raman scattering in semiconductor magnetoplasmas has been studied in the resonant as well as off-resonant transition regions. The resonant nonlinearities of the semiconductor are even high in magnitude, but they exhibit longer response time. On the other hand, the off-resonant nonlinearities of the semiconductors are even comparatively smaller in magnitude, but their response time is very fast. Okay, next slide, please. Okay, theoretical formulations. In order to develop the model, we consider the parametric coupling among the three waves, that is an intense coherent wave, an induced optical phonon mode, and the scattered Stokes component of the pump field. These are the phase matching conditions that we have used among these fields, and these are the basic equations that we consider to derive the expression for Raman susceptibility. Next slide, please. Using these equations, we first obtain the perturbed carrier density associated with the optical phonon and Stokes mode. Then we obtain the resonant Stokes component of the electron current density. Then by its time integral, we obtain the nonlinear polarization, and then we obtained its third order component, and finally we obtained the expression for third order Raman susceptibility. Next slide, please. One can see from the previous slide that the Raman susceptibility is a complex quantity and it contains two terms. One is the intensity independent and other is the intensity dependent. Then we rationalize these equations and calculate the real and imaginary parts of the intensity independent and intensity dependent Raman susceptibility. And for numerical calculations, we assumed N-type indium antimonide crystal that is assumed to be radiated by a pulsed carbon dioxide laser at 10.6 micrometer. Next slide, please. Yeah, in these figures, we shows the nature of variation of the real and imaginary parts of the intensity dependent and intensity independent Raman susceptibility on externally applied magnetic field, because this is the semiconductor magnetoplasma. Here one can observe the change in sign as well as enhancement in real and imaginary parts of intensity independent as well as intensity dependent Raman susceptibilities. Next slide, please. Yeah, in conclusion, I would like to say that this behavior can be explained on the basis of resonant conditions. These two resonant conditions, this is the resonance between the coupled cyclotron plasmon mode and the scattered Stokes mode. Other is the resonance between electron cyclotron mode and pump wave frequency. The results also allow the tuning of scattered Stokes mode over the wide range of frequencies and explore the fabrication of optical switches and frequency converters by selecting appropriate values of doping concentration and external applied magnetic field. Thank you. Any questions, please?
So why your Raman susceptibility is dependent upon the magnetic field?
Upon the magnetic field. Because we consider the semiconductor medium at liquid nitrogen temperature, and at liquid nitrogen temperature, the dominant scattering mechanism is due to optical and acoustical phonon modes. Here we assume the scattering is due to optical phonon mode, and that is the Raman stimulated Raman scattering.
No, but where that magnetic field is coming into picture there?
Magnetic field induces the coupled mode along with the plasma electron plasma frequency. That is, electron cyclotron frequency contains the term magnetic field, and by highly doping we assumed the electron plasmon mode, and under the sufficient intensity of the laser beam, these two modes coupled each other.
So in which direction of magnetic field you will prefer to?
Magnetic field is transverse to the pump wave direction.
And if I put along the pump direction?
Then the Lorentz contribution to the magnetic field to the effective nonlinear susceptibility will be very small. And we get the Raman order susceptibilities approximately 2 orders of magnitude smaller.
So this is basically a theoretical calculation, right?
Yes, sir. This is the coupled mode approach under classical hydrodynamic approximation.
So, okay.
Yes, sir. Thank you, sir.
I am done. Yeah, thanks.
Yeah. So, Gopal, you said this work is useful in using for high-speed optoelectronic applications.
Yes, sir. High-speed optoelectronic devices.
Right.
We suggest
wait.
the fabrication of optoelectronic devices, including frequency converters, optical switching, optical Raman amplifiers for telecommunication technology, as well as Raman lasers. We also suggest.
Yeah. So, can you please give one example where this calculation is important, how it is directly connected?
Sir, actually, the relevant experiment has not been performed. So before this, we cannot say that what is the actual results that we obtained that agrees with the
assume that these results will be reproduced in an experiment. How will how will this apply for some particular application, application?
Sir, this is very difficult because we obtained the enhancement at a resonant frequencies, and the corresponding magnetic field is very high. That is of the order of 14.2 Tesla in our case.
Okay. No, how is it useful to an application?
Sir, actually the experimental cost will take this is much.
For example, what is trying, you specify one experiment. For example, you say that in optical switch. How in optical switch it will be useful?
Sir, in optical switches, other semiconductors, including silicon and germanium, are used, but in literature, I didn't find the 3-5 semiconductors. This calculation is made for indium antimonide crystal.
Okay, fine. Thank you.
Because the data was available for this crystal only. We find in literature.
Thank you.
Okay, thank you, sir.
Our next presenter is Kavish Bharadwaj. Poster number is CP0407. Kavish, please
sir.
begin.
Can you hear me now?
Yes, please begin.
Good afternoon all. I am going to present our work on trap losses in a quadrupole magnetic trap. Next slide, please. So we have performed magnetic trapping of rubidium atoms in a single chamber assembly. We have loaded the atoms in a magnetic trap from MOT because the magnetic trap is only a few Kelvin deep, and atoms can't be loaded in a magnetic trap directly from rubidium vapor at room temperature. So we found out the lifetime of atoms in this magnetic trap to be around 5.5 seconds, and the decay happens of atoms in this magnetic trap due to two reasons. One is due to the background collisions, and other is due to collision among atoms within the trap. So because our future experiments are related to RF dressing and TAP, so we have tried to study this lifetime. Next slide, please. We have measured this lifetime in presence of an additional beam, which is off resonant to the transition which this atom can make. the atoms in this magnetic trap are in F equal to 2 hyperfine sublevel, and this light is resonant to S half F equal to 1 hyperfine level to excited state hyperfine level, that is 5p 3 by 2 F prime equal to 2. So this beam is off resonant, and it is off resonant by about 6.8 gigahertz. So in presence of this beam, the lifetime of atoms in the magnetic trap reduced significantly. For example, at 2.5 milliwatt power, the lifetime reduced by 50%, and at 7.5 milliwatt power, the lifetime got reduced to less than half a second. Next slide, please. So by this, we have concluded that the losses due to additional beam present in the magnetic trap is higher than the Majorana loss. And we are also trying to find out the reasons for these losses. In this study, the background loss coefficient remained constant for all these additional beam powers. That was 0.18 second inverse. However, the two-body loss coefficient beta increased significantly. That's all. Thank you.
Yeah, nice work. So, Dr. Rahul, you want to start?
You can start. I will take over.
Okay.
Let's start.
So, okay, you are just for studying the light-induced this thing. You are doing this experiment, or you have some specific experiment in your plan?
Sir, we wanted to increase the lifetime, and we always talk about the light leakage from our AOMs. So we wanted to quantify how much is the loss rate due to in presence of an additional laser beam. So we were trying to do this, and we found out that our losses are more compared to Majorana losses or other losses. So we will continue this study.
Okay, so if we'll go to, it is just only it is off-resonant excitation, or something more is happening with the this loss, whatever loss you are getting.
Yes, sir.
That is just a heating effect, or?
Sir, it was not heating because the scattering rate, because due to this additional beam, was very small. So we suspect that it is because of hyper fine changing collision or some state changing collision, which is inelastic in nature, that can provide enough energy to atoms that they are lost out of the trap.
Or some light assisted enhanced collision is there?
Yes, sir. Yes, sir. Some of the these things might be happening.
Okay. I'm done, Dr. Rafur.
Yeah, so I mean, I am also wondering what is the idea of in doing this light-induced loss study?
Sir, we want
that too in a magnetic trap, because typically when atoms are trapped in a magnetic trap,
Yes.
they're all in dark. I mean,
Yes,
there's
sir.
no
This
need
is-
of light. Whereas one would be interested in looking at maybe three-body losses or something like that in a magnetic trap, or
Yes.
hyperfine changing collisions because of some other because of the density and things like that.
Yes, sir.
Now, what was the motivation?
Sir, we wanted to know how much effect is due to the leakage lights out of the AOMs, and whether they are so significant that we always worry about them.
Okay, fine. Thank you.
Thank you, sir.
Our next
But
presenter
in order
is
to avoid the leakage of this leakage from the AOM, you are not putting because your lifetime are very large, basically, right? 6 seconds. So you can put a mechanical shutter.
Sir, no, we have not used mechanical shutters in this.
After AOM, if you suspect like that, then you can just simply put a mechanical shutter and see whether you can get a.
Sir, shutters we have not used in our experiment, and in our further experiments on RF dressing and all, we wanted to know how much is the use of those shutters, because they also take some time to shut down the light.
Okay, so when you change this detuning, so do you see any kind of resonance kind of thing there? Or it just as you increase the detuning and you measure the loss rate?
Sir, detuning was already 6.8 gigahertz.
So only at one fixed detuning you have carried out your experiment.
Yes,
so
sir.
you haven't changed your detuning further away or try to see it?
No, sir, not yet. We will try to do that, sir.
Okay. Chakera sir, you have some question? Okay, maybe
I'm done. Okay.
Yeah.
Our next presenter is Shikha Mishra. Poster number is CP0507. Shikha, please begin. Shikha, can you hear us?
Yes, I can hear you. Hello? Hello?
Please start.
Okay, thank you. In this work, we have studied enhanced synchrotron X-ray radiation from collective oscillation of electron bunch in laser plasma accelerator and Wiggler. Laser plasma accelerator are cost-effective and compact because of huge accelerating gradient of 100 gigavolt per meter. But simultaneously, in last 1 decade, they have also emerged as a good source of synchrotron X-rays also, which are produced by the betatron oscillation of electron inside the plasma cavity. In our experimental observation, in this work, we have proposed a method for efficient X-ray generation. There are two types of oscillation. One is random betatron oscillation and next one is collective betatron oscillation. In collective betatron oscillation, all electron oscillate in phase and with maximum betatron oscillation amplitude, which will lead to increase in peak X-ray flux as well as critical energy. So if in experiment we will observe collective oscillation, the source will be more efficient. We have used 150 terawatt laser system where laser have interacted with gas jet and by the interaction of gas and laser, an accelerated electron and X-ray were absorbed. Next slide, please. Yes, these are the results. We have used these laser and plasma parameter for obtained electron beam and X-rays. In electron beam spectra, we could clearly see the collective oscillation and corresponding X-rays. We have observed clearly these oscillation at density above 8 into 10 raised to power 18 per cc, which was found to be increased with higher plasma density, and impact of which we have seen on X-ray images also. At higher plasma densities, as collective oscillation amplitude increased, flux and X-ray divergence both increased simultaneously with the oscillation amplitude. To see its clear effect, at same plasma density, we have analyzed the two shots, and we have found that when these collective oscillations were present, the peak X-ray flux was almost double as compared to the shot when oscillation were absent. Next slide, please. Hello, next slide, please. Hello, can I go to the next slide, please?
Next slide, please. Hello.
Yes, thank you. Then we just tried to investigate the reason behind those oscillation, and we found a systematic variation in electron beam deflection in vertical plane, on which plane we have found those oscillation. We have found that electron beam deflection increased with higher plasma density. In literature, the same deflection. Hello, am I audible?
Yeah, you go ahead. Go ahead.
Okay, thank you, sir. In literature, we have found the same systematic variation because of asymmetric laser intensity profile. So in our case, there may be a possible reason which causes those collective oscillation and made our source more efficient. So in conclusion, we have demonstrated an efficient X-ray generation source with triggered corrective beta tone oscillation. We have reported a peak brightness of more than 1 into 10 raised to power 21 photons per second per stadion in 0.1% bandwidth at a critical energy of 35 plus minus 5 keV, even in a plasma length of 4 mm with electron beam energy 100 to 300 MeV. And finally, these oscillations not only provide an efficient source, but also provide a source which can generate polarized X-rays because of dominant oscillation in a single plane. Thank you. Hello.
Dr. Pradhan. Yeah, you
Yes.
begin. You begin, please.
Okay. So, what kind of X-ray energy you generate using your system?
Sir, tens of keV, 30 to 40 keV in our case we have observed.
And what is the basically intensity?
Sir, brightness I have mentioned, which is at the order of 1 into 10 raised to power 20 to 22 in our case, photons per second per stadion.
Okay. And what is the basically width of this spectral width of this?
Yes, sir. Sir, this look like a synchrotron spectrum, so this is almost broad with a certain critical energy.
So with synchrotron, how it compares basically in terms of intensity?
Sir, yes, if we compare brightness of our X-ray source, so in that case, it is almost comparable to a synchrotron source, which we get in second generation.
Okay. Thank you. Nice talk. So, Dr. Rafu.
It was a nice talk, but I don't have any questions. I'm sorry.
Okay, sir.
Yeah, I have a few questions.
Yes, sir.
How do you control your random and collective oscillation?
Yes, sir. Sir, in this case, we haven't controlled it. We just observed that whenever those collective oscillation were there, higher flux was observed. But in future, we have made a plan to control those oscillation by introducing some asymmetry in laser intensity. For example, if we introduce pulse front tilt in laser intensity, so by tuning pulse front tilt as well as um, the plasma density, we can control those oscillations. Sir, one more thing. Yeah, yes, sir. In my second slide, I have shown that with plasma density, those oscillations were changing. So by changing plasma density, we can control our oscillation for the present case.
No, but what parameter which controls this? Okay, or physics-wise, what controls this? Collective behavior.
Sir, yes, sir. That is off-axis injection. If all electrons are injected off-axis at the same localized position, they will exhibit collective oscillation.
Okay, why? Why on axis will not lead to collective behavior?
Yes, sir. Sir, because these collective oscillations are mainly governed by the transverse forces. And if electron will inject on axis, those forces will be almost zero on that axis.
Okay, but but what is the limit on off-axis injection?
Limit, sir, limit like maybe I could not understand.
See, you said that off-axis lead to collective
Yes,
oscillation. So up to
right, sir, right, sir.
yeah.
Like up to what extent I can, sir, laser diameter is the maximum limit, but lower means maximum limit is laser focal spot.
Okay, so
More than that is not possible.
okay, so that means if you increase the laser spot, then what other parameters we are going to compromise on the laser acceleration?
Sir, definitely laser intensity.
Yeah, so there is a limit on that.
Yes, sir.
Okay.
Yes, sir.
Okay, I'm done.
Our next participant is Atul Kumar, poster number CP0508.
Yes, sir. Yes, ma'am.
Yes, please begin.
Poster is not visible. My PPT is not
Yes,
visible.
yes, just wait for 2 seconds. Please wait for a minute.
Okay.
Yes, please begin.
Yes. Good afternoon, all of you. The title of my paper is the laser-driven shock study in aluminum foil coated with a PMMA polymer. So first, I will briefly discuss about the introduction. The laser-driven shock studies are useful in study of equation of state of matter under extreme condition of pressure and pressure, which is very important in different branches of physics like phase transformation, material science, astrophysics, and inertial confinement fusion. So the pressure can be enhanced by two ways. One, we have to increase the laser intensity, or here we have used the low density material pre-coated on the target, and this can enhance the shock pressure by well-known technique known as impedance mismatching technique. If the intensity is higher than the 10 to the power of 14 watt per centimeter, then the preheating effect uh, uh, can dominate due to generation of X-ray in plasma, and which these X-ray can moves with the velocity of light and preheat the unsock material inside the target. So to avoid this preheating, we have used this low density material as low Z. So low Z can avoid this preheating since low Z material can reduce the X-ray formation. Next slide, please. So this is our experimental setup. In this ND glass laser beam is focused on the target inside the vacuum chamber, and a part of beam is used to probe these target, and two-frame pseudography is used the measurement of particle velocity. And apart from this particle velocity measurement, we have used filtered X-ray diode to measure the X-ray fluence, and with the two filters, B8 and titanium filters. Next slide. Next slide, please. These are main results in which the experiment is performed on to target simple bare aluminum with the thickness of 6.5 micron and PMMA coated 6.5 micrometer aluminum. And the first plot shows the scaling of laser intensity with measured particle velocity in two targets, bare aluminum and PMMA coated aluminum. From this graph, it has been clearly shows that by coating the PMMA, the particle velocity can be enhanced by of the order of 20%. And second and third plot shows the X-ray emission from the two filters B8 and 3 micron titanium filter. B8 shows the softer part of X-ray transmission, and filter 3 micron titanium filter shows the transmission of harder part of X-ray. From this figure, it is yes, it is clear that by coating the PMMA, the harder part of X-ray is reduced significantly. So this can reduce the preheating of the material. Thank you. Thank you.
Yeah.
Hello.
Yeah. So you are using low Z material to reduce the X-ray emission, right?
Yes, yes.
And
Sir.
then why we are using low density also?
Yes, low density is used to enhance the shock pressure inside the target. And in this case, we have obtained the 20% in enhancement in velocity, particle velocity. So shock pressure is enhanced almost
Is
40%.
there any optimum value of density?
So no, less than the target value. So here aluminum is 2.5 gram per centimeter cube, and PMMA density is 1.18 gram per centimeter cube.
Okay, so there is only
we can further reduce the density, so we can enhance the shock pressure.
Okay, I am done.
So, Mr. Kumar, can you tell me how the X-ray emission is getting enhanced when you have a PMMA coating? In what sense?
It is reduced by PMMA coating.
Oh, it is reduced. Okay.
Yes, sir. Because it is low density as compared to aluminum. Low jet as compared to aluminum.
I see. Okay. Thank you.
Atul.
Yes, sir.
Yeah, see, you're coating with PMMA, which is transparent material, isn't it?
Yes, sir.
So your laser beam not passing through that layer. Finally, it will interacting with aluminum, isn't it?
No, it is laser focused on the PMMA target.
Okay.
The plasma is formed inside the with the PMMA target.
No, but it can transmit also, no, through that. See, partly it will be creating a plasma.
Yes, sir.
And partly will be transmitting through it also. In fact, it can lead to self-focusing also. In PMMA.
Sir, the intensity is very high, 10 to the power 14 watt per centimeter.
Yeah, so that
it forms the plasma.
No,
so above critical density, it cannot penetrate inside the target.
Okay.
Hello?
Okay, I'm done.
Okay. Thank you, sir.
Our next participant is DPSL Kameshwari. Poster number is CP0509.
Good afternoon, everyone. I'm Kameshwari. Am I audible to everyone?
Yes, please continue.
Yeah. Good afternoon, everyone. I'm Kameshwari from University of Hyderabad. Today I'm going to discuss about the effect of the background gas pressure on laser ablative plasma on shock waves generated from a 20 micron thick aluminum foil. Next slide, please. Next slide, please. Yeah. So the tabulated values here show the typical laser parameters that were considered. The results that were being presented were the simulated results generated using flash 2D radiation hydrodynamic code, and these were the laser parameters. The wavelength is of 532 nanometer, and the domain that is shown at the center is the physical domain where the film at the center representing the 20 micron thick aluminum foil and showing the direction of the laser beam. The front end of the target showing the ablation regime and back end showing the blow off regime. So in order to discuss the background gas pressure is varied from 0.1 atmosphere to 1 atmosphere. So the images showing on the right side were the pressure images taken at 50 nanosecond for all the 4 background gas pressures, that is 0.1, 0.2, 0.5 and 1.0 atmosphere pressure. So the thin layer that can be seen at the front side of each image showing the shock front, and the bright region appearing at the center is the plasma region. The shock is formed because of the accumulation of the mass that is removed from the focal region, and plasma is the number of free electrons and ions that were removed. And so if we can clearly see this, the expansion of the shock is more for lower background gas when compared to the higher background gas. Like if we compare the 0.1 atmosphere and 1 atmosphere, In 0.1 atmosphere, the shock is at around 700 micron, while at 1 atmosphere, the shock is at 500 micron, and the strength of the shock has as well increased. The images on the lower side representing that the shock and plasma parameters were increasing with respect to the background gas. Next slide, please. So these were the plasma and shock radius and plasma and shock parameters, representing that the plasma and shock expansion were more prominently more for lower background gas and were less when for higher background gas. So we can confirm that the plasma and shock wave were being spatially confined with the increasing background gas, and these were right side were the plasma and shock parameters, indicating that plasma and shock parameters were high for higher background gas and low for lower background gas. Next slide, please. And these were the pressure plots showing the pressure at 1 atmosphere of background gas, where the at 500 nanosecond the shock front with higher strength is showing the hemispherical structure, and the shock front on the blow-off regime showing the more axial expansion direction, that is called as the blow-off shock. And these were the plasma parameters indicating a decrease with respect to the increasing time. So from this, we want to confirm that the increase in the background gas pressure leading to increase in the plasma and shock parameters, and spatially confining the plasma and shock waves. Thank you. Thank you.
Why have you choose aluminum as your substrate?
So I can't hear you.
Yeah, you have chosen aluminum. You are using aluminum, right?
Yes, sir.
Suppose I use gold, then what difference I am going to get?
It is the ionization of the material that is going to affect the plasma and shock parameters, sir.
With respect to background gas pressure.
Yes, sir. Even though whatever the material may be, the ionization of the material is playing the role here.
Okay. And you are using just air, not any specific gas, right?
Yes, sir. In this present work, we are just presenting in presence of air. If it is a helium or argon, the condition may be different. It is the atomic weight of the background gas that plays the role when the background gas is varied.
Okay, thank you.
Yes.
Okay. Yeah, please go ahead.
Okay, fine. Thank you. So, you have studied this confinement as a function of pressure of the gas.
Yes, sir.
Do you have any idea about what would happen if the nature of the gas is changed? Like if you choose gases with higher AC polarizability or something, what would happen?
Like example, sir?
Some gas which has a
That's what, sir.
polarizability,
It is
finite
the
polarizability.
background gas, atomic weight of the background gas plays the role there, sir. It
Not
will
the polarizability, is it?
polarizability, I'm not sure about it, sir.
Some asymmetric molecule which, if you apply an electric field, it would polarize and create an induced dipole moment in it. If you choose some polarizable gas, what would happen? I mean, at least, what do you expect will happen?
Splitting of the plasma plume may take place, sir.
Okay. I see. So what do you mean by splitting of the plasma plume?
Like
Spatially separate out or what?
yes, sir. It was studied in literature that plasma is splitting into two lobes, showing and even um, splitting in the radial as well as in the axial directions is observed, sir.
Okay. Fine, thank you.
Leading to some instabilities in the plasma.
Okay. Okay, fine. Thank you.
I have one or few more questions. Yeah.
Yes.
See, this is your theoretical simulation, isn't it?
Sir?
This is a theoretical work.
Yes, sir.
Yeah. So is it practically possible such you have a laser which is going through a gas at atmospheric pressure?
Atmospheric pressure is experimentally done, sir. Yes, at atmospheric pressure, it is possible.
What about your laser beam quality? See, it is
Quality?
now normally we create a shock or create a plasma on a foil which is
Yes,
in
sir.
vacuum, isn't it?
Generally, it will
Yeah.
be done in vacuum, but yes,
Yeah.
sir, our experiments were done in 1 atmosphere background gas as well.
But what about your beam propagation? You are focusing the beam on target. Before that,
Yes.
it will encounter the atmospheric gas.
Yes, sir.
So the beam quality will not degrade. Laser beam
No,
quality.
sir. No, sir.
Why not? It will see some medium, isn't it?
Yes, sir.
So,
Experimentally, I'm not sure about it, sir. Most of my work is
just
done
you said
theoretically.
this has been done experimentally.
Yes, sir, but were done experimentally, sir.
Okay, just think of that. Okay.
But experimentally, this may be possible. This may be a complication that working on a thin film of such 20 micron thick foil will be a little bit tough because foil will be undergoing oscillations because of the high energy beam that is interacting with it.
No. See, before that, the beam has to encounter your gas, which is at very high pressure, atmospheric pressure, isn't it?
Yes, sir.
So the beam parameter will degrade. It will not be able to.
Actually, it is the
Your focal spot on the target will be very
yes.
poor. The intensity on the target will reduce. Okay. In fact,
Yes.
before that, it will create plasma in
At the focal spot.
the atmosphere itself.
No, sir.
Because your beam is converging, isn't it? When you focus it,
it is being focused at the focal region.
Exactly. So you have kept your target on that focal spot, isn't it? But
Yes,
before
sir.
that, now you have a medium, some medium.
Yes,
and
sir.
beam is converging.
Yes, sir.
When it progresses through it, okay?
Yes, sir.
So it will see a medium, isn't it?
Yes, sir.
So
But since this is a nanosecond laser, its absorption with the surrounding medium will be negligible, sir.
No.
Sir?
Even intensity, if you see intensity, nanosecond beam.
Yes, sir.
What is the intensity you are putting on the target? 10 to the power 13?
It's in gigawatts, sir.
Yeah, so
2.5 gigawatt.
No. See, focus intensity at the target.
Sir?
It will be 10 to the power 13, somewhere close to 10 to the power 13. Watt per centimeter square.
It is 2.5 gigawatt per square centimeter, sir.
What is your focal spot?
Focal spot is 500 micron.
500 micron.
Yes.
Pulse duration is 10 nanosecond.
Yes, sir.
So it will be 10 to the power 9, you mean to say?
Yes, sir.
Okay. I am done.
Yes.
Our next participant is Sai Shiva. Poster number is CP0510. Sai Shiva, please begin.
Okay. Am I audible, madam? Hello.
Please begin. Please begin.
Yeah, good afternoon, everybody. I'm Sai Shiva from University of Hyderabad. I'm presenting my work on three-dimensional hydrodynamic simulations of laser-induced metal blow-off from thin metal foils and the modeling challenges involved in the modeling setup. Please go to the next slide, madam. Next slide, madam. So this is the introduction of my work. So I would like to simulate the laser-induced material blow-off from thin aluminum foil using the three-dimensional flash RSD code. and the challenges involved in the 3D modeling is addressed in this present work. And the final aim is to simulate and validate the experimental observations. So these are the experimental observations. This the first figure is the schematic of our model setup, and the second figure shows the experimental shadowgrams, where we clearly observe that the aluminum foil coated on the glass substrate is used to blow off the material, and we can clearly see the material ejecting from the rear side of the aluminum foil. And the third figure shows the blow after the post analysis of the target material. We can clearly see the nice spots on the aluminum target. So our aim is to simulate the all these experimental observations. So this is the simulation setup. So so these are the typical laser parameters used to study the to update or blow off the material from the aluminum foils. So during the modeling setup, we encountered different challenges. The first thing is the laser beam focusing at the glass foil interface. So this is the crucial part. And the second one is the implementing of the equation of state of different materials. So in this case, we have implemented 3 different materials, glass, aluminum, and air. So that implementing is a difficult task in the modeling. And the third one is the restricting the physical movement of the target foil, because we see here in this figure that the target is moving unconditionally. So we need to physically constrain this target movement. So in order to constrain the stop that target movement, we have given some input conditions into the target into the code. Move to the next slide. So these are the blow-off simulations. We clearly see that the material blow-off taking place at different time scales, and we can also see the formation of shockwave and its evolution at in the ambient atmospheric air from the rear side of the target material. So we conclude that we have overcome all the challenges that have been addressed in the earlier side. So our next target is to compare the experimental results with the simulated results. So that is our future scope. Thank you very much.
So you are using also background gas pressure for your calculation?
Yes, sir. We are using air as the background medium.
Okay, and with the background, you can replicate your experimental data with your simulation?
Yes, sir. The results that we have shown are the preliminary results. So in the future work, we are going to validate with the experimental work.
Which simulation code you are using for this one?
We are using Flash 3D hydrodynamic code, sir.
Okay.
Hello?
Yes, sir.
Hello. So what kind of so what kind of models does your code use for simulations?
Model in terms of, sir, the
physical model.
Okay, sir. It considers the laser propagation model, laser deposition model, and the physical plasma models like the electron heat conduction through the materials, and the radiation components, and radiation emission from the target materials.
Okay. And how intensive are these in terms of computationally? How intensive are these?
So actually, the simulation takes around half day or 1 day, sir, for this particular simulations.
On what kind of system?
We have a workstation. Yeah, we have a workstation here with a RAM of 16 GB, and i3 processor, Xeon processor. So it takes around half day to 1 day to simulate this one.
Okay. Okay, fine.
Yeah.
Thanks.
Thank you, sir.
Okay, I have done. Go ahead.
Sir.
Our next participant is Amit. Poster number is CP0511. Amit, please begin.
Hello everyone. So today I am going to talk about the velocity mapping in hot dense laser produced plasmas. So as Ravi talked about in his keynote talk, TIFR AFIL actually hosts two CPA based high power ultra short pulse lasers which are shown here. They are mostly namely 20 terawatt laser pulse width of 30 femtosecond giving energy of 0.6 joule and 150 terawatt laser giving the pulse energy of 3.7 joule onto the target. Apart from their high peak power, the basic difference between these two lasers is their intensity contrast. If you see the top figure here, at 25 picosecond, 20 terawatt laser can give an intensity contrast of 10 to the minus 6. But whereas the 150 terawatt laser is a quite having high intensity contrast, as high as minus 9 at 25 picosecond earlier. So this basically governs the nature of laser matter interaction and thereby the formation of an hot dense plasma. So can we go to next slide, please? Next slide, please. Yeah. So when such high intensity pump beam interacts with the solid targets, it generates a very hot, dense solid plasma, and thereby the relativistic jets, which actually carries the laser energy deep into the target. And as we know, the ultra high intensity physics becomes very challenging because the nature of their transport and the plasma formation, as the instantaneous profile of the plasma density becomes very crucial parameter as it controls most of the coupling physics and hence the nature of the plasma at very different time scales. So the plasma interaction region moves on ultra fast time scale and hence it is extremely difficult to track. But what we here use is a power of a pump probe technique where we excite with intense pulse and then second harmonic probe basically interrogates the plasma and we measure the Doppler shift from it. With low contrast 20 terawatt laser, one can see the Doppler shift where initially you can see a huge red shift followed by the blue shift and the expansion velocity as high as 10 to the 7 centimeter per second. So basically pump launches a compression wave initially which pushes the critical surface inside and that's why we see this red shift followed by the rarefaction wave behind blue shift, and with very high contrast laser you shoot a minimum red shift that's basically due to the repulse generated at the target and you can see the explosive blue shifts thereafter. But this is when we are only talking about the space integrated transfer average information, but actually the plasma is highly non-uniform and included in nature. Can you go to next slide, please? So we have carried out, next slide. So we have carried out space and time result. Next slide, please. Of plasma dynamics. Hello. Can we go to next slide?
This is your last slide.
Okay, at initial time scale, we have developed a 16 spectrometer multi-channel 2D profile velocity map. At initial time scale, we can see very high rate shift followed by the different parts of the probe which are going under a blue shift as the time progresses. And we can see different amounts of shifts from the transferred location, non-uniform plasma dynamics. Measuring the time-dependent Doppler shifts have gave us the information about different position across the probe beam. We achieve the velocity mapping at hundreds of femtosecond time resolution and thereby microsecond spatial resolution across the spatial length of the plasma. And this is important for 2D map of critical surface motion, 2D velocity mapping, and thereby strong.
Please, judges, please ask questions.
Dr. Pradhan, you ask.
Yeah. So your probe is co-propagating with the in the palm direction. Hello. 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 Hello.
Judges, shall we
I
move?
can hear you.
Yeah.
Yeah,
So
we can hear.
maybe there is some communication problem from his side. Yeah.
I had a question too,
Amit,
but I don't know.
Amit, can you hear listeners? Amit, can
Mr.
you
No,
hear?
Amit, can you hear us?
Okay, maybe we have to move to the next.
I think we will move on to our next presenter. Our next presenter is Yash M. Ved. Poster number is CP0512. Yeah, Yash, can you hear us?
Yes, I can hear you. Am I audible?
Yes, yes, please begin.
Hi, good afternoon, everyone. I am Yashved from Apple Lab. As Amit described, that we have two lasers, high power lasers, a 20 terawatt and a 100 terawatt laser. So I will not get into the details of it. Our earlier work on ultrafast dynamics of plasma showed us the 1D measurement using the pump probe techniques. 1D means transversely resolved but spatially integrated. Can you move to the next slide? As you can see that the plasma is not a 1D in nature, it is a 2D plasma in nature, and there is a need of a special technique to measure the transfers as well as the spatial resolved plasma dynamics. So for this reason, we have designed a 2D spectrometer. Can you go to the next slide, please? So we have designed a high resolution multi-channel spectrometer, which is ready for 2D Doppler measurements. In this spectrometers, we have like 16 high resolution ultraviolet spectrometers. The Doppler shift we know is expected around something 0.05 nanometers. And these spectrometers have a wavelength of like 404 to 422 nanometer in UV range. The grating slides is around 2400 lines per mm, and the slit size is 5 micrometer. The CCD resolution of this spectrometer is like 4096 pixels, so which gives us a resolution of 0.03 nanometers, which helps us to resolve the plasma dynamics in high resolution. At the end of the spectrometers, we have connected fibers to it. So there are 16 fibers which are attached to the spectrometers, and each fiber has one end which is barely cleaved, and the other end is connected to SMA connector, which is like connected to the spectrometer. A housing, as you can see on the left side of the picture, in the center picture, a housing is made for the for hosting all the spectrometers, which provides a common triggering power supply as well as heat dissipation. There are cooling fans to dissipate the heat from this spectrometers. These spectrometers are tested in single shot as well as in continuous mode, and a lot of data has been taken and analyzed for their performances. The fibers on the right side image, if you can see, array of fibers are mounted on a custom made fiber holder, which will couple the light, which will couple the probe beam, and this mount is placed on an XYZ theta mount alignment. Uh, so there are 16 spectrometers which are multi-channel. They have a very good resolution of 0.03 nanometer, and they can be triggered in a single shot. So we have like all spectra which can be displayed on a single screen in a software, and we have like a temp and transfer as well as spatial profile in every shot of the plasma. Can you move to the next slide? So these are the earlier results from our lab. The red shift, which indicates there is an inward motion of the plasma as the time propagates. We see a blue shift that the plasma propagates in the outer motion direction. Yeah. Next slide, please. Okay. Thank you, everyone.
I have a
Can
question.
I go ahead? Yeah.
You are using an array of fiber basically, right?
Yes, array of fiber, 16 individual fibers.
Why you are using that?
In order to capture the spatial of the probe, we are using each spectrometer which will probe the spatial profile of the plasma.
Okay, but for that purpose you are using CCD camera, right?
No, we are using spectrometers.
Okay, for spectral profile.
Measurement. We are doing a Doppler shift measurement.
Okay. Then how do you couple this light to this fiber?
We have this probe beam coming out, and we have this probe beam coming out from the which reflects from the critical surface of the plasma, And these fibers are mounted on the spatial chamber. Can you take to second last slide, please?
No, but what kind of collimation optics you are using before that?
We are using F2 imaging. F2M imaging.
What is the diameter of each each fiber core? Core diameter of each
400 micrometer dia.
Okay, very large diameter. Okay. And for the CCD, whatever the special measurement you are doing, then what kind of optics you are using? So you said that around 0.03 nanometer spatial resolution you can get.
Yeah. This is for spectrometer. Spectrometer has a resolution of 0.03 nanometers. It can resolve in that range.
Oh, spectral resolution. Okay.
Yeah, and we are resolving spectrograph.
Okay. Okay, Dr. Raful.
Yeah. So how are you getting this? How are you doing the time triggering? I mean, when you capture this data, what are you using for?
We are using pump probe technique.
Ah.
And so we have this all the spectrometers which are like connected to each other with via BNC trigger. Laser trigger from the laser, and we give this master trigger to the trigger box, and from that all the spectrometers are triggered at a time.
Now this spectrometer detector is also something like something that can be triggered. I mean, with a high voltage or something.
Yes, the spectrometer takes a TTL 5-volt TTL triggering. So the probe beam which comes, which will be like delayed with respect to pump. So we give the trigger of the pump pulse so that the spectrometers are ready to receive the signal.
What type of detector does the spectrometer have? Final detector, which
it will have a grating and a CCD.
CCD. Okay, so the CCD image is triggered with your trigger signal.
Yes.
To capture at that given instant.
Correct.
Okay.
Correct.
So what are the time delays involved? I mean, once you trigger the CCD to dump the image, does that reflect anywhere in your delays?
In some femtoseconds to picosecond of delay. Of the probe.
Okay.
Like femtosecond to picosecond delay of the probe.
I see. Okay. Fine. Thank you.
Yes. I have a question. See, you are collecting light from critical density, isn't it? By a lens.
Yes.
And you are putting into your fiber channel, multi-channel.
Correct.
Then how do you say it is 2D? Because you are collecting, lens is collecting light from all the area at the critical density. So each fiber will have contribution from all the information which is lying on the critical density at that area.
So we are doing an F2F imaging mode. So it's in an imaging mode.
Yeah.
2D imaging.
2D imaging. So in that case, the resolution would be.
Excuse me, judges, there is a request that we are short of time. So can we just squeeze the Q&A session, please?
Yeah. So special resolution governed by your
will be in micrometers. Special resolution will be in micrometers.
Yeah, depending on your fiber diameter.
Correct.
Yeah. Okay, that's it.
Thank you.
Next participant is Suman Bagchi. Poster number is CP0513. Suman, please begin.
Yes, I hope I am audible to all of you.
Yes, please begin.
So good afternoon, everyone. I will be continuing the poster on laser plasma interaction, and compared to my previous speakers, I will be focusing on the other aspect of the laser plasma interaction, which is an acceleration from such intense ultrashort laser pulses. And as we all know, that this when such an obliquely incident ultrashort laser pulse incident on such a foil target, it is a very strong source of intense and highly bunched and coherent electron sources, as we have already seen from my previous speakers. When such electrons emit, because of their high kinetic energy gets emitted from the thin foil targets, they create a electric field gradient on the surface, which is known as the sheath layer. And now that sheath layer is the cause of a strong field gradient, which gives rise to the ion acceleration from such foil targets. So my poster is focused on the use of such proton beams for the radiography of microstructures and a dynamic evolution of the expanding plasma plume. So as I already mentioned that the accelerators have lots of implications in our science and fields of science and technology. The use of energetic ion beams from such intense matter interaction provides us a good opportunity to study the dynamic evolution of matter in real time. Can you please go to the next slide? Yes, so you can see from here, our experimental target is first we focus a 25 femtosecond intense laser plasma on a thin foil target, and then we put, and then the proton beam which is emitted from such foil interaction, laser foil interaction, is then probes the metallic foil target and eventually reaches onto the detector surface, which is imaged by a CCD camera. And on the second experiment, we have a long pulse laser, which is a unstretched or the stretched laser pulse of 560 picosecond duration forms a plasma on a secondary target, and the evolution of such long pulse produced plasma is being probed by this proton beam on the CCD camera. The basic fundamental formulation is known as the target normal speed acceleration mechanism, and which is, as I already explained earlier, the slides on the bottom shows from the different target foils, for example, in nickel 5 micron and 1.5 micron tantalum of different foil thickness, how are the proton beam profiles recorded on the radiochromic films from the first layer and the second layer itself. And we have chosen, based on the uniformity of the proton beam profile, we have chosen the this nickel 5 micron foil for our study. Next slide, please. Just a second. Next slide, please. And here, this slide shows the dynamic evolution of the expanding plasma plume. The leftmost picture shows the static picture where there is no plasma. However, as we go towards the right, we can see the evolution at different time scales, and we can see the expanding plasma plume expanding plasma plume evolution as it is embedded on the proton beam profile. And as we can also see corrected by this D profile, we can see that the proton density from the center is being dispersed towards the edges, like radially expanding radial expansion, and which is because of the radially expanding electric field in the plasma. And from this, we can see we have expansion velocity of 10 to the power 6 meter per second. Yes, thank you. I'm ready to questions.
What kind of proton density you get with this one?
This is typically 10 to the power 8 to 10 to the power 9 number of protons per shot we get.
Okay. And whatever this picture you are showing, these are how this imaging you are taking by pseudoscopy or?
Yeah, this is basically we take the proton beam profile on the radiochromic film, and we have also done it with the scintillator screen also. So what we do is that we expose the secondary target with the long pulse laser beam, and at a certain time delays, we let the proton beam go through the plasma, and this profile of that plasma is embedded in the proton beam, and which is recorded by the radiochromic films.
Yeah, I am done.
Yeah, so in this dynamic evolution of plasma plume, this picture, what is happening beyond 80 picoseconds? The plasma plume seems to be vanishing, and then...
Exactly. The picture we are seeing here is a culmination of two things. Number one, the hydrodynamic expansion of the plasma, which is because a mass of the plasma which is being detached from the foil surface and eventually going forward. So when you see the longer time scale, that is 80 picosecond and above, you can see the bulk of the plasma has actually moved away from the surface, and therefore which is not being covered by the proton beam. So whatever the initial gap or whatever the initial reduction in the proton density, which is visible till 80 picosecond, goes down, and at 120 picosecond, or even if you go higher times, you will see the surface coming back to this minus 240 picosecond, which is the leftmost picture. So it is during this time period, the plasma can be probed by the proton beam. Beyond this time scale, the plasma has already expanded at a longer distance, which cannot be covered by the proton beam.
I see. And do you see any oscillations in this plasma, in this proton beam?
Right now, we do not have that much of a spatial resolution. What the proton beam is most sensitive to is the electric field distribution inside. So we are, this is our initial experiments, and moreover, this particular observation is also, I would say, influenced by the hydrodynamic expansion. So what we plan now is to repeat the same experiment using the short pulse, 50 femto, 25 femtosecond laser pulse, so that we can get rid of this hydrodynamic expansion, so that we can, the electric field distribution and whatever oscillations, if at all, within the plasma, that should be visible to us.
Okay, thank you.
So I have an announcement to make. Actually, we are already running over the time of the next session, which was supposed to start at 4:15. So I request all the presenters to really follow that time which has been given to you. It's 3 minutes. And I also request all the judges to please try to help us in this. The next session had to be started around 4:15. It's late, it's getting late, and it will delay all the proceedings. So shall we take the next candidate now? Over to IMD.
Yeah, please.
Our next speaker is Tarang Garg. Poster number is CP0514. Tarang, please begin.
Hello, good evening, Chair. I'm here to describe about the. Hello, am I audible?
Please begin.
Yeah.
Yes, yes.
I'm here to describe about the collimated structure we put to reduce the Doppler width in the atomic beam. So in the laser isotope separation of YB176, ytterbium-176, there is an isotope shift of 94.94 gigahertz between the nearest isotope, that is a YB174. So we put up a new structure that in this image it is shown in the red one. It is designed and put above the crucible assembly to reduce the Doppler width. Now this vapor flow dynamics through this new geometry was done computationally using the direct simulation Monte Carlo in the open foam module named DSMC Foam Plus. Now this new geometry causes the atom to be stopped. Now when the vapor is rising from the crucible surface to the laser atom interaction area, there are atoms which are going in the longitudinal direction of the lasers. So this collimating structure, we call it Doppler reducer, reduces the causes the atoms which are going in the longitudinal direction to be stopped, and hence only the atoms which is having less velocity in the longitudinal direction passes through the structure. Now moving on to the next slide. So how did we did the simulation? I made this a vapor. You can see this image on the right hand side, top side, that these are the particles which we started with. On the bottom surface, I gave the evaporating surface from which the atoms are going inside the vapor domain at the density of 5 × 10⁻20 atoms per meter cube. The source temperature was at about 800 Kelvin, which is near to over the experimental condition. Now the Doppler reducing walls is absorbing the atoms striking to it. Now other assumption is hard-sphere collision model is valid, and there is no clustering of atoms which behave as a molecules. And further, as we do the experiments in 10⁻⁻6 millibar of vacuum, so we have not taken the background air density. Now before collimating structure and after collimating structure, you can see from the bottom left side image that the atom is now filling very less of the vapor domain. So because of the because we have put up the Doppler reducer, we are able to achieve the less Doppler width, and the Doppler width comes out to be 327 megahertz at a laser frequency of 555 nanometers. On the on the right hand side bottom image, you can see the velocity distribution of the atoms which are present in the laser atom interaction area. Next, we also did the experiment with the laser system available with us, and from the experiment was done using 3-step photoionization technique, which
Tarang, please wind up.
Okay, So from 3-step photoionization technique and the absorption, and we varied the lambda 1 in the steps of 30 megahertz and see the collected ionized ions on the collector plate, and then we plotted those results. We plotted those results, and we can see that from those results that the FWHM measured out to be 330 megahertz. So this is how we reduce the Doppler width of the laser vapor beam in the laser atom interaction area. Thank you.
Dr. Rahul, you want to?
Yeah. So my only question is why ytterbium 176?
Sir,
why not some other element?
Sir, in our morning session, there was a talk given by Dr. Anil Kumar Singh regarding the enrichment of the YB176 going on. The project of enriching YB176 in our group. So hence we started with the YB176. Later on, we are moving on towards enriching of other nuclear medical isotopes. So further on, we will do similar kind of simulation and we will achieve a proper geometry for those isotopes.
Thank you. I'm done.
Chakera sir.
Yeah, I am done. You can ask.
Okay, so we can go to next speaker.
Okay, thank you. Hello.
Yeah, next speaker.
Okay, thank you very much.
Hello. Hello.
Our next presenter is Saurav Sarkar. Poster number is CP0405. CP0405, Saurav Sarkar. Saurav, can you hear us?
Yes, madam. I can hear
Yes,
you.
please. Just a moment.
Okay. My PPT slides are not visible,
Please
madam.
wait for a while. Yes, please begin.
They are not visible, madam. My slides are not visible on my screen.
What are you seeing now?
Your slide is visible to all others, so there may be a problem at your end.
I can't see the slides.
So there may be a problem at your end. So can you move to the next speaker then? Till you fixed it.
Right now, your first slide is being displayed. So if you remember it, you can.
You could open it in your computer separately and then go ahead.
Saurav Sarkar, you heard. Please open it in your computer. Now we are seeing your first slide, so you can start.
Madam, this slide is different actually. This does not belong to his presentation. The title of the paper is
You share your slide. You share it from your end. Saurav, can you hear us? Saurav? Our next presenter is Sachin Narayan Rao. Poster number is CP0515. Sachin, are you there? Sachin? Sachin, are you there?
Hello, those presenters whose presentation has not yet been done, please raise your hands on your PC so that we know, because Hello, Mr. Sachin, are you there?
Madam, connection problem. We are able to hear you.
Hello, so in that case, we will take a break of 5 minutes. This poster session, oral presentations, this particular session is now over. We will take a break of just 5 minutes and then we will start the next session, which is industrial presentations. So please be with us.
Attendees, Mr. Ajit Upadhyay. Madhu Babu, are you there?
Yes, madam, I'm here.
You are yet to present, no?
Yes.
Yeah, then you please make your presentation. The CP number is?
CP0505.
Yeah. CP. Yeah, CP0505.
Yes, good evening to all.
Time.
My name is Madhu Babu. Dr. Ajit Upadhyay is at some other work. He is busy. I am going to present his presentation, his poster. Are you able to hear me? Hello?
Yes, bolo.
Is it clear?
Please continue. Please continue.
Okay. Inverse complex scattering resource PSA simulation. Gamma resource PSA simulation. Gamma rays are essential tools to investigate the dynamics of matter on atomic scales. In a self-synchronized all optical setup, gamma is emitted due to intense scattering of laser pulse with laser wake field accelerated electron from a gas jet target. Here we can see the experimental setup. We take a high intensity laser pulse and split into two parts. One part is used to generate the high energy electron bunch using laser wake field acceleration technique, and the other part of the laser is used to collide the accelerated electrons to generate gamma ray radiation. The next slide, please. Okay, these are the laser and plasma. Okay, previous slide. Okay, these are the laser and plasma parameters which were optimized to get the 250 MeV energy electron bunch. These parameters are optimized using the PSC code epoch, and the output of this epoch code is given as input to the particle in cell code pecan GPU. This is the GPU based particle in cell simulation code, and it is installed in two nodes HPC cluster, Kshitis 5 at RRCat. The simulation electron beam parameters were used in the code Pecan GPU to calculate the gamma ray radiation generation through inverse competence process ICS. Okay, this is the plot energy and number of electrons. This is quasi energetic. The peak is at 250 MeV and it extends up to nearly 600 MeV. Okay, next slide, please. Okay, this is the simulated gamma ray spectrum showing radiated photon energy at different angles with respect to electron beam propagation direction. The color scale shows the number of photons radiated. Here it is around 750 keV energy photon we got at divergence angle nearly 2 degrees. Thank you. The energy is 1.7 MeV photon energy nearly, and the number of photons is greater than 10^7 photons. Thank you. Are there any questions? Please.
Chakera sir. Dr. Chakera.
Madhu.
हाँ sir, बोलिए.
Yeah, why your electron spectrum having quasi-monogenetic emission? Normally, it should have broad decreasing energy profile of electron.
Okay, this is due to not a electron injection is not sharp at it's some particular place. This is continuous. Maybe the reason, maybe due to continuous injection.
Okay, in your simulation, what intensity of your scattered beam is assumed?
What intensity of?
Your scattered beam.
Gamma ray beam, electron beam.
Main laser beam.
Laser 10 previous slide, second slide, 10 power 19 watt per centimeter square, I think.
10 power 19.
I am not clear. Please previous slide, please. Second slide. Oh, yes. 2.6 into 10 power 19 watt per centimeter square.
Okay. So on what parameter your energy of the content scattering photon depends?
It what, sir? Please come again.
Major parameter on which your emission radiation spectrum depends?
It depends on electron energy.
Or apart from that?
Apart from that, synchronization, the laser pulse and electron beam synchronization.
So flux of your photon?
Yes, it depends.
On what?
See,
this is the energy of content scattering depends on electron energy, isn't it?
Yes,
but what
yes.
about the photon flux depends on what?
Photon flux depends on electron flux.
And one more parameter, or is it on electron flux? Electron flux only.
Electron flux and photon energy, laser energy, laser. Yes, laser intensity.
Yeah. So ultimately, laser photon flux also.
Yes.
At the interaction area. Okay.
Yes.
Okay, I'm done.
Yes. Hello.
I'm done.
Okay.
So with this session ends here, and now we move on to the next session. We will immediately start this session, which is industrial presentations. So I would request Dr. Piyush Saxena, Secretary ILA, to session this chair. Over to you, Dr. Piyush Saxena. Please start the session.
So, madam, this session is over now?
This session of oral presentations is over now. We move on to the next session. We are not taking any break because we are running out of time. And we will start the next session, which is industrial presentations. And this session will be chaired by Dr. Piyush Saxena, Secretary, Indian Laser Association. So over to you, sir.
Yeah. Am I audible? Am I audible?
We can clearly hear you, yes.
Okay. Good afternoon, everybody. Now we are starting the industrial presentation session. In this National Laser Symposium, first of all, I congratulate the organizers that they have given opportunity to present the products of about 15 exhibitors on the website. You just go through the exhibition corner also. I request every participant for that. In this industrial presentation, the first company which is presenting the details is Atos Instruments Marketing Services from Bangalore, and Mr. Anand, the joint director of the company, will present his talk. So now I give the podium to Dr. Anand. Dr. Anand.
Good evening. So shall I share my screen? Hello?
Yeah.
Yeah.
Yeah. Dr. Anand, 10 minutes for your presentation.
Yeah, yes. Just sharing my screen. I hope everyone can see my screen. Hi. Good evening, everyone. First of all, I would like to express our gratitude to the committee to give this wonderful opportunity to give a presentation on our products. We are Atos Instrument Marketing Services based in Bangalore, and we have regional offices in Mumbai, Delhi, Indore, and Kolkata to cover the pan-India operations.
We have specialized in different applications like spectroscopy and scientific imaging, lasers, thermography, NDT, solar cell characterization, gas controllers, and cryogenics. So we have already installed more than 700 installation all over the India, more than 63 cities we are covering. So this is our main principal company, Andor Technology. I hope everyone will be familiar with this product line. Andor Technology, we have working with them from past 20 years, and we have more than 300 installations in India. We are mainly specialized in spectroscopy and scientific imaging. Now, Andor Technology is a part of a big name that is Oxford Instruments. So the one part of the Oxford instrument are handling by us. So that is the cryostats for the optical measurements. So now towards the Oxford Instruments, we are handling the cryostat sections. So we have now liquid nitrogen and helium cooled cryostats for spectroscopy and microscopy. CCR configuration for both samples in vacuum and vapor. We can provide 3.5 Kelvin and to 500 Kelvin temperature range. And this is the lowest liquid consumption in the market. So these products are suitable for UV visible and area spectroscopies. If anyone have requirement for cryostats, you can contact us because now we are doing this cryostats business. In extent to the cryostats business, we are already have another company called it. This is a full-fledged cryostat, which is having various temperature options, 4.5 K and 10 Kelvin, and this one have ultra low vibration interface for the optical measurements and the magnetic measurements. So this is a new product from Coldedge. This is actually a portable cryostat. You can use this cryostat for your different applications. Like one cryostat you can use for different applications. So once you have the system, you can put the system to one application. You can finish that one, and you can go to the another experiment, and you can engage the same cryostat with that one. So this cryostat, it's actually a portable one. You can put it on a optical table or your experimental setup table. It can give, the vibration levels are very less than 10 nanometer, and it can have optical, electrical, magnetical, and measurements structures. So also we are working now with a new company, Skondal. It's a Russian company. They are the pioneers in the field of superconducting nanowires, single photon detectors, liquid helium dipstick, and CCR-based SN SPDs. We have high ultra efficiency, about 90% quantum efficiency, and very low jitter, and we can configure to 2 to 32 channel detections. We have already installed one system in NPL recently for this counter system. So now we are expanding our product line to the lasers. So this is one of our new company called Mersens. This is from France. So this company can give you quantum cascade laser, which can serve 10 micron to 21 micron. So this 10 micron to 21 micron range, now it's a new laser wavelengths for the scientists. So the main advantage for this quantum cascade laser, when you have 10 micron to 21 micron wavelength range, the absorption rays that are very stronger in that region. Also, there will be less crosstalk interference from other molecules. So you can get a better absorption spectra or emission spectra when you use these kind of lasers. And specifically for the nuclear safeguards, we have a perfect detection wavelength that is 628 centimeter inverse. Also, this wavelength you can use for the gas and gas spectroscopies like benzene, toluene, or hydrogen cyanide, propane, etc. So this product does not need any ITR clearance. It's from France. Also, we are now serving with a new company called Phyla from Spain. This company can provide superconducting lasers with the higher repetition rate of 100 megahertz, and the stability is better than 0.5%. This is the best stability you can get it in the market with the higher repetition rate. Also, we are already working with Sahar laser
for the ECDL setup. So we can provide you MOPA or type amplifier systems up to. This is a new proprietary laser from Zahar Laser. So this is a volume Braggs grating laser. The speciality is this is a very low cost laser for the application of rubidium, calcium, strontium, or any kind of ion cooling trapping spectroscopies. So usually whenever you go for these kind of applications, rubidium, calcium, strontium cooling spectroscopies, you need a little bit more power. So whenever you go for a more power, you need basically the systems will be expensive, but this is an alternative for expensive system, and it can give the same all characteristics of a normal external cavity laser. The only difference is this one does not have much tunability, but all other characteristics are very narrow line width up to below 15 kilohertz. And this is a monolithic structure, so there is no mechanical cavity resonance, low temperature drift, and it can be portable system also. We can give in package. So this is the beam characteristics for the micron PPG lasers. You can see power 300 more than 300 milliwatt. We can give it 780 nanometer perfect wavelength for the rubidium spectroscopy and very low temperature drift. The tuning range will be very less. So if you know your absorption line exactly, then this will be a perfect choice for you. And the line width is very narrow. It is below 15 kilohertz. This system can cost approximately 10 lakhs only. Usually the ECDL setup will cost you 50 or 40 lakhs. So this is a perfect alternative for the spectroscopy applications. Also, we are now moved to the pulse lasers. Also, we have now nanosecond and picosecond lasers, on femtosecond lasers also. So we have working with prospective imaging. They are providing the femtosecond fiber lasers. We have fixed wavelengths. Also, we have the tunable wavelengths from 750 to 1040. The pulse duration is more than 100 femtosecond. Also, we have two other companies, Valo Innovation and Phyla. So they are specialized in ultra short femtosecond lasers. So Phyla can give 15 femtosecond pulse width, and Valo Innovation is specialized in 50 femtosecond pulse width. So if any kind of requirement, you can contact us now. So thank you very much for the time.
Thanks, Dr. Anil.
Yeah, small correction. I'm not doctor. You can call it Mr.
I request you, if you have any indigenous product,
yes,
make in India product, then ILA will display it on its website. ILA is going for all the make in India even products to display it on its website. So I request you to give all such products detail to ILA as information.
Yes, thank you very much, sir. We will do. We are already in collaboration with different institutes, but it's on in the process actually. Once we get the details, we will give you, sir.
Okay, thanks. Thank you very much. Our next presenter is Mr. Ankit Singhal from Laser Science Services Private Limited, Mumbai. And Laser Science Services Mumbai was founded in year 1988 by Dr. Lalit Kumar. And today it represents the more than 20 leading laser manufacturers. So not going in much detail, I invite Mr. Ankit for his presentation. Mr. Ankit.
Good afternoon, everyone. Good afternoon, everyone. Welcome all the dignitaries and friends to NLS. I would like to thank NLS, the committee member, to invite Laser Science to be a partner of this, and would like to thanks everyone in this committee. Now, laser science, most of you know that we're a leading supplier of laser and photonics equipments. So it is founded by Dr. Lalit Kumar in 1988. As you know, he has done his PhD from IIT Mumbai. And recently we have added one more wing to our company for the industrial solutions, that is CLI, Coherent Laser India, and it is started in 2017. So this is our building in Navi Mumbai at Mahape. So in laser science, we are one of the leading supplier of scientific and industrial lasers, spectroscopy system, microscopy system, other characterization systems, just like AFM system, Raman spectroscopy. We are imaging, high-speed imaging, in terahertz imaging also. We have quite few solutions for all the scientific and industrial requirements. So our vision is to give the best system possible to the scientist and to the industry. So along with the product, we always believe that the quality service also must be associated to any of the instrument. So we are giving utmost priority to service. So we have a team of more than 10 service engineers with us who is providing all the on-field service to the customers. So as you can see, we are in this field since last 30 years. You can find almost all the institutes, R&D institutes, we have provided a system, just like all the IITs, all the DA units, Department of Atomic Center units, then DRDO labs, ISRO labs, Department of Biotechnology, the labs for that, and various of other R&D institutes, just like ICER, CSOI labs, NICER, and other state universities. So this is our team, you can see. So we have more than 30 people working with us. We have quite a professional company segregating all the divisions: sales, servicing, marketing, order processing, and accounts. So we can see, and we have hiring and topmost scholars from PhD and who has done MS from other countries to enhance our product portfolio and provide good service to the customers. So coming to the product part, so as described earlier, we are presenting more than 20 companies all over the world who are the best in their field. Some of these companies are Thales, Coherent, Benek, PCO, Optosigma, Whiterun, Delight, Radiance Optics, Donggu. So these are the companies who are dealing with. I'd like to say few product from each of the companies. Just like I would say Thales, they are providing the petawatt system, particularly if I say, although they have quite wide product in other sectors, but for our segment, we are dealing with the petawatt system particularly, and one such system already installed in RRCAT Indore. Then Coherent, it's a very familiar company for all of us, you know, so who is one of the biggest manufacturer of laser and photonics components in the world. So they are giving just from every single diode laser to complex femtosecond laser systems. So you have any diode laser, gas laser, excimer laser, then femtosecond laser, oscillator systems, femtosecond amplifier systems. We have everything under our portfolio. Then if you need any components, optics, mechanical components, then we have Optosigma with us. Then for imaging, we have PCO, and for if you need any atomic layer deposition system, we have Benek and Radiance for the solution. Then we have Dell systems, Litron, Leoptech, AP, Festech, Class 5. This particular Class 5 is dealing with quite high power laser system, particularly in OPCPA type of laser system. Then we have streak camera, then ALD system, PLD system, then Moog bifringence measurement system, Simrock, the famous company for the filters, and Kimon for HECD laser system. So these are actually, if you see the product, we have more than 10,000 product. If you see all the companies, we have more than 10,000 product. So if you feel anything to buy from us, please feel to write to us. So these are some of the key achievement we have achieved in past years. So one of the achievement is, as I said, it's a petawatt system installed in Arakat, Indore. It is supplied by Thales, and of course, it is the in charge is Dr. Chakera, who is also a part of this NLS. Then another complex CEP system, PRL Ahmedabad. I can say it's a very proud to say that we laser science have installed this CEP system by our capability without taking support of the principal company, that is Coherent. So this is the kind of service expertise we have. So I can say that we have cumulative of more than 60 years experience of our service capabilities. Then this is a in-house development, you can say, welding and cladding system. Along with we have integrated all the parts at our end and supplied a welding and cladding system in IIT Hyderabad. You can see a picture of the complex system as well. So apart of this achievement, we have various other things in past years, just like a terawatt system in TFR, then some LIDAR system, then amplifier system in TRFI Mumbai. These are the few systems which laser science has brought to India for the first time. Then there are also some in-house activities going on in laser science just to cater the Make in India process. We are also focusing in that part of the segment in which we can provide the industrial solution and the scientific people also, the indigenously developed systems. These are some laser cutting, welding and marking machines which are developed by ourselves in our company. These are some of the examples of our research and development activities. So if you have any inquiries or any requirement, please feel free to contact us in the following email ID and contact number. Thank you.
Thanks, Mr. Ankit. Laser Science Mumbai is a pioneer, founder member as a corporate member of the ILA. And Laser Science Mumbai also sponsors the Best Poster Award in the National Laser Symposium.
Our pleasure.
So we again acknowledge thanks from Indian Laser Association to Dr. Lalit Kumar and Laser Science Mumbai. Thanks for your presentation.
Thank you.
If you have any indigenous products which you want to display on ILA website under the Make in India, so please share the details of those things to ILA.
Sure, sir. We do have some indigenously developed product, which I have
Yeah.
already shown in my slide. Surely
Yeah.
we can give such item detail to ILA so that it would be marketed very well.
Yeah. Thanks.
Thank you. Thank you, sir. Thank you, everyone.
Thanks, Ankit. Our next presenter from industry is New Age Instruments Private Limited, and Mr. Prashast Chalda is joining us. Hi, Prashast.
Hello, am I audible?
Yeah.
Shall we start? Hello?
Yeah, please start.
Good. Hello, Prakash. Hello.
Yes. So, good afternoon, ladies and gentlemen.
So
My name is Prashash Sharda, and I am here to present on behalf of New Age Instruments and Material Private Limited. And before everything, I would like to thank NLS for providing us with this opportunity to speak in front of, to speak in this symposium. For the first slide, we at New Age have a pan-India presence with offices in Delhi, Mumbai, Bangalore, and Hyderabad. We comprise of a young team of 45 to 55 strong technocrats, which have a perfect blend of young as well as experienced technical team who are spread pan-India and are able to provide a solution to our customers as well as to be able to find the best fit for our overseas partners product to meet the research and application need. We cater to everything from delivering components to subsystems and from a process. Now you may ask us, what sets us apart from a plethora of private Indian companies in the scientific field? Well, to begin, we are part of a very few companies that have a dedicated R&D team that have been duly recognized by DSIR as a private funded R&D group. We also have been certified for quality management by International Organization for Standardization. In the following slides, I'm going to walk you through some of our projects as an industrial partner with government labs such as DRDO and even BARC, and some of the off-shelf products that we offer related to the field of optics and laser. About our R&D section, it is called New Age Research and Development Organization, and it was started in 2013 by Mr. Samir Sharda, who is a master's in lasers and modern optics, and has been working with New Age since its inception. And the focus of this group is innovation. And NARD, as on start of 2022, is a team of 18 dedicated R&D engineers who have experience and exposure in the field of lasers, spectroscopy, optical designing, fast detectors, embedded electronics, software design, and mechanical designing. Our team now has PhDs, MScs, MTech, BTech, and diploma engineering in the field of laser and modern optics. Now I'll start off with a few projects that we have done with the various research institute as part of our collaboration. The first is the spectral analysis of IR absorptive surfaces. This project involves the study of how angles of reflection of topography of surface and its texture can affect the overall reflection measurement. This also involved setting up of a test facility to achieve detector training of complete sensing mechanism. What we offered was 6-channel system with a resolution of 0.03 to 0.08 nanometers and covering wavelength from 250 to 800 nanometers. We also designed a fiber optic coupling module to couple max light to the spectroscopy channels. Now on to the next slide. Our next project was a plasma and spectral analysis for trace elements. This project became a starting point in developing solutions in the field of elemental, molecular, and trace gas analysis. We developed the algorithms, UI, the user interface, and the electronics involving nanosecond level gating and delay generator circuits to do the time-dependent studies. And all this was done in-house by our own R&D department. The next up is the lifetime measurement system. In this, it required the fluorescence lifetime spectroscopy investigating the changes in fluorescence over time of a sample when irradiated with a pulsed UV, visible, or even near NIR light. This decay in fluorescence can be measured over a wide time range. from picoseconds to milliseconds and even beyond that. Next up is the standoff bioagent detector. This system was designed to detect the presence of unusual increase or change in bioagent presence in an air cloud from a safe distance of 500 meters. It involved designing of gated PMTs sensor to not only dig out the fluorescent signal in broad daylight, but also using the same sensor to find the distance of that cloud. And this has been quite an achievement for us as it has not been done in India before us. Our next up is a 6-channel laser ignition system. The aim of this project was to develop a multi-channel laser-based primary charge igniter. Our team developed a military-grade 6-channel fiber-coupled laser diode firing unit that was able to ignite the primary charge, and the user was given a flexibility to vary the parameters like the laser power, the duration, and set a delay between all the different channels. And in this project, we developed our own UI as well as our own laser diode circuits, driver circuits. These are some of our products that we have developed in-house as part of our R&D group and under the Make in India initiative. The first is the Lumen High Power LED. It has a cluster which can provide up to 10 watts of optical power with a wavelength from 275 to 850 nanometers as per the customer requirements. Next up is the Lumen Hall Plus. It is a multi-utility light source having inbuilt an halogen lamp, one LED, and an external port for additional source. It has an inbuilt cuvette holder for doing the measurement on the system itself. Our next is the Lumen LED Star. Our multi-channel LED sources covering wide spectrum from 275 to 2000 nanometers. The user can select for up to 4 channels to 8 channels and select his different wavelength ranges, and it can be provided with its own UI and on the system itself. Next up is the Lumen LCX LED light controller. It is a multi-channel controller having 4 to 8 channels, and it gives the full freedom to user to operate the LEDs or lasers even in pulsed or CW mode. And the user can vary the power, rep rate, and the duty cycle to suit their experiment needs. Our next up is our Seeker module. These can be used to detect ultra-low light signals as well as the fast detection of optical signals in nanosecond time domain. More about this will be discussed later in the presentation. Our Infinity series includes some of our detector laser diode drivers and even a PSD module, which can be used to monitor laser beam jitters and sensing the position of the laser spot with an accuracy of 2 micrometers, less than 2 micrometers. Next up is our ERA-SM spectroscopy module for performing vast applications. It is a portable system with its own UI and a touchscreen, and which has its own inbuilt battery, making it more reliable for the field. This is our ERA-SM spectroscopy module. It is itself in a standalone unit with its own circuitry and the UI, and it can be used for various applications like LIBS monitoring, absorption spectroscopy, transmission, reflection, fluorescence, and even plasma analysis. Next up is our Infinity series of laser diode drivers. Our laser diode drivers can be used to precisely control the laser's optical output while protecting the laser's diode from overcurrent, overtemperature conditions.
2 minutes.
To complement. Excuse me?
2 minutes more.
Okay. I'll hurry up then. Next up is a macro power laser powered energy display unit. This can be used to measure this. A macro is a user friendly display unit where the user just needs to plug and play with the plug and play system, and wherein the user can plug in the sensor and and have entire laser power energy measurement capability at its fingertips. This system has its own laser tuning, data logging, graphing, normalizing, and power of energy density attenuation scaling features as well. Next up is our muzzle flash detector. It is based on the principle of electro-optic principle, and this system has a saturation level indicator that can be controlled using gain control knob, and thus it can be used in different environments. And we can proudly say that this system was supplied to PXC Chandipur as well. Next up is our Seeker series detector modules. We have a wide range of detector modules such as APD, balanced photodiodes, position sensing detectors, PMT modules, and even silicon pin photodiodes as well. The detectors are available in high speed versions with different gain to suit the user applications. Next up is our Raman systems. We have various Raman systems for applications in chemical, explosive, narcotics, gemology, and even scientific research. We have a portable Raman system, a handheld Raman system, a Raman system for free space, and a micro Raman system as well, as per the user applications. Some of our Hawk Raman clients are DRDO, IB, and IIT Delhi, and BARC as well. Next up is our LED solar simulator. Our LED solar simulator has a wavelength range from 365 nanometers to 1050 nanometers, and our total power output can be seen from 10 mm from the surface, and it can even be used as a tunable light source using single wavelengths for single wavelength applications as well. All these products have been designed by a team indigenously in-house, and all products that we developed are import substitute. All these systems are tested and supplied by reputed organizations like DRDO, ISRO, CSIO, DIE Labs, IIT, and NITs, and other government and private organizations as well. We have more than 20 years of experience in spectroscopy, high-power laser diagnostics, emission, and detection studies as well. So if you have any questions regarding or any queries, feel free to ask me. Thank you.
Thanks for the nice presentation on your product details.
Yes.
If you have all such indigenous products can be displayed on ILA website. So please share the details of these
Yes, sure, sir.
To ILA. I again thank you for your nice presentation. If you have any query, then we will ask on your email address given in the website and the exhibition corner also. Thanks for now.
Thank you. Thank you.
Okay.
We thank you, sir, for chairing this session. And now we end the session of industrial presentation. And our next session will start at 5:30.
Okay.
Thank you, sir.
Thanks, madam. Thanks.
Hello all the participants. Welcome back to our next session, which is the last session of today's events. And this session is on nonlinear optics. It will be chaired by Dr. Alok Ray. Dr. Alok K. Ray is a Rajaramanna Fellow, BARC, and Senior Professor, Chemical Sciences, HBNI, Mumbai. He retired as an outstanding scientist and head Project RIS BARC during November 2018. His current interests include societal applications of fluorescent dyes and graphene quantum dots in selective and sensitive sensing of trace toxic chemicals in portable water and physiological aqueous media. So I request Dr. Alok Ray to please take the session forward. Over to you, sir.
You, Dr. Asaudi. Here in this session, we have one very experienced professor, and second speaker is a relatively younger speaker. Both are on nonlinear optics and its application in photonics and lasers. First speaker is Professor Pratima Sen. Professor Sen had the opportunity of working at the prestigious Heriot-Watt University, Edinburgh, after submitting her PhD thesis in 1980. After that, during 80 to 1990, during 10 years, she has worked as research associate in different Indian universities. And finally, in 1990, she joined research scientist scheme and worked as research reader finally in the Sri GS Institute of Science and Technology, Indore. And then she worked as professor of physics at Devi Ahilya University, Indore from 2006 till her superannuation in July 2021. Her research interests, of course, include nonlinear optics and related areas, quantum computing, and she has guided 14 research scholars to complete their PhD under her supervision. She is a very good teacher and guided many project students. So without wasting much time, actually, I request her to present her lectures. Professor Sen.
Hello. Yes, hello.
Share your,
yes, I am sharing my PPT.
Please.
Can you see it? Hello? I'm sharing my PPT.
Still not on the screen.
It is not on the screen. Suddenly my camera has stopped working.
Ma'am, you have to again share it from the WebEx platform. The PPT open on your computer needs to be shared from WebEx.
Yes, I'm sharing it from the... Am I visible?
No, not till now.
Am I visible?
Yeah, your voice is coming only, but you're also not visible.
Okay. So maybe the problem is with the camera?
Professor Sen, you have to start your video. Right now it's off.
It says that we cannot display your video.
At least share the PPT.
It is at the bottom.
Maybe
yes.
At least you share your PPT. Your voice is clear. You can see your voice, listen your.
Yes. Oh. I don't know why this is not working.
Can you tell?
But am I audible?
Yes. Your voice is very clear. So you can share your PPT, madam. Then maybe video part we can.
Madam, there is a share button
Yes.
on the bottom of your screen. Can you click on
Yes,
that?
yes, yes. Yes.
If you click on that, a window will pop up wherein you will be able to see the presentation which.
Yes, it is coming now.
Yeah.
Yes.
Can you just put it? Ma'am, can you just select the presentation?
Yes, please.
Yeah.
Yeah, it is coming.
Now, can you
Is
just
it visible?
start the presentation? Yeah,
Yes.
it is visible. Can you just start the presentation, start the slideshow?
Sure, sure. Sure, 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 sure. Thank you, sir.
Yes, ma'am. Please.
So good evening to all of you. First of all, I am really very thankful to the management for giving me this opportunity to talk on the topic of my interest, that is nonlinear optics. In particular, I am really thankful to Dr. Mukesh Shah for this purpose. And I am in touch with nonlinear optics since my inception in research. And that is why I thought of talking about it right from its infancy to its blooming youth. So, at the time of my inception in research, why did I study nonlinear optics? I did not know, because my supervisor told me to study nonlinear optics. So I did it. But later on, with respect to time, I came to know that it gives us amazingly new phenomena. There is a lot of understanding of fundamental physics. It leads to important applications, starting from everyday life up to specialized ones. Now, the year 2022 marks 61st year of birth of nonlinear optics, soon after the demonstration of first ruby laser in 1960. In fact, 61st year is one of the remarkable years in our culture. It is actually the intense electric field at optical frequency that we get by lasers, which leads to optical nonlinearities. The optical nonlinearities are capable of amplifying the laser intensities, and in turn, nonlinear optics grows because we get advanced source intensities. In fact, if we put a nonlinear optical element within the laser cavity, then it is possible to make diversity of new lasers in terms of generating new frequencies and making pulsed lasers. Actually, it appears to be a cyclic process. Like, because of large intensity, we get nonlinear optical effects. Because of nonlinear optical effects, we get amplification. And again, because of amplification, we get large intensities, and so on and so forth. So the first recognition of optical nonlinearity was the observation of second harmonic generation by Peter Franken and his team in 1961. He was from Michigan University, and in one of the alumni memoir in the alumni meeting, he said that when I came to know about lasers, I thought that they are really fantastic sources, and my mind started doodling calculations, and I could find that the lasers can generate electric field amplitudes of the order of 100,000 volts per centimeter, which is not far away from the interatomic field. Then how the matter would react to it? He carried on with the perturbation calculations and found that there is a possibility of second harmonic generation. He rented a Luby laser, and he, along with his team of researchers, could observe a weak blue spot at the second harmonic frequency. The paper was then submitted for publication to physical regulators. It was accepted. The paper was showing a bright spot at ruby frequency, that means at red spot, and a blue spot at the second harmonic frequency. But when it went for the printing, the lithographer thought that the blue spot is very weak and probably it is some noise. So he successfully and meticulously removed the dot. And the journal published the paper about the dot without the dot. And that was the marking of the birth of nonlinear optics. Since then, the developments in the field were phenomenal. It is appropriate to remember the genesis of the field and the remarkable progress made in the first few years. It is unjust to not to mention about the celebrated ABDP paper from Harvard University. That was a paper by Armstrong, Blambergen, Duquesne, and Persson, And it told about how many types of nonlinear optical interactions can be seen. It was a theoretical paper, but simultaneously many papers came out in the same year. It was optical rectification and optical mixing, harmonic generation, and giant optical pulsations from Ruby, through which we could make Q switching of lasers, which enabled laser pulses in 20 to 50 nanosecond range, with peak powers of megawatts to be generated. The attendant increase in peak power had an immediate impact on the efficiency of nonlinear interactions. Then, stimulated Raman scattering phenomena related Ruby laser operation in the IR regime, self-trapping of optical beams, intensity-dependent changes in refractive index of liquids, stimulated Raman and Brillouin scattering, tunable coherent parametric oscillations. The list is long, 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 and very, very long, but I am stopping at 1965. Today, it shows that how a tightly focused laser beam can generate new offshoot beams at various wavelengths which originally did not exist. It has paved the way to generate lasers across the rainbow and beyond. It is helping us to recognize the nature of nature. One can generate comb frequencies useful in time measurement. It has also enabled scientists to generate pulses as short as attoseconds. And in fiber optic communication, we can amplify signals such that they can travel thousands of kilometers without degradation. Ground-based telescopes use nonlinear optical technique to get blurless images due to Earth's atmosphere, and it enables us to squeeze light below the short noise limit. In fact, the impact of NLO on science is widely understood, at least by those who are working in the field. It has led to many, many Nobel Prize winning sciences and world changing engineering. When I think about its spectrum, it varies from deep infrared up to extreme UV. In which kinds of materials it can be observed? Then the span is from bulk materials up to the quantum structures. In all these materials, the nonlinear optical effects can be observed. So, what this nonlinear optics is all about? As soon as the word optics comes to my mind, it is nothing but a replication of the interaction of radiation and matter. But the fact is, if the electric field amplitude of the radiation is very small in comparison to intra-atomic field, then we see linear optics, a simple reflection, refraction, absorption phenomena, how lenses they work. And on the other hand, if the electric field amplitude is comparable to the intra-atomic field, then we see nonlinear optical phenomena like multiple wave mixing, harmonic generation, nonlinear refraction, nonlinear absorption, etc. But it is not only the electric field amplitude that matters. It is also the time of interaction that matters. If the interaction time is very, very large in comparison to the dephasing time, then we see steady state phenomena. And if the interaction time is of the order of dephasing time, then we see phenomena like coherent transient effects, optical nutation, photon echo, self-induced transparency, etc., etc. But what is eye-catching to a common man is the intensity-dependent refractive index, because that means we can control the velocity of light. The group velocity of light can be made very, very small in comparison to the velocity of standard velocity of light c, whereas it can be made faster than the velocity of light. So the light speed reduction to 17 meters per second in an ultra-cold atomic gas was reported as early as 1999 in Nature. Another effect that is nonlinear optics, steady-state effect I will be concentrating on. It is the study of how intensely light interacts with matter. Actually, the intense interaction is always in two ways. Either the light has a very large intensity, or else it resonates with the system in some way or other. In a normal interaction, the optical response usually scales linearly with the amplitude. As you can see in this figure, that if the input intensity is small, then output intensity linearly varies with the input intensity. But if the input intensity becomes large, then you can see a small curvature. The optical effects that we can see is, as I said, second harmonic generation, we are putting in the red light and getting out a blue light at 2 omega frequency, and the omega frequency of course comes out. And similarly, if there is a Gaussian beam, then it automatically gets focused when it passes through the nonlinear optical medium, or it may get diverged due to the nonlinear optical medium. This is called as self-focusing and self-defocusing phenomena. Now, what has triggered the phenomenal growth in the field of nonlinear optics? The founding pillars of nonlinear optics are definitely radiation and matter. So if the nonlinear optics has to grow, that means there has to be an advancement in the radiation sources, as well as there has to be an advancement in matter. As long as advancements in radiations are concerned, we can get lasers at various frequencies, we can get pulsed lasers, which give rise to very large intensities, we can get better coherence. And as far as matter is concerned, we started with bulk materials like semiconductors, transition metals, conjugate polymers, nanostructures, waveguides, optical fibers, graphene, carbon nanotubes, and recently near epsilon zero materials. So because of all these developments in radiation and matter, we have got phenomenal growth in the field of nonlinear optics. But in each kind of material, the mechanism of optical nonlinearity is different. So if I talk about bulk materials, then in fact in these materials, the transition frequencies can be modified by suitable doping. And as I said, the nonlinearity directly depends upon the resonance. So we can get resonances at different frequencies, and so at different frequencies the nonlinearities could be observed. In case of optical fibers, although the nonlinearity is not much too large, but because of long interaction lengths at the end of the fiber, we find that there is sufficient changes due to nonlinear optical effects. In conjugate polymers, it is highly charged correlated virtual excitations. In case of nanostructures, the size-dependent transition frequencies, surface effects, they become important. In heterostructures, the photon confinement plays an important role. And in case of carbon nanotubes, graphene, etc., the researches have been made, and we find that there is reverse saturable absorption, free carrier absorption, as well as thermal nonlinearity occurs in these materials. In photonic crystal fibers, high index difference between the silica core and the air-filled microstructure enables tight mode confinement, and which results into low effective area and thereby a high nonlinear coefficient. In epsilon near zero materials, as the name suggests, nonlinearity is inversely proportional to the refractive index. And in case of quantum confined structures, apart from the photons, the electrons are also confined, and that gives rise to large optical nonlinearities. So I would like to say a few more words on nonlinear optics in micro, nano, and quantum structures. In case of microstructures, I would talk about composite materials. In the composite materials, the field distribution inside the composite is non-uniform, and it is possible to concentrate the field in specific locations, which enhances the optical nonlinearity. As a matter of fact, a composite material can display larger nonlinear response than its constituents. In nanostructures, if the size of the particle is reduced below the mode volume, then the optical properties are monitored according to the size due to surface effects. The mode confinement gives rise to resonant cavity type of effects and results in field enhancement, suppression or enhancement of spontaneous emission, etc. In case of quantum structures, along with photon confinement, electrons are also confined, and thereby absorption of photon gives rise to electron pair called as excitons. The excitons are analogous to hydrogen atoms, and they exhibit optical properties similar to that of the atoms. When I talk about nonlinear optics in optical fibers, I think the first thing that comes to our mind is dispersion, because dispersion was the biggest challenge in nonlinear, in long distance optical communication systems. So when we talk about optical nonlinearities, the optical nonlinearity adds to the dispersion. But thanks to scientific community that they have converted this challenge to opportunity and have shown that both the enhanced and the reduced dispersion lead to constructive effects. The pulse propagation in optical fiber is described by nonlinear Schrodinger equation, which comprises of both group velocity dispersion as well as self-phase modulation. If both these effects, they add to each other, then we get enhanced dispersion. But if both these effects, they compensate each other, then we see the phenomena of solitron propagation. A solitron is the one which propagates long distances without any dispersion. So there is a picture taken from this NPTEL lectures, and here we can very well see that in normal dispersion regime, the dispersion due to group velocity dispersion as well as due to self-phase modulation, they are in the same sense, and therefore they add each other. And due to this, there is enhanced broadening of the pulses. And that in case of self-phase modulation, new frequencies are generated. And that leads to a very novel phenomenon which is called as supercontinuum generation. I will talk about it later in my talk. Another one is anomalous dispersion. In case of anomalous dispersion regime, the dispersion in group velocity is in an opposite direction to that of the self-phase modulation. With the result, the total dispersion is compensated and we get the solitons or the propagation. So, because of the enhanced dispersion, we get supercontinuum generation. There is spectral broadening and generation of new frequency components, which are the inherent feature of nonlinear optics. Apart from this, how nonlinear optics has impacted present-day science and technology can be directly seen because nonlinear refraction and absorption, they have led to the phenomena of optical bistability, which gives rise to optical switches, optical memory elements, and we can think about all optical computers. Four-way mixing, another nonlinear optical phenomena, it gives rise to optical phase conjugation, and because of that, we can get blurless images. Multiphoton absorption, again, a nonlinear optical phenomena. It leads to ionization at the focus of the laser beam and localized plasma. The localized plasma vaporizes the target, removing the material, and that has made possible micro machining with femtosecond pulses. And because of that, we can get micro electromechanical systems. Stimulated Raman spectroscopy enables to observe spectral changes associated with cancer cells, and that has given rise to real-time automated identification of skin cancer. I have given very few applications of nonlinear optics because of the paucity of time. And now I would like to talk about a tiny amount of work that has been done by our group. First of all, my tribute to Professor P.K. Singh, who was the founding member, and he expired last April only. Actually, I appreciate him so much because to do research in universities, to do research in research institutions is quite possible. But to develop a work culture and to develop a research attitude in colleges is really remarkable. And that was done by Professor P.K. Singh. And by now, there are around 50 students who are now in very good positions and are performing their researches in the field of nonlinear optics. These are all the names of their group members. And due to these many group members, we could touch upon many nonlinear optical related phenomena. We studied coherent transient effects, optical nonlinearities in quantum confined structures, in fibers, squeeze state generation, optical nonlinearities in conjugate polymers, in metamaterials, in transition metal oxides, in 2,6 semiconductor thin films, in solid state plasma, stimulated Raman and Brillouin scattering in 3,5 semiconductors, third order optical nonlinearities due to excitons, nonlinearities in presence of magnetic field, so on and so forth. But I would be concentrating on a very small area. Basically, optical nonlinearities mainly concentrate on second and third order optical nonlinearities corresponding to three-way mixing and four-way mixing. I'm talking about third order four-way mixing phenomena, where there are possibilities of non-degenerate four-way mixing and degenerate four-way mixing. I'm talking about degenerate Fourier mixing, which leads to intensity-dependent refraction and absorption. The intensity-dependent refraction and absorption was studied by our group. We studied both its theoretical aspect and experimentally also we have determined it. For theoretical aspect, we used density matrix analysis as well as time-dependent perturbation technique to study optical nonlinearities in quantum confined structures as well as in optical fibers. And in experimental determination, we used Z-scan technique to study optical nonlinearity in bulk materials like lithium niobate, which was developed in RRCat Indore, and in other thin films which were developed in UGC DAE-CSR Indore Consortium. And we are very thankful to both the institutions because it was because of them that we could develop the samples and could characterize them. And we studied them, and I'm just giving the experimental setup that we had in our laboratory, that was Z-scan setup. This gives both the closed aperture as well as the open aperture detection. In closed aperture, we get peak and valley kind of structures in the output, whereas in the open aperture, we get a valley, either valley or the peak kind of a structure. What is done is the sample is moved across the focal point and the intensity variations are detected. So this was the one that we had used, and the number of samples are very many. Some of them are zinc oxide with various dopants, graphene, then graphene as grown, as well as anil graphene layers, undoped and doped chromium oxides, as well as nickel oxide. All these white ones were developed using pulse laser beam deposition technique, and all these ones, they were developed by using ion beam sputtering technique. So they are TiO2 films as deposited, annealed, as well as nickel oxide films, and so on and so forth. So these were very few things that I wanted to talk about my own, because the area is very vast and I wanted to cover as much as possible. Although nonlinear optics in itself did not get any kind of Nobel Prize. Of course, always the founding stones, they don't get any recognition. It is what comes up that gets the recognition, whether we talk about Taj Mahal or any other structure. So I'm talking about the Nobel Prize which are related to nonlinear optics, or which used nonlinear optical techniques for it. So in 1964, it was about the fundamental work in the field of quantum electronics. And in 66, development of optical methods for studying Hertzian resonances in atoms. In 81, development of laser spectroscopy. In 97, development of methods to cool and trap atoms with laser light. In 2000, developing semiconductor heterostructures used in high-speed optoelectronics. In 2005, quantum theory of optical coherence and development of frequency comb technique. In 2009, transmission of light in fibers for optical communication. In 2014, efficient blue light emitting diodes. In 17, LIGO detector and observation of gravitational waves. And in 2018, Ashkin, who did work on optical tweezers and their applications to biological systems, and Morrow and Strickland, generating high-intensity ultra-short optical pulses. I will tell two more words on the second one, that is generating high-intensity ultra-short optical pulses. The other one, optical tweezers, were already discussed in today's earlier session by Dr. Banerjee. So now, for generating high-intensity ultra-short optical pulses, initially ultra-short laser pulse is fired into optical fiber. So the first step of this is to stretch out the laser pulse. And then the stretched low intensity pulse is amplified into a stretched high intensity pulse. Later on, we compress this pulse and get nearly 10 to the power 15 watts of powers of the pulse, of the coming output pulse. Now this power is more than that generated in hundreds of large nuclear power plants combined. Scientists have used such lasers to generate plasma-like states of matter and for ultra-precise cutting and machining. Some new things where this span further goes is another new dimension is the event horizon. As soon as the fact horizon comes into my mind, I think that I cannot see beyond horizon. And that is what happens when a probe wave travels in presence of a soliton wave in an optical fiber. The refractive index variations due to soliton, they do not allow the probe to pass through it. With the result, the probe finds this soliton as the horizon. To the probe, the soliton boundary can thus appear as a horizon which light can neither enter nor escape, in analogy with the behavior at the boundary of a white or a black hole. This is intervention with the astronomy. This allows signature of horizon dynamics to be identified in the probe spectrum, where frequency up conversion occurs at a white hole horizon and frequency down conversion occurs at black hole horizon. This paper appeared in Nature Communications in 2014. Another dimension is the one the seafarers used to tell about the story of the giant waves that appear without warning in the high seas. They used to say that these mountainous waves were said to be capable of destroying the vessel or swallowing it beneath the surface. And then these waves used to suddenly disappear without the slightest trace. Initially, it was thought to be mythical. But in middle of 1990s, a freak waves proved very real when recorded for the first time by scientific measurements during encounter at Dropner oil platform in North Sea. These waves are called as oceanic rogue waves. The physics behind rogue waves is still under investigation, and the observation indicate that they are usually steep, solitary, and tightly grouped profiles which appear like walls of water. Now it is nature, and nonlinear optics is making us understand nature, because a similar situation can be created in optical fibers, in the propagation of waves in optical fibers, as well as these water waves. Both of them, they can be mathematically done by using nonlinear Schrodinger equation. So we can study the optical rogue waves and can simulate it with the water waves. So this is a remarkable expanse of nonlinear optics, and it indicates that it has a long way to reach its saturation limit and is increasingly becoming an interdisciplinary field of research. With this, I would like to say that nonlinear optics is as exciting today as it was 61 years ago. It is one of the founding stones of new research fields. It is helping us to understand the nature of nature. And there are many exciting features which are yet to be revealed. With this, I thank you all for your kind attention.
Thank you, madam, for very nice talk on the evolution of nonlinear optics and its present position and its scope in the future. What I think will be very useful for the many young colleagues who are working in this area or thinking to work in this area. So, any question from the audience? Madam, this advantage you told this, just I have one question, madam. This nanostructures, quantum structures, when you do the nonlinear optics, that is of the very exciting area. But for application, you need to have a conductivity, also good conductivity for the heat dissipation or the laser damage threshold. So that also are taking care.
Yes, you are very right. That is why, yes, that is why we are now looking for transparent semiconductors. And in fact, transitional metal oxides, they can be useful, they may be useful because they can be made transparent as well as conducting by using suitable dopants. And that is why in my just last year's paper, I have used nickel oxide and titanium oxide and all those kinds of things. The films were transparent, although we were still lacking on its conductivity, but yes, they are the promising candidate materials.
I think there is chat box also. If there is no other confusion, okay, madam, there is another question.
Madam, how SRS is used for the cancer detection? Can you please highlight something?
Actually, the cancer cells, uh, they have a slight difference than our normal cells. So with the result, the shift in the their Raman signal is different from the normal cells as compared to the cancer cells. So that is how we can find out this expanse of cancer cells, from which area the more shift is coming or the lesser shift is coming, that can be examined.
Okay, Madam, thank you. We are really very sorry to hear that Professor P.K. Sen, he expired last year, because always used to see both of you in NLS papers with that. Earlier we used to see, and that is a really you have to carry on with that in the life. But thank you, Madam, for all your future effort and for a good teacher as a for the many students there carrying that flags. Thank you, Madam, for
Thank you.
the talk
Thank
to
you so
NLS.
much. Thank you. Thank you so much.
Have a good
Thank
health.
you, Dr. Ray. Thank you so much.
Our next speaker is a relatively younger scientist, Dr. Someswara Rao. He'll be now talking on the application of nonlinear optics on lasers in optical parametric oscillator. Dr. Rao joined Laser and Plasma Technology Division BRC in the year 2001. He has been involved in the design and development of high average power tunable laser facility for the laser isotope separation project in BRC. He received DAE Group Achievement Award in 2011 for design and development of high power laser facility. He obtained his PhD from HBNI, and he has built and studied several broadband, narrowband OPO systems. Now his present interest to develop the high repetition rate, multi-kilohertz repetition rate, single longitudinal mode OPO and its application for the in spectroscopic study for the medical isotopes. Dr. Someswara Rao, please.
Sir, am I audible? Hello.
Continue.
Sir, am I audible?
You are
Yes,
audible.
Rao, please go ahead.
Uh, uh, Thank you, sir, for your kind introduction. First of all, I want to thank organizers for giving me this opportunity. My talk is all about recent development of high repetition rate optical parametric oscillators in our lab at BRC. My title of the talk is Development of Single Mode High Repetition Rate Visible Optical Parametric Oscillator and its Spectroscopic Application.
Dr. Rao, can you please go to full screen mode?
Okay. Okay. Yeah. It is visible.
Please put it in full screen and continue.
Put it in full screen mode and then please continue.
It is now coming in full screen.
Yeah, please go ahead.
Okay. I have outlined my presentation in the following way. First of all, I'll give introduction to optical parametric oscillators by giving some basics, and then I'll discuss about the issues in developing high repetition rate OPOs tunable in the visible region, and then I'll describe the development of high repetition rate BBO OPO, which is a new development, and then I'll discuss the single mode operation of the high repetition rate BBO, which is a new approach we have developed a new approach for achieving single mode operation in these devices. And then I'll talk about application of the SLM-OPO, developed SLM-OPO in the isotope separation studies of lutetium-176. If you see this picture, actually, you find lasers that have been developed over last 60 years. In the middle, you see the wavelength bar. Above this wavelength bar, you will find fixed wavelength lasers, and below the below the wavelength bar, you can see the tunable lasers. If you look at closely, there are wide gaps in which actually you don't find solid state tunable lasers. Only in at particular wavelength regions, like for example in UV region, and as well as in this visible region. Currently delivering high power. Currently, dye lasers are serving for this purpose. However, there exists another class of tunable lasers that they can widely tunable. At the same time, they are solid state in nature. They can deliver high powers as well. Uh, because they but unlike this conventional tunable lasers, they rely on nonlinear parametric process, which is transparent, which is instantaneous in nature. So we can operate these OPOs all the way from CW to nanosecond, picosecond, femtosecond time domains. This is the picture that I want to compare the tunable lasers and the OPOs. Bottom you will see the tunable lasers. These conventional tunable lasers, most of them are laboratory based. They are not commercially available. Only this titanium sapphire, which is a solid state in nature, and then they can it is a viable laser, and then it is commercially available. If you look at the dye laser, dye laser is ubiquitous. It can find everywhere, but it is limited by wavelength tunability. You can tune only few nanometers, 20 to 25 nanometer. If you want to cover the entire visible region, you need at least 20 dice, 10 dice, sorry. On the other hand, these OPOs, they have this technology. The OPOs technology has been matured to a point where you can find, you can tune the lot of extremely large spectral coverage with a single device. And also it can access to different spectral regions not available to lasers. So what is the basic mechanism behind this OPOs? Actually, if you see, the basic mechanism is when a high intense laser passes through a nonlinear second order nonlinear crystal, it will generate additional two frequencies, which is called signal and idler, following the conservation rule. The momentum conservation, which selects the a particular pair of frequencies to get pair of signal and idler pair that should get amplified out of this infinite possible signal and idler pairs. This also provides wavelength tuning, but just by altering the refractive index, you can tune to a wider wavelength. If you say the parametric gain, it is given by this equation. It is strongly dependent on phase matching condition, and as well as it also depends on the length of the crystal and the intensity with which we are putting in the crystal, and then the nonlinear coefficient d effective of this crystal. With the perfect phase matching, you can in fact you can achieve higher gains. The gain will might be exponential. So now how to achieve phase matching? The phase matching in normal condition without phase matching, the generated signal grows and couple backs to the pump laser without getting amplified with an interval of this coherence length. This coherent length is about 10 to 100 microns. How to disperse this is mainly because of dispersion of the material. How to offset this dispersion of the material is basically we have to use birefringence. This is one of the technique, birefringence of the anisotropic crystal. So but this in this anisotropic crystal actually the refractive index is not only dependent on the frequency, it also depends on the direction of propagation as well as the polarization state. So by judicious choice of this polarization state and direction of propagation and frequency, we can achieve phase matching. In BBO crystal, there are two allowed phase matching directions. One is type 1 phase matching, in which you can, if the signal and idler are polarized in polarized as a O rays. O ray is a ordinary wave. The refractive index surface of the O ray is a circle sphere. It doesn't depend on the direction of propagation, whereas the E ray the E ray depends on the direction of propagation. If that in type 2 phase matching, if the signal and idler are either of these either ordinary ray and extraordinary ray, then it is called type 2 phase matching. So this phase matching act as a filter actually. So if a pump beam passes through this crystal, if they are not phase matched, you will not the pump will not be depleted and you will not get anything of any signal or idler output. When they are perfectly when they are partially or you can start the signal and idler, so at the expense of pump, so you can achieve a gain in the signal. So there is a adverse effect associated with the walk-off, that the direction of propagation of ordinary waves and extraordinary waves is not collinear in birefringent crystal. Actually, if you see this picture, the extraordinary wave, the pointing vector is making an angle called, that angle is called walk-off angle. Because of this adverse nature, the pump beam, which is polarized as an extraordinary wave, start to deviate from the signal without efficient transfer of energy from pump to signal. So the distance over which the pump separates out from the signal is called aperture length. In case of BBO crystal, the aperture length will be around, if you focus the beam around with a beam waist of 200 micron, it will be around 4 mm. It is BBO crystal having larger walk-off angle. So the techniques for compensating this walk-off, we use cylindrical focusing. There are other methods also, but mainly cylindrical focusing seems to be effective. It will interaction length can be increased in cylindrical focusing. So what is so if you want to increase the parametric gain, you can give we have to give feedback to this parametric gain. For that, actually we have to put the crystal inside the cavity formed by two mirrors. We can give feedback to either signal or idler. So these OPOs are characterized by threshold actually. So above the threshold, the signal and idler dramatically increase from this pump laser. So by just tilting the crystal, the phase matching conditions will alter. From there, you can get can generate a tunable output. So there are among the various OPOs, actually nanosecond OPOs, type 2 BBO got got importance. It is it is established as a most practical OPO. It is used in various applications, right from the spectroscopy to industry. However, these OPOs are mainly restricted to low repetition rate. Suppose if you want to use it in Avelis process, these are not available because they are available only at a low repetition rate. We have constructed this OPO. We have generated a tunable output of 410 to 2700 nanometer tuning range, with an efficiency of 30%. So basically, what are the challenges that are impeding the development of this multi-kilohertz repetition rate OPOs? So if you see these OPOs, as I said, they exhibit high threshold fluence. If you calculate the threshold pulse energy, it will be around few tens of millijoule. So for narrowband operation, again the pulse energy requirement further goes up. It may be around 50 millijoule per pulse. So so we can tightly focus the pump beam to increase the to decrease the pulse energy requirement, but that is not possible. But it is counterproductive because large walk of just now I told it is because of large walk of losses. Pump will be getting lost without transferring energy, and also they have a very small acceptance angle. If you tightly focus, it will reach beyond the acceptance angle. These OPS also put stringent demands on the pump lasers for high spatial and temporal quality. If the quality, if there are irregularities in the spatial and temporal profiles, it may alter the phase matching conditions and degrade the performance of these OPOs. So such high quality UV pump lasers delivering such a high pulse energy at the multi-kilohertz repetition rates are not yet available. So these are restricted to only low repetition rate. So what is the solution? Then we thought of reducing this threshold pulse energy to 1 millijoule. That enables to pump these OPOs with the commercially available DPAC cells with the pulse energy having 2 to 3 millijoule. So for that we thought of using elliptical focusing to the pump laser. So in such a way that if you can maintain a larger beam size in the walk-off plane and tight focusing in the non-walk-off plane, we can we can increase the interaction length as well as we can maintain high intensity in the insensitive plane. And also this line focusing, the advantage of line focusing, it reduces the thermal gradients as well as it maintain a low power density at the crystal surfaces. That will benefit us. And also we thought of determining the optimum focused pump size for which the threshold pulse energy reduces to sub-millijoule, and at the same time the intensity must be much below the damage threshold. So for that we have developed a numerical model in which we have assumed the pump beam as a cylindrically focused beam with the major axis on the x-axis and the minor axis and the y-axis. This model has we have included the walk-off effects and the phase mismatch in this particular model. This pump and the signal, similarly the signal is also a cylindrical elliptical beam. So we have defined V ellipse. V ellipse is nothing but the ratio of beam waist size in the x-axis to the y-axis. If it is 1, it is a circular beam. If it is more than 1, it is a elliptical beam. So after writing this gain in the signal power in terms of spatial overlap coefficient, it will be it is as shown. We have achieved this figure, this equation. This HS is now dependent on the focusing parameters as well as the phase mismatch as well as the pump beam walk-off. So this HS, if we can evaluate with different parameters of pump beam, we can get the spatial overlap, how much spatial it is getting overlap, and subsequently we can calculate the threshold by substituting the HS value. Please visit this paper. All the parameters are listed in this paper. The coupling coefficient, the HS is maximized with respect to phase mismatch. That is called HSM. We have for different pump beam parameters, pump focusing parameters, we have plotted we have calculated the HSM value for different ellipticity of the pump beam. So we got if HSM is increased from if we have achieved a parametric gain of 12 if the ellipticity has increased some from circular to with a ellipticity of 25. So, but however, we find that at the focusing condition, the pump intensities are calculated to be at the focusing condition. The pump intensities are calculated to be approaching the damage threshold. So we thought of uh, we thought of calculating the threshold energy for a maximum size of the elliptical beam at which the threshold reduces to less than 1 millijoule. So for that we have programmed or we have calculated from our program. We have achieved a figure the elliptical pumps optimum size of 3.9 mm in the walk-off plane and 260 micron in the non-walk-off plane. With the we have calculated the intensity at this focusing size. It is much below the damage threshold, which is about 1 gigawatt per centimeter square. We have developed optical cylindrical focusing system. It is constituted. It is based on the cylindrical focal focusing telescopic lens system and a spherical lens. What it will do, it will compress the cylindrical focusing lens, compress the pump beam in the horizontal plane. The spherical lens focus the beam in the non-walk-off plane, so that we can achieve what we have calculated in the through our model. We have achieved a beam size of 4 mm in the walk-off plane and 250 micron in the non-walk-off plane. So this is the optical layout of our constructed OPO. The DPSL system it is giving a power of maximum pump power of 17 watt at 5 kilohertz repetition rate. Pulse width is around 10 nanosecond and repetition rate is 1 to 5 nanosecond. We have used a type 1 BBO in our OPO. This is the insert showing the how the pump beam is focused into the crystal. These results we have published in the journal. Please visit this journal. We are the first to demonstrate this high power high repetition rate operation in OPOs tunable, which are tunable in the visible region based on OPO crystal. These are the figures that I have taken when the OPO is operating at 492 nanometer, the left one, and 630 nanometer at the right one, extreme. The wavelength is limited to 490 to 630 is basically because we got broadband mirrors only particular for the particular wavelength only. So this is the power stability of the OPO. The stability is around power stability is around plus or minus 2%. But it is a broadband, it is a free running. There is no spectral reduction of spectral line width. The spectral line width varies from 0.2 to 0.6 within this range. But however, if you say that the theoretical calculation, it goes up to 10 nanometer if near degeneracy. BBO, this is the specification of our BBO system. BBO tuning range is 490 to 630 nanometer, maximum power of 2.5 watt. The efficiency is 25%, the pulse width is 6 nanosecond. So how to reduce the spectral line width? Then again the task comes. Actually, we have explored different type 2 phase matching, in which actually if you see the gain bandwidth of type 2 varies from 0.1 nanometer to 0.5 nanometer. Whereas for type 1 phase matching, the gain bandwidth varies from 0.15 to nanometer to 10 nanometer. However, in type 2 phase matching, the divergence broadening dominates the gain bandwidth. It is larger by 3 times, larger by a factor of 3. So if you can reduce the this divergence broadening, we can have a low spectral line width. So how to reduce the reduce the divergence broadening? So if you see how why this divergence broadening is coming in type 2 phase matching. If you see the wavelength shift curve, because of this extraordinary wave propagation of idler, the wavelength shift curve is not symmetric. It is showing it is asymmetric for a non-collinear angle. So the simple technique for achieving reducing this divergence broadening is double pass the pump beam. In double passing, what will happen if you say the forward non-collinear angle and the backward non-collinear angle, which are having different gain at different wavelengths. So they are having a gain at a different wavelengths. So in the double passing, only collinear waves will be amplified. The non-collinear having a different gain at gain at different wavelengths will vanish without getting amplified. So that way, the diverge. After passing the after putting the pump reflector, you'll see a much reduced divergence broadening. Now it is limited by only gain bandwidth of the uh, OPO. The spectral line width is only limited by the gain bandwidth. But the problem with the type 2 phase matching is they have a lower the effective coefficient. If you see the effective coefficient, the nonlinear coefficient decreases with the wavelength, and also when compared to type 1 phase matching, it is very less. And also the angular variation is only 10 degree is 3 to 4 nanometer degree in case of type 1, whereas in case of type 2 it is 10 degree. So we need a larger aperture size crystal, as well as a length, as well as a long crystal. So this type 1 BBO, we have used only 5 by 7 15 15 meter cube crystal, whereas type 2 we have increased our size 6 by 12 into 20 mm. So this type 2 is less efficient and having high threshold. So how to avoid this problem? Then we have checked the performance of type 2 based BBO OPO. We found that the crystal temperature, we found that at a repetition rate of above 3 kilohertz, the power is going down. Then we have monitored the crystal temperature, the temperature temperature gradients, actually, by imaging the crystal using a infrared imaging camera, and we have noticed the peak temperature. We have noticed that the thermal loading increased to a substantial amount. The thermal gradients in type 2 reaches a temperature tolerance limit of 16 Kelvin centimeter. So we thought of restricting the repetition rate to below 2 kilohertz in case of type 2 BBO OPO. So this is the plot showing the
Yes, sir.
uh,
Another
sir,
2 minutes, you should finish it. Okay, please try to complete.
sir, sir. So with the pump reflection in the with the pump reflection, we got a reduction in the reduction in the spectral line width, as well as the threshold. So that allows us to put fabric perodactylon inside the inside the cavity because the spectral line width has reduced and the threshold has reduced. This is the schematic of the single SLM OPO that we have developed in our lab. These are the spectral line width. These are the wavemeter pictures that we have screenshots of the wavemeter. The spectral line width is around that time average spectral line width is less than 250 megahertz for our BBO for our single mode OPO. This is the specification of our single mode OPO. Now coming to the application of this developed single SLM OPO for photoionization studies of lutetium-176. So this lutetium-177 is an excellent choice for radio targeted radionuclide therapy. The simultaneous emission of this beta beta rays which are used for therapy, and then the sufficient amount of gamma rays which are useful for imaging make it theranostically desired isotope. The applications include cancer treatment. This lutetium-177 is produced in the nuclear reactor by irradiation with the neutrons. So there is ever-growing requirement for this lutetium-177. The lutetium-177 for generating lutetium-177 we have to require enriched lutetium-176. So we are developing our indigenous separation technology for which is based on the Avlis process, which is based on three-step photoionization scheme. The three-step photoionization scheme is given by Dr. Asawadi et al. The solid lines indicates the hyperfine pathways for high selectivity. They have used all multimode lasers in for initial testing. This isotope selectivity offered this scheme is predominantly due to the first step transition to attain high purity in the product. SLM laser single mode lasers are essential for the first step. So we have incorporated our SLM OPO in the system. This is the RMS facility developed by Asavari et al. We have incorporated this SLM OPO with the existing system. In place of dialyzer 1, we have replaced our SLM OPO. And then found out the lutetium-176 photoionization signal. The SLM OPO tuned to this particular first step transition. This is the stability of this OPO. We have achieved a long-term stability of plus or minus 10 femtometer. The spectral line width is 200 megahertz. So we have achieved a photoionization signal. We have using this SLM OPO in the first step transition. The degree of enrichment has been increased to 2.62, better than 96%. This blue line is showing the photoionization signal obtained with the SLM OPO. The black line is signal is showing the showing the photoionization signal using multimode lasers. So my future scope is presently working on these OPO configurations and design innovations by adopting the advanced OPO technologies to develop single mode high repetition rate more than 5 kilohertz tunable in the spectral region of UV, visible and IR. Based on these compact proposed OPO systems, an all solid state laser facility could be developed for the enrichment of medical isotopes for nuclear medicine. I want to thank Dr. K. Dasgupta, former Associate Director BTDG BRC, who initiated this program in BRC, this OPO program. I want to thank Dr. Alok Ray, sir, who is my guide. and well-wisher. And I thank RC Apnaji and Dr. Sucharita ma'am for fruitful discussions. I thank Dr. DJ Biswas and former director head LNPTD and Padmalinia madam for their support in the hard times. I thank Kundu sir and Dr. S.K. Dikshit sir and Dr. Vasdev sir for critically reviewing my work. Thank Dr. Archana Sharma, Director BTD Beam Technology Development Group for her strong support and encouragement. I want to end my presentation with a quote: "A little more persistence, a little more effort, and what seemed hopeless failure may turn into glorious success." Thank you.
Thank you so much, sir. It was really very good that you have developed the laser single longitudinal mode, almost 1 kilohertz repetition rate OPO,
Yes, sir.
wide latitude OPO. I think very few labs are working on that area, and you have started applying also for the spectroscopy, also high resolution spectroscopy. So congratulations, and you should continue in that work. And maybe you have to
Yes, sir.
increase the repetition rate and
Yes, sir.
more stability also, so that you can more useful. Any
Yes, sir.
question in the audience? So what are the challenges for Someswara
Yes,
to
sir.
increase repetition rate?
Main challenge is the
visible.
temperature gradients actually. If you can handle this temperature gradients, we can increase the repetition rate.
Yeah, think is that in addition to spectroscopy, some other application for the DAE nuclear program, because it's a widely solid state
Yes, sir.
technology.
The trace analysis point of view, there are so many applications actually. If I can go to infrared region, if I can develop some OPOs in the infrared, that will be great achievement actually.
Go on working in that area. And okay, thank
Yes,
you
sir.
very much. And
Thank you, sir.
with this, we conclude this session, the last session of the third day, and I hand over the session management.
Thank you very much, Dr. Alok Ray, for chairing this session. And with this, our today's events end here. So tomorrow our session starts at 9 o'clock in the morning, and it will start with thesis presentations. So I request all the presenters who are going to present their thesis, please be there online exactly at 9 o'clock, 5 minutes prior to 9 o'clock. And I also request all the evaluators, all the judges also to connect with us 10 minutes prior to that, so that we can start the session in time. A very good night to all of you, and see you tomorrow at 9 o'clock. Thank you very much.